Good morning, Gophers. Welcome to GopherCon 2021. I am here in the amazing Microsoft Learn TV studios with my co-hosts, Aaron Schlesinger and Johnny Boursiquot. We will try to keep the dad jokes to a minimum, but we can't make any promises.
No promises.
We can pretty much promise that there will be a lot of corny jokes. We wish we could have been in person. We tried to make it happen. Unfortunately, things didn't work out. We upgraded from my office and we gained some more co-hosts, so that's a positive. First off, thanks to all of our sponsors.
Just want to shout out a couple of them. I want to thank Microsoft, Capital One, and Salesforce. They were instrumental in helping support us, getting the show online on really short notice. So do make sure to visit the virtual meeting spaces. You can see them on the agenda on GopherCon.com. They do require you to sign up, so make sure to do that. And there's also a link to our Discord. So do make sure to go chat with our sponsors in their channels on Discord as well.
Yeah, and the VMS is the virtual meeting spaces. Some of them are doing fun little trivia games. Some of them are doing open office hours to talk to them about the things that they're working on.
Yeah. Great technical content in there too.
So there's some technical sessions.
Indeed. So listen, we are streaming on multiple platforms, but that also means that there's a chat and conversation and engagement going on all of these platforms. We would like to centralize that, however, on Discord. So if you want to perhaps heckle the MCs, especially Aaron for not getting the memo about the attire color and all that stuff, that's the place. That's the place to do that. The speakers and sponsors obviously are going to be hanging out in there. So every time you see a talk, you want to engage them on Discord. That's the place to do it. You want to chat about the topic, whatever suits you. Jump in there and get in touch with people, make new friends, and this is what it's about. It's all about when we're doing these things virtually. So we also have a return to Gopher Town. That's something I didn't engage in last year, and it's really, really wicked. So you have this little avatar, you walk around and you bump into other people, and all of a sudden a video stream of them pops up. And it's the weirdest thing in the world to me.
You get to like sit down at a table and play chess with somebody.
Yeah, it's like great innovation. I'm sure they use Go for some of the backend systems. If not, they really should be.
If they don't,
we're gonna have
emails.
We're gonna have words. Yeah, there will be exchanges. But links to all of these places are available on the GopherCon.com homepage. So there's a section for all the things you should know as a Gopher attending GopherCon virtually this year. You'll get the links to all of these places all in one place. So. A special thanks to the speakers. All the speakers you're going to see today, those, the majority of them are live in the studio with us, and we thank them for making the trip, for coming out here and being part of this amazing journey of ours. And we also have some pre-recorded ones as well for those who couldn't make it on site. But we do appreciate our speakers. They are a huge part of our community, and every time they make the effort to come up with content, sort of endure all the anxiety and stress that sort of predates having to basically face all of you and deliver that content. We do appreciate them for that, and we give them a big shout out.
Huge shout out. Yeah. And there's a special channel on Discord, right? There's Peanut Gallery.
Yes.
That's the Peanut Gallery. Yeah.
Last year on Discord, we created a channel called Peanut Gallery. That is where you can go to heckle all of us. Mm-hmm. Oftentimes, we'll be looking at it while we're here, and we'll interact with you, and sometimes when we're outside the studio. So if you want to heckle the MCs, you can do that. We'll invite the speakers to come heckle us from behind the camera, too. Mm-hmm. So.
Especially me. Tell us what you think about the color scheme over here versus the lighter colors over there. Feel free. Yeah, I'm pretty confident in my choice. Yeah.
Yeah. So we also have some additional contributed content from outside.
Yeah. So we've got Mark Bates, who put together the lightning talks this year. And we've got a really, really great year of lightning talks that are going to be coming up. Is it later today, I believe? I think so.
Yes, I've got to look at the schedule.
Yeah, I think it is. We'll confirm.
But yeah, Mark does a fantastic job every year of putting together lightning talks. If you've not spoken publicly before, it's also a really great opportunity to try that out. They're short, most places will do 5 to 7 minutes to talk about a hobby, a personal project, or thing you're doing at work. So it's a nice way to kind of dip your toes into public speaking if you haven't done that before.
Highly encouraged.
Definitely.
Unfortunately, we're filled up for this year, but
yeah. I mean, there's always next year, of course, too. Even if you are experienced with public speaking, it's a great way to try out a new idea or test out the waters, so to speak, for your new idea. So that's great too. I also want to thank GoTime. So the GoTime team is back this year. The GoTime podcast is back this year. They're going to be contributing some content as well. One of the coolest things I'm excited about from GoTime is a Family Feud style game. This is where members of the Go team kind of
essentially
compete,
they survey, they'll survey a broad audience, in this case it's you, the Go community, about a bunch of questions. You'll provide answers, and then they have to guess what the popular answer was. Correct or not correct.
It's great fun.
We did an episode of that actually, very much like this one.
Yeah, it was quite humorous
it
because all of
was-
us are dying. Like, why is that the most popular answer?
we're obviously, we've been doing Go for a while, and we can tell the answers from those who are still sort of learning. Going like, well, that's not a keyword, so we're being very, very specific about what.
Then you can also see who's trolling
You
too.
can see exactly. My favorite language is COBOL. I'm like, what? Really?
And so in order to make this game more fun, we encourage you to actually go complete the survey. The more people who answer the questions, the more entertaining this is going to be. You choose your own adventure, whether you want to troll with the answers, whether you want to give technically correct answers. You can do that at gotime.fm/GS, short for Gopher Say, which is what they're calling the game. So we encourage all of you to go participate in that survey.
Yeah, I mean, that is going to be great fun. I think, we've got, almost 4,000 people watching the live stream.
We have over 5,000 people who have subscribed.
I got to
And so we've probably acquired more people on YouTube organically as well.
Yeah, you got to update your number just like your shirt.
Yeah, that's very true. Fair enough, yeah. Peanut Gallery, let me have it. Let's see. Let's hear it. Yeah.
Now we're going to have to buy you a matching shirt for tomorrow.
That's fair.
Yeah, you'll see me tomorrow with a tie-dye or something. Yeah.
Apparently, Learn TV, they didn't hand us a wardrobe crew or makeup crew.
Yeah, right. We just showed up with what we had.
So so we've got a lot of exciting content planned over the next 3 days. I know some of this starts early for some of you, so we really appreciate you joining us early. There will be a rebroadcast later today where you'll be able to see everything, including the MC sessions kind of replayed. So if you need to step away, we kind of recognize that. In addition to that, all of the primary content, I should say, the VMS content isn't recorded, but all of the primary content is recorded. It'll end up on our YouTube channel with everything else over the next couple of days. So don't feel bad if you have to miss anything. You'll just miss our lovely faces.
Yep, our lovely faces and our Brady and our dad jokes too. Yeah,
and the dad jokes.
Okay, so coming up next.
Yeah, I mean, we're really excited for all the great sessions here that are coming up. We have a very generic talk coming up, I would say. What would you say?
I mean, technically, it's to talk about generics.
Yeah.
Not from generic people, though.
Not
because
from,
these are,
certainly not. Yeah. So who do we have coming up?
So coming up next, we have 2 members of the Go team. We have Robert Greisemer and Ian Lance Taylor, who are going to be talking to us about generics, which I know all of you are excited about. There's been a lot of momentum there, so they're here to give us an update, and I'm really looking forward to that.
Yeah, me too. So take it away, Robert and Ian.
Thanks very much for the introduction. Hello, everybody. Good morning. We had a really hard time with the title this time. We had to change it a couple of times, but we stuck with generics. We've all been waiting for this moment for some time now, with excitement or perhaps with trepidation. But that moment has come. generics will officially be part of the language starting with Go 118, released for schedule sometime next February. We have talked about generics at past GopherCons. Last year we presented a detailed design. We had a working prototype implementation. We had finalized the syntax. We had figured out how to represent constraints as interfaces. And we had a working type inference. But there were a few things that we were not entirely happy with. In the meantime, I think we have figured out these last issues. I'm personally very happy with where we arrived. We have a design that is pretty clean. It is 100% backward compatible with existing programs, and it has some room to grow. And most importantly, there is still a feel of this is Go. So what exactly is new? If you look at the step back a little bit and look from a 30,000 feet point of view, there's really just three things. And those three things are obviously type parameters for functions and types. These are the visible signs of genericity. And then there's a new, different view of interfaces. They are now not just able to define sets of methods, but also sets of types. And finally, type inference, which hopefully should smoothen out the generic code a little bit and make it a little bit more lightweight. I'm going to cover briefly each of these topics to give you kind of a flavor of the things to come. So let's start with type parameters. A type parameter gives you the ability to parameterize a function or a type with types. A type parameter list looks very much like an ordinary parameter list, except that we use square brackets instead of parentheses. I'm going to show you a couple of examples to show you how this works out in practice. So this is your generic min function that you've seen probably many times, probably written a gazillion of times, and hopefully we don't have to write it anymore in the future. We can make this function generic by replacing our float64 type with a type parameter, in this case t. And because we have a new type t here, we also have to declare it, and that happens in this type parameter list, which is marked here in red. When we want to use this min function for int arguments, we have to call it, of course, with our int arguments, but we also have to provide the respective type, which is int in this case. Providing this type argument to the function is called instantiation. That's a fairly important part in generic programming. Instantiation happens in two steps. First, all the provided type arguments are substituted for their respective type parameters. And then in a second step, after substitution has happened, the compiler checks that each type argument implements its respective constraint. And what that exactly means, I'll go into it a little bit later. But if instantiation fails, or I should say if that second step fails, then instantiation fails, and in this case, your program is not going to be valid. So going back to our original example, we can instantiate this generic min function just by itself without actually calling it like this. We provide a float64 type argument to min, and then we get a non-generic min function, which is essentially our original min function. And we can then call it like any ordinary function. And just how to see how this looks for types, because we can parameterize types, of course, as well. Here's an example of a generic binary tree. And here the data type is generic. We use a type parameter t again. And we can now create an instance of a string tree, for instance, by instantiating this generic tree with the string type. We can also have methods on generic types. I'm not going to go into details here. So let's talk a little bit about the kind of types that a type parameter can be instantiated with. Let's talk about type sets. So an ordinary parameter list has a type for each parameter. So in this case, we have the type is float64. And this type actually tells us what kind of values are valid as arguments for x and y. So this float64 type is a set of values. Now, in type parameter lists, each type parameter also has a type. And this type is kind of a meta type, and it tells us what kind of types are valid for this type parameter. So this meta type actually defines sets of types, and we call this a type constraint. Now, in our generic min function, the type constraint is imported from the constraints package. This is a new package in our standard library. And here, the ordered constraint describes the set of all types with values that can be ordered in some ways. And in our case, they can be compared with the less than operator. And the constraint ensures that only types with orderable values can be passed as arguments to this type parameter. And it also tells the min function that within its body, operators of types that are of this type parameter t can be, operands of that type parameter t can be used with the less than operator. In Go, constraints must be interfaces. Interfaces define methods, and so it's obvious that we will be able to define type constraints that require certain methods to be present. But constraints ordered is an interface too, and the less than operator is not a method. So how does that work? So until recently in the Go spec, an interface defined a set of methods. If we have an interface with methods A, B, C, then we say that the interface defined has a method set with the methods A, B, and C, and every type that implements those methods actually implements that interface. But there's a different view. We could look at the set of types that implement those methods and then say that the interface actually defines that set of type. Now, each type that is an element of this type set implements that interface. And it's pretty obvious that these two views are essentially identical. I mean, for each set of methods, we can imagine this typically infinite set of types. And now we're just saying the interface defines that infinite set of types. And if we want to check if a type implements the interface, we just check whether that type is an element of that set of types. But this view as a type set has some advantages because we can now control it in new and different ways. For instance, we can add types explicitly to the set. And in order to make this happen, we have extended the syntax for interfaces exactly to be able to add additional types. For instance, here we have an example of an interface with 3 types, int, string, and bool. And this interface defines the set of exactly those 3 types. Or another way of saying this is that these 3 types implement this interface. Now, if we're going to go back to our previous example, remember the constraints.ordered interface. This is the declaration of that interface. Here, this declaration states that ordered is the set of all integer, floating point, and string types. The vertical bar expresses a union of these types, or in this case, type sets. And integer and float are interfaces that define type sets themselves that are similarly defined in the same package. Note that there are no methods on this interface. Usually, we do not care about a specific type. Like, we don't want to have a set that just contains the int or string type. We care usually about all the string types and all the int types. And that is what this new token tilde is for. Tilde string, in this case, denotes the set of types that consists of all types whose underlying type is string, or all string types. So of course, with Go 118, we'll still want to be able to specify methods. And so we'll still be able to do that, of course, in interfaces. And we can embed other interfaces as usual. But we will also be able to embed arbitrary types and unions of this form and tilde type elements. Now, used as a constraint, the typeset defined by a constraint interface defines exactly the type arguments that are permissible as arguments for the respective type parameter. And within a generic function, for operands of type parameter type, only the operations that are permitted for all the types in the respective typeset are permitted on those operands. Interfaces used as constraints may be given names such as constraints.ordered, or they may be used directly inline inside the type parameter list. For instance, here we have a type parameter list that declares two type parameters S and E, which might be written like this. So here S is a type parameter that requires a slice type, an arbitrary slice type whose element type is not further constrained. This is a fairly common scenario. And because it is so common, we've introduced some syntactic sugar that allows us to leave away, or actually we've removed some syntactic sugar, I should say, that allows us to leave away the interface curly braces around it. And we can just write the second line, as I've shown here. And finally, because the empty interface appears quite often in type parameter lists, and for that matter in Go code, we introduced a new pre-declared identifier, any, that is an alias for the empty interface. And so this, any identifier can be used anywhere instead of the empty interface. Interfaces that define typesets are a powerful new construct, and they really make constraints work in Go. But for now, such interfaces may only be used inside type parameter lists in constraint position. But it's not hard to see how such interfaces might be useful in general for arbitrary variables. And maybe that is something that we will do in the future. And I think there is an issue for that. So finally, the last but not least new mechanism, it's type inference. I'm only going to touch very briefly on this. Going back to our original example, with type parameters comes the need to pass type arguments, which can make for rather verbose code. And though frequently these type arguments, they can actually be deduced from the ordinary parameters that are arguments that are passed in a function call. So here we have our generic min function again. We pass two arguments A and P of type float64, and by comparing those types against the parameter types, here there's only one, T, so by comparing T against float64, we can infer that the type for T actually must be float64. This is what the compiler does, and if it can do that successfully, then we can simply leave away the type argument, which leads to a function call for min that looks like any ordinary function call, no type parameters or anything. Now, the exact details of type inference are pretty complicated, but using it is not. Type inference either succeeds or it fails. If it succeeds, type parameters can be left away, and all is good. The generic function call looks like any ordinary function call. If it fails, then the compiler will complain, and we simply provide those type arguments. Now, we have tried to strike a balance between the complexity and inference power for type inference, and we probably haven't gotten it quite right. And so there's some room to fine-tune and refine over time. The effect will be that more programs won't need type arguments. But the important point is that programs that don't need type arguments today, they won't need type arguments tomorrow. That's really it. 3 major new things in Go: type parameters for functions and types, a more powerful form of interface types to express constraints, and type inference to smoothen out programming generic code. Thank you very much. I'm going to hand it over now to Ian Lance-Taylor, who will go a little bit more in detail with type inference and how to use generics in Go. Thank you very much. Thanks.
Thanks, Robert. Thanks for that great description of generics as they're going to come into Go 118. So I'm going to start by describing a particular kind of type inference, which we call constraint type inference. So I'm going to start with an example. Suppose we want to scale a slice of integers, returning a new slice in which each element has been multiplied by some value. We don't care what the exact type of integers are in the slice, so it's easy to write a generic function for this, similar to the ones that Robert showed earlier. But there is a problem with this particular definition, which I will explain as we go along. Now, continuing the example, suppose we have a multidimensional point type, where each point is simply a list of integers, giving the coordinates of the point. Naturally, our type has methods. For the purposes of this example, the details aren't really important. Sometimes we want to scale a point. Since a point is just a slice of integers, we can just use the scale function that we wrote earlier. Unfortunately, this doesn't work. We got a compilation error, which you can see on the screen here. What went wrong? The problem is that the scale function returns a value of type slice of e, where e is the element type of the argument slice. When we call scale with a value of type point, whose underlying type is slice of int32, we get back a value of type slice of int32, not a value of type point. And of course, value of type slice int32 does not have any methods. So this all follows from the way that generics work. But for an example like this, it's not what we want. In order to fix this, we have to change the scale function. The changes are highlighted in red here. We've introduced a new type parameter, s. That's the type of the argument. We've constrained that type parameter s so that the underlying type of its argument must be a slice of some element type e. So the first argument to the function, the first regular argument, is now type s rather than slice of e. And the result type is also now slice of s, is now just plain s. Since e is constrained to be an integer, the effect is the same as before. The first argument has to be a slice of some integer type. The only change to the body of the function is that now we pass s rather than slice of e when we call the make function. This new function acts the same as before if we call it with a plain slice. But if we call it with the type point, we now get back a value of type point, and that's exactly what we want. But it's fair to ask, and here we're going to get into the inference part of the talk, why is it okay to write the call to scale without passing explicit type arguments, as shown in the comment there? The new scale function has two type parameters, s and e. In a call to scale where we don't specify any type arguments, function argument type inference that Robert described lets the compiler infer that the type argument for s is point, as Robert showed us. But the function also has a type parameter e, and we need to have a type argument for that type parameter. The process by which the compiler can infer that the type argument for e is the element type of the slice is what we call constraint type inference. The exact definition of constraint type inference can be found in the language spec, or rather it can soon be found there. It's not quite ready yet, but soon. There is a description in the generics proposal, which you can find in the link at the top of the slide. Those are the complete formal definitions, though. Today I'm going to describe it somewhat less formally in a way that I hope is easy to understand. Constraint type inference deduces type arguments from type parameter constraints, hence the name. It's used when one type parameter has a constraint defined in terms of another type parameter. When the type argument of one of those type parameters is known, the constraint is used to infer the type argument of the other one. The simplest and by far the most common case of constraint type inference uses a constraint of the form tilde type for some type, in where that type is written using other type parameters. We can see this in the scale example. S, the type parameter s, has the form tilde followed by a type written in terms of other type parameters, in this case the type parameter e. Since s is written in terms of e, if we know the type argument for s, we can infer the type argument for e. S must be a slice type, and e is the element type of that slice. So let's put it all together. In the call to scale, p is a point whose underlying type is slice int32. Function argument type inference uses the argument lowercase s to infer that the type argument for uppercase s is point. That matches the tilde slice e. Remember that tilde slice e means that the type argument can be anything whose underlying type is a slice of some element type. In this example, the untyped constant 2 doesn't tell us anything using function argument type inference. So the compiler then applies constraint type inference. Since S we know is point, and point's underlying type is slice of int32, E is inferred to be int32. The compiler does have to then verify that int32 satisfies E's constraint, which it does, since int32 is an integer type. Now, all the type arguments have been successfully inferred, so the function can be instantiated and called with no explicit type arguments required at the call site. That was just an introduction to constraint type inference and why and how you may want to use it. As I said before, for full details, see the generic proposal or the soon-to-come updates to the language spec. For the final part of our joint talk, I'm not going to discuss what generics are or how to use them, but rather when to use generics and when not to use them. To be clear, this portion of the talk will provide general guidelines, not hard and fast rules. Use your own judgment. But if you aren't sure, I suggest that you use the guidelines I'm going to discuss now. Let's start with a general guideline for programming in Go. Write Go programs by writing code, not by defining types. When it comes to generics, if you start writing your program by defining new type parameter constraints, you're probably on the wrong path. Start by writing functions. It's easy to add type parameters later when it's clear that they'll be useful. That said, let's look at cases where they are useful. One case where type parameters can be useful is when writing functions that operate on the special types that are defined by the language, slices, maps, channels. If a function has parameters with those types, and the function code doesn't make any particular assumptions about the element types, then it may be useful to use a type parameter. For example, a function that returns a slice of all the keys in a map of any type, any map type. The code wouldn't assume anything about the map key type. That makes it a good candidate for using type parameters. The alternative to using type parameters for this kind of function is typically to use reflection, but that's a more awkward programming model. It's not statically type checked. It's often slower as well. Another case where type parameters can be useful is for general purpose data structures. By a general purpose data structure, I mean a data structure like a slice or a map, but one that's not already built into the language. For example, a linked list or a binary tree. Today, programs that need such data structures write them with a specific element type, or else they use an interface type. Replacing a specific element type with a type parameter can produce a more general data structure that can be used in other parts of the program, or perhaps by other programs. Replacing an interface type with a type parameter can often permit the data to be stored more efficiently. In some cases, using a type parameter instead of an interface type can mean code can avoid type assertions and can instead be fully type checked at compile time. For example, here's what a binary tree data structure might look like using type parameters. Each leaf node in the tree contains a value of the type parameter t. When the tree is instantiated with a particular type argument, values of that type argument will be stored directly in the leaf nodes. They will not be stored as interface types. Here we can see a method on the generic binary tree. Don't worry about the details or the formatting I used to fit the code onto the slide. The point is that this is a reasonable use of type parameters because the tree data structure, and even the code in this method, is largely independent of the element type t. The data structure does need to know how to compare values of the element type t, and in this method it uses a passed-in comparison function to do that. You can see that on the fourth line in the call to bt.comp. Other than that, type parameter doesn't really matter at all. That binary tree example illustrates another general guideline. When you need something like a comparison function, prefer to use a function rather than a method. We could have defined the tree type such that the element type is required to have a compare or a less method. This would be done by writing a constraint that requires a compare or less method, using the kind of constraint as interface writing that Robert described earlier. And it would mean that any type argument used to instantiate the tree would need to have that method. But that would mean that anybody who wants to use tree with a simple data type, like int, would have to define their own int type and write their own compare method. If we define tree to take a function, as we did in the example code we just saw, then it's easy to pass the desired comparison function. And if the element type happens to already have a compare method, we can simply pass a method expression like element type.compare as the comparison function. To put it another way, it's much simpler to turn a method into a function than it is to add a method to a type. So for general purpose data types, prefer a function rather than writing a constraint that requires a method. Another case where type parameters can be useful is when different types need to implement some common method and the implementation for the different types all looks the same. For example, consider the standard library's sort.interface. It requires that a type implement 3 methods, len, swap, and less. This example shows slicefun, a generic type that implements sort.interface for any slice type. For any slice type, the len and swap methods are exactly the same. The less method requires a comparison, which is the fun part of the name slicefun. As with the earlier tree example, we will pass in a function when we create a slicefun. And this code shows how slicefun is used to sort any slice using a comparison function. Here we use type parameters to implement the sort.interface methods for any slice type. Using type parameters is appropriate for this kind of example because the methods look exactly the same for all slice types. At this point, I should mention that Go 119, not 118, but 119 will probably have a generic function to sort a slice using a comparison function. And that generic function will probably not be implemented using sort.interface. But the general point is still true, even if this specific example will most likely not be useful in the future. It's reasonable to use type parameters when you need to implement methods that look the same for all the relevant types. Now let's talk about the other side of the equation. When should we not use generics? When are type parameters not a good idea? Well, Go has interface types. Interface types permit a kind of generic programming. For example, the widely used io.reader interface provides a general mechanism for reading data from any value that contains information, such as a file, or that produces information, such as a random number generator. If all you need to do with the value of some type is call a method on that value, use an interface type, not a type parameter. io.reader is easy to read, it's efficient, it's effective. There's no need to use a type parameter to read data from a value by calling the read method. For example, some people might be tempted to change the first function signature here that just uses an interface type into the second version that uses a type parameter. Don't do this. Omitting the type parameter makes the function easier to write, easier to read, and it turns out the execution time will most likely be exactly the same for both versions. Going back to the choice between type parameters and interface types, when there is a common method that is used by different types, consider how that method is implemented. Earlier we said that if the implementation of the method is the same for all types, go ahead and use a type parameter. Inversely, if the implementation is different for each type, use different methods. Don't use a type parameter. For example, the implementation of read from a file is nothing like the implementation of read from a random number generator. That means that we write 2 different read methods, and neither method should use a type parameter. Although I haven't talked about it too much today, Go also has reflection. Reflection permits a kind of generic programming in that it permits you to write code that works with any type. If some operation has to support even types that don't have methods, so that you can't use an interface type, and if the operation is different for each type, so type parameters aren't that helpful, use reflection. An example of this is the encoding JSON package in the standard library. We don't want to require every type that we encode to support a Marshall JSON method, so we can't use interface types. But encoding an integer type is really nothing like encoding a struct type, so we shouldn't use type parameters. Instead, the package uses reflection. The code's too complicated to show here today, but take a look at the package if you're interested. In closing, this discussion of when to use generics can be reduced to one simple guideline. If you find yourself writing the exact same code multiple times, where the only difference between the copies is that the code uses different types, consider whether you can use a type parameter. Another way to say this is that you should avoid type parameters until you notice you're about to write the exact same code multiple times. Thanks for listening. I hope you've learned something today. I hope you'll all be able to use generics in Go. I hope you will all use generics in Go when the 118 release comes out. I hope you use them wisely and well. Thanks. And now, we'll hand it back to Erik, Johnny, and Aaron. Keep the excitement going here at GopherCon. Thank you.
Thank you so much, Robert and Ian. I can't tell you how excited I am for, next February? Yeah, this is going to be, I'm going to cuddle up to some generics, during the winter, snow falling, by sitting by the fire, getting to, you know how to use the type constraints and things. Yeah, this is exciting stuff. And
I'll be abusing them and then finally learning to use them appropriately.
Yes, all of it, we shall all be abusing generics in the beginning, as we tend to do.
Yeah.
But yeah, I mean, did you find anything particularly interesting that you didn't already know was coming, Aaron?
The tilde operator, I had read
Yep,
about it,
yep.
but I didn't fully grasp it, I think.
Yeah, indeed. And I really appreciate the guidance towards the end there that Ian gave, basically of when to use generics, rather when you should consider using them, and really other ways you should avoid using them. I think that as we embrace generics and start to understand how to actually use it, sort of in an idiomatic way, it's going to become clear what the patterns are, what the best practices are. But in the meantime, I think we have to give ourselves a little room to experiment and to kind of make mistakes.
So I should forgive myself for writing.
Yeah,
terrible code,
you'll be
Okay.
you'll be all right.
I feel a little better now.
Fully functional FP library and Go. Forgive yourself after.
Forgive
you
yourself.
forgot.
That's awesome.
And so in our peanut gallery, we've had some commentary about the look and feel of the studio.
Yeah, I mean, I think the peanut gallery was probably livelier than any of us expected. So
Right.
thank you all for participating there. We had great commentary about the talk, intelligent conversation. My favorite part, I think, was there was a comment that the studio looks like a nightclub. I
Yeah,
think.
and so I mean, it may have been purposeful, right? Like, I mean, there's no after party, so we're going to have to
Right.
dual purpose this space.
Exactly.
So that means you're going to stand up and start dancing?
We
or-
tried to get a disco ball.
Yeah.
Oh,
and,
that
it
wasn't in the
didn't
budget?
come through.
We have a break dancer. Or do you break? Maybe you can do it.
When I was in
Yeah.
high school,
Yeah,
not
so-
anymore.
okay,
Broken
not
femur
anymore.
pretty much
Okay.
put an end to that
All
one.
right, we'll get a break dancer to come in. And yeah. So yeah, I mean, thank you all again for participating there. Please do continue. That's some great conversation, and you can see, myself, Eric, and Johnny. We participate also while the talks are going on, and we're totally excited for that too. So
Indeed.
We've got some additional fantastic talks coming up.
Yep.
In addition to the main content that you'll see, if you go to the agenda page, we talked about it kind of in the opening. There'll be some virtual meeting spaces. There's a couple of them coming up. CockroachDB has a VMS coming up. Microsoft has one on GitHub Actions. And then Buff is doing an open office hours as well.
yeah.
So make sure to check those things out. Those are the only things you have to register for. Just the platform itself will require you to kind of register to get into those VMSs. Outside of that, participate as you are on all of the platforms we're streaming to right now.
Yeah. And speaking of sponsors, I think we have one with us now.
Yes, so we have Stephen Houston here with us from Bread to talk to us a little bit about how they're using Go for payments.
Yeah, and this is an interesting space, I think. It's something that we may not have seen too much of yet.
Now,
So-
when you mean payments, are we talking like cryptocurrency or just regular good old dollars and
No,
cents
just
and
good,
things?
good old dollars.
Find out.
No, yeah, let's go find out, huh?
See if we can get him on. Yeah. All right, Stephen, can you hear us?
Happy GopherCon.
Yeah, likewise to you too. So yeah,
If-
Johnny,
if
I
we
mean,
could,
that's
we having a Travolta disco ball off. Did I hear that right?
You didn't ship it. That was part of the deal for the sponsorship, man.
There-
You were-
There's 2 days left. You could overnight it to us.
Yeah,
I'm
this
just
is
Man.
possible. Yeah.
We'll have to look at that. Maybe we can use some of our Bread Payments products to make that happen.
yeah.
Or somebody could hack the lights. I mean,
Okay, yeah, Gophers, get on that. Let's do it.
so you're using Go in part of the payment workflow?
Yeah, in fact, Bread pretty much uses exclusively Go in the back end. We're buy now, pay later, so we do have loan options and things like that. So for managing like loan schedules and when payments are due and balance histories and transactions and all of that, it's done using services written in Go. Generally, gRPC communication going on there between services. We have front end that's JavaScript, and so we'll do some REST and things like that with the front end. We integrate with some third parties. In some cases, maybe GraphQL that we do using Go. It's a pretty neat setup, and we're having a lot of success with it, and pretty much the whole flow of how that works is built on Go.
Now, who'd you have to bribe or threaten to be able to use Go inside the financial industry?
That would have to be a question for someone else, because I just wrote the code. No. I think it's a good choice, and we're having good success with it.
So when I think of payments, I think of a lot of regulation, a lot of requirements, for security and so forth. So can you walk us through maybe some of the a little bit more special considerations you might have had to make when you're building these systems?
Yeah. So we have a lot of different teams at Bread that are kind of built to handle that, and we have a great legal team and compliance team. Our team of product managers are just excellent, and they meet requirements. They handle the compliance. They pass that down to us. We implement it generally if we're going to make any changes, to that scope or anything. We obviously have a process of running it through our different teams to make sure that we're meeting all necessary steps. It's definitely a challenge. You can't just you can't just try to resolve things or fix things on your own without worrying about, like you said, all that compliance.
Yeah, for sure. I don't know about you guys. I've had to run up against compliance every once in a while over the past couple of years.
I worked in healthcare for a while. That was not fun.
Yeah, and you hear it. Sometimes it's not so bad when you actually have to do it, but then you hear it and you're like, oh, this is going to take me a year or something to implement. So.
That's the least favorite part of every engineer's job, to be part of all the sort of the running around you have to do to check all those boxes.
Yeah.
Can you just leave me alone and let me write code?
That's, like I said, we have great PMs at Brad that really do the majority of the running around for. I can't say enough good things about them.
Nice.
Sweet.
That's awesome. Well, it's been great talking with you, Stephen. We've got a run-up of content here, so we're pretty excited about. We wish we had more time to talk with you, but it's been great hearing about how Bread is leveraging Go inside the financial space, and I hope to see more kind of sectors that we wouldn't have traditionally see these things in.
Yeah, this is novel, at least for me. I haven't seen a lot of Go in the financial sector yet, so that's great that they're pushing these boundaries, and yeah, I'd love to see it in more
I'd love to see it in healthcare, too.
Yeah, right. If they can do compliance in finance, why not in healthcare, too?
You heard it here first. Aaron says use Go in your compliance. You just smooth, just ease your way. You'll be smooth as butter. You just,
There's gophercompliance.com. That's my site. Everyone sign up. Let's do this.
Sign up for my
He
newsletter.
will happily help you with it for $500 an hour.
Yeah, absolutely, yeah. Yeah, well, so speaking of new content, our next content is coming up. We have got Felix. I apologize in advance, Felix, if I get this wrong. I think it's Geisendörfer, maybe?
Oh, that sounds.
Yeah,
that sounds right.
Anyone can say it sounds right, so I appreciate that.
I got your back.
Thank you,
I got
Johnny.
your back.
Thank you. Yeah, so Felix is a staff engineer at Datadog, and he is going to talk to us about profiling and observability from scratch. So just a tiny little bit about Felix before we go to his talk. This session is for folks who are interested in reducing costs and latency or debugging those really tough problems, especially in distributed systems, your memory leaks, your network problems, your communication problems, that kind of stuff. This is something that we run up against, probably all three of us, maybe every day even, when we work on our distributed systems in our jobs. So, I'm super excited to see this content from Felix. coming up right now. Shall we go to the talk?
We shall.
All right, well, take it away, Felix.
Hey everybody.
Somebody
It's good
commented
here to
about
be at
the sign
GopherCon
bucket.
2021. The title of my presentation today is Go Profiling and Observability from Scratch. The target audience for this presentation are intermediate Gophers who are interested in reducing resource consumption, improving latency, or mitigating incidents afflicting their Go applications. The agenda for doing this is to start by introducing a simple model for scheduling and memory management, which is important to understand Go performance. And then we'll talk about profiling, including all the various profilers. And for the first time, we'll also look at the overhead of the various profilers built into Go. This is the biggest part of the presentation. Additionally, to give you a full picture of Go observability, we'll also talk a little bit about tracing, metrics, and third-party tools that you can use. About myself, my name is Felix Geisendörfer, and I'm currently a staff engineer at Datadog working on continuous Go profiling as a product. Before that, I spent 6.5 years at Apple working on factory traceability stuff using PostgreSQL and Go. In my spare time, I like to play beach volleyball and to contribute to open source. If you're interested in the latter, you can check out my README on GitHub to find which projects I've been working on. All right, let's talk about scheduling and memory management. Go's primary job is to multiplex and abstract hardware resources, such as CPU, memory, and networking. In fact, this is very similar to what an operating system does. And if you look further down the stack, you'll see that these patterns of memory management and scheduling exist everywhere. For example, your SSD has a built-in garbage collector. So it's really important to learn these patterns once, no matter at which layer of the stack, because they'll be useful for any future endeavors you might have as they repeat themselves in the landscape of computing. The following model is very simplified, and it might be a repetition for some of the more experienced Gophers here. But I hope that the more simplified picture I'm going to present today is going to be more useful for intermediate folks who may not be thinking about what the runtime and scheduler and memory management system of Go usually have to accomplish. To introduce this, I'll use a simple example of an HTTP GET request. So we're requesting an URL here, and then we're printing out the status code. From the scheduler's perspective, what might happen is that the scheduler initially schedules our Go routine, called G1 here, onto a CPU core in order to prepare the HTTP request. Then the Go routine has to wait for the network on the response, which means the scheduler can take this Go routine off the CPU and do something else. In this case, there's nothing else to do, so the CPU core remains idle, just waiting on the network. And finally, once the network response comes back, the scheduler can put the G1 Go routine back onto the CPU to run the printf code to print out our status code. Reality is, of course, a little bit more complex than this, but I think this gives you a good idea of what the scheduler is doing. Another way to look at this is to think about the scheduler putting Go routines into one of three states. They're either executing, waiting, or runnable. In our example, G1 starts in the executing state while preparing the HTTP request. Then while waiting for the network, it gets put into the waiting state. And then once the network response comes back, it gets added to the runnable state, which means the scheduler is now looking for a CPU core to schedule it. And finally, the Go routine gets scheduled onto the CPU core again to run the from printf statement. The bigger picture for scheduling then looks like this. You usually have a bunch of Go routines that are executing on various CPU cores. In this case, you could actually tell that there's 50% CPU utilization right now. Then certain events such as sleeping, I/O, channels, or mutexes can transition a Go routine from the executing into the waiting state. And Go programs usually have a lot of Go routines in the waiting state. The scheduler is designed to handle hundreds of thousands of Go routines in that state, so that list can get quite large. Those Go routines usually eventually get awoken again by their sleep finishing, or the I/O completing, or the channel or mutex operations being done, and those Go routines become runnable. A well-running Go program usually shouldn't have many Go routines in the runnable state. In this case, we don't see any of them here, because if you get a lot of Go routines here, it actually means that you have more work to do than your CPU cores can handle. And finally, if you have runnable Go routines and the CPU core becomes available, they get scheduled again. So yeah, this was a very simplified picture. In reality, it's more complicated, as Go schedules Go routines on operating system threads, which are then running onto the CPUs. The schedule is also deeply integrated with networking channels and mutexes to accomplish the things you've seen before. And as I mentioned, it's very scalable. Now let's talk about memory management. What you see here is a big picture of a program, Go program's memory, divided into several stacks for G1, G2, G3, and a heap. Usually you have many of these small stacks, one per Go routine, and they start at a small size of 4 kilobytes. And you have also a big area of memory called the heap, which is used for shared data and other stuff. So let's talk about the stack first and get an intuition for what the memory management costs are on the stack. Here we have a simple program that is making an addition of 2 numbers and then printing out the results. When this program starts, the Go routine that is running has to allocate some space for the sum variable on the stack. So it puts it on this little area of memory here, and then the stack pointer that you can see on the right is pointing to the next free space on the stack in case we want to allocate more stuff on the stack. Also highlighted here is the area for the main stack frame, which includes all the memory used by the current function on the stack. Then the add operation is executed here, which needs 2 more variables to be pushed on the stack, A and B, which have the numbers 23 and 42 here, which means we allocate a new stack frame, and the stack pointer gets advanced further down again. And finally, we print our sum, but before that happens, the add function has to return, and as the add function returns, we have to sort of clear out that space on the stacks that was used for it, and that is simply done by moving the stack pointer back up to where it was before. So it's a very cheap, easy operation to free stuff on the stack. In fact, we don't even have to overwrite the data that we allocated for the add function. And then the print can happen. Now let's talk about heap allocations. Here you have a big picture of the heap, this time with a few objects allocated on it. And what I want to point out here is that the heap usually has 2 types of objects. There are the reachable ones. One of them is highlighted here in green. And what makes them reachable is that you can follow some pointers from a stack through potentially some other objects all the way to that reachable allocation here. And then you've got unreachable allocations like this one, where nobody points to it or it's pointing to nobody. And although this one, which has a pointer to something else, but it's not pointed to by anybody. So both of these allocations we just saw are garbage and can be cleaned up. And that's the job of the garbage collector, which has to periodically come in and clean up those unused objects. As you might imagine, compared to heap allocation, stack allocation is very cheap. Because with heap allocation, you first have to find a spot for the memory to be placed on the heap, which is a subject in its own right. But then the GC also has to do a lot of work to actually locate the unreachable objects and figure out that it's safe to remove them, because it has to do all this graph traversal that we've just been doing by hand. And for this reason, heap allocation and GC can often make up 20% or more of the CPU time of your Go program. So the general advice is to reduce, which means to either avoid heap allocations completely or to turn them into stack allocations. Reuse, which means figuring out a way to not throw allocated stuff like structs and buffers away, but to reuse them for another time. And recycling, which is basically just saying sometimes it's okay. You don't have to get rid of all GC work. Once you've done enough optimizations, some GC work is okay. Let the GC recycle the objects for you. One thing I would like to point out here, that because it's maybe a little unintuitive, is that reducing heap allocations can speed up unrelated code as a second order effect. And this is because the garbage collector has to iterate through all the stuff on the heap, which basically trashes all your caches, which basically makes things a lot slower just after a garbage collection, because those caches have to be repopulated with the stuff that your Go routines were actually trying to do. So optimizing memory allocations can be a very worthwhile endeavor in general. Now let's talk about profiling. The CPU profiler in Go is, as you might imagine, responsible for figuring out how much time your Go routines are spending on the CPU. In the example we had in the beginning, that is the time that we've highlighted here. The simplest way to explain how that works is you could imagine the pink gopher playing the role of the CPU profiler, and the blue gopher being the program you're trying to profile. And the pink gopher is like, hey, what you doing? And the blue gopher answers X. And then again, hey, what you doing? Y. Hey, what you doing? X. And the pink gopher just keeps a table where it keeps count of how many times the blue gopher has given the same answer to this question, which then basically gives a frequency table of events, which can be used to figure out what the blue gopher was doing during the period of profiling. A little bit more accurately described, the CPU profiler captures the on-CPU time of your code by interrupting your process for every 10 milliseconds of CPU time that it was spending, and then takes a stack trace to put into a frequency table of stack traces, like we're seeing here in the profile data section. One thing to point out here, the sample count and the CPU nanoseconds are completely redundant, and the latter is derived from the former. You can configure the sample rate using runtime set CPU profile rate, but my recommendation is to not touch this, especially in a production setting, A, because 100 Hertz is usually good enough, and B, because there's actually some problems, especially up to and including Go 1.17. So if you're interested in a few more details on how this works under the hood, the CPU profiler installs a signal handler, as you can see here. And this signal handler is being invoked by the operating system using a system call called setItimer, where the Go runtime tells the operating system it wants to be notified every 10 milliseconds of CPU time that are passing by sending a sigprof signal to this signal handler. When the signal handler receives the signal, all the Go routines and all the operating system threads in your Go program are stopped, and the signal handler passes on the information to the sigprof function. And the sigprof function is actually pretty long and complex, but the gist of it is highlighted here. It's taking a stack trace, and then the stack trace gets added to the CPU profile. So that's pretty great, but there's even better things coming for Go 1.18, because setItimer actually has some issues. In particular, it fails to deliver more than 250 signals per second, and this can bias profiles to systematically underestimate CPU spikes. See the GitHub issue mentioned here. And the good news is that in Go 1.18, Reese Hildner has contributed a patch that will fix this by using a different system call called timer create. And not only will this probably fix the 250 signal limitation, it should also get rid of some thread bias when it comes to the signal delivery. So Go 1.18 should really be a nice improvement for CPU profiling in Go. Now let's talk about the block profiler. The block profiler captures off CPU time while waiting on channels and mutexes, but it does not capture off CPU time waiting on sleep, I/O, system calls, GC, and a bunch of other stuff. So really be aware that it's only channels and mutexes that are being captured here. The profile data is basically showing you cumulative contentions and delays per stack trace, and you can configure the sample rate by using runtime set block profile rate. My recommendation for production applications is to use the value 10,000. Here's a little example of how that works in practice. Let's say you have a little program that creates a channel and launches 2 Go routines. When the Go routine 1 executes the first line of code here, which is passing the number 1 into the channel, it has to wait because nobody's reading from this Go routine. Because Go routine number 2 that can do the reading is currently calling time.sleep for 1 second. Then when Go routine 2 finishes its sleep and receives from the channel, that unblocks Go routine 1. And in this moment is when the block profiler kicks in and basically captures a stack trace of this event, of the chen send operation, and also the duration that the channel was blocked here, which in this case is 1 second. And then the program can continue. The block profiler can also do this for mutexes, and it looks very similar. Here, G1 is locking a mutex and then going to sleep, while G2 is trying to acquire the same mutex, which it can't do because it's being blocked by G1. So it has to wait for G1 to call unlock, which then in G2 causes the lock operation to proceed, And again, this exact spot here on the right-hand side is when the block profiler comes in to capture a stack trace and the wait duration. And then the program continues. Which brings us to the next profiler, because this is a little confusing. There's also a mutex profiler. And this one also captures the off-CPU time that Go programs spend waiting on mutexes, but not channels. And the profile data looks exactly the same as the block profile. And it also has a little knob for controlling the sampling rate. In this case, my recommendation would be a rate of 10, which would mean 10% of all the events. Why is this mutex profile even a thing if the block profile already does mutex contentions? Because superficially, yeah, block seems like a superset of mutex. In reality, it's not, because the mutex profile shows you what code is doing the blocking, while the block profile is showing you what code is getting blocked. And both perspectives can be useful, so you should enable both of these profilers. If this was confusing, here's a better example. Basically, the mutex profiler is different from the block profiler because, again, here's the block profiler capturing a mutex contention. As you can see, the stack trace gets captured for the lock operation in G2 that was getting blocked. And for the mutex profiler, which we're showing now, you can see that the stack trace is captured on the left-hand side for the unlock operation that caused the Go routine G2 to become unblocked. So again, two perspectives of the same events that are happening, both can be valuable. This finishes our little tour of Go profilers that are focused on capturing time. And I want to use this opportunity to talk about time a little bit more as it relates to user time. So here you have a user that is waiting for 100 milliseconds on a request. And in this particular case, the request is actually being executed by 3 different Go routines that are running concurrently, which essentially means that this request is spending 300 milliseconds of Go routine time, which is the time that is cumulatively passing for all our Go routines. And this time could then also be divided in some of this Go routine time being executed on CPU and some of it off CPU. What you can see here is that it can lead to interesting things such as 150 milliseconds of CPU time being spent to serve this request, even though the user only experienced 100 milliseconds of time. So this explains why sometimes you can see more time spent on a CPU profile than the execution duration of your request or program is. Another angle to look at this is to picture all these different times that your Go routines can be spending on this little diagram here. Go routine time is basically the cumulative time of all the Go routines. If you would capture the start time and end time of each Go routine and added up all those durations, that would be Go routine time. Then you have CPU time, which is the time that those Go routines were running on CPU. Again, this can be larger circle than the real-time circle, depending on the level of parallelism in your application. Then you have the mutex and block profile, with the block profile being a superset of the mutex time, but again with different stack traces, so they're both separately useful. Then you have what I like to call untracked off-CPU wait time, which includes several things such as I/O, system calls, or sleep, or scheduler backlog, etc., where profiling really has kind of a blind spot and cannot really capture this time, and we'll need other techniques that we'll discuss later. And then you've got real time, which is basically a subset of Go routine time that generally intersects with CPU, mutex, and block time, which all of this can be a little confusing, but hopefully this gives you a better idea of what profiling can show you and what also it can show you and where you need different tools. Let's move on to memory profiling, which is different from time profiling. The memory profiler in Go produces profile data that shows you the cumulative allocations and memory that's still in use for each stack trace. So every part of your program that's allocating, you will see how much data was allocated at a particular function or line in your program. And then you will also see how much of those allocations are currently still alive on the heap. The memory profiler doesn't do that for every allocation. Instead, it's sampling every 512 kilobytes of malloc using a Poisson sampling algorithm. And the memory profiler also keeps track of when the objects are freed, especially only for those sampled objects. And that is used to later calculate the in-use fields that you see above. The memory profiler also has a sample rate control knob, which is called runtime mem profile rate. But my recommendation is to leave this untouched, especially in production, because it's a pretty good default. If you want to see this from another perspective, let's assume we have a simple main function that allocates a user struct and then prints out the value of it. And what happens here is the moment that this line executes, essentially the memory profiler can capture a stack trace along with the information on the size of this allocation. And the reason this works is because the compiler internally converts this allocation here into a function call to runtime new object. And that is where then eventually the memory profiler gets to execute the stack trace capturing logic that I just mentioned. And then eventually the program can continue running. The last profile that we're going to talk about today is the go-routine profile. The go-routine profile captures essentially go-routine counts per stack trace and can tell you how many go-routines you have in total and what was the last known function and line that those go-routines were essentially executing. One word of warning here, the go-routine profile is a stop the world profile that has to temporarily stop all your go-routines. And the amount of time that this stop the world phase lasts is directly proportional to the number of go-routines used by your application. So if you have a very high number of go-routines, this can become an issue for your tail latencies. Unfortunately, there's not a lot of good workarounds right now because the go-routine profile does not offer any sampling mechanism, so you always have to iterate over all of them and get all the stack traces. But still, there's a few very good use cases for this. For example, detecting go-routine leaks, or you can also use this to diagnose why a Go program might be hanging, because there's a debug2 output that can show you which go-routines are waiting for longer than 1 minute, which can be super useful in some situation. Notably, the clock profiler cannot tell you this because it will only emit events after some clocking event has finished. So some still ongoing clocking event, you can only diagnose with the go-routine profile, essentially. Next up is tracing, which we'll talk about briefly because it really complements profiling in ways that are super useful, and you should at least use at least some amount of tracing in your applications. At least that's what I think. The main idea of tracing is, if we go back to our Hello World program here, or Hello HTTP, what we basically end up doing to trace it is to capture a start time of this operation, and then we print out how long this operation took. And this is a form of tracing, where we're basically capturing some interesting information from our application performance-wise, along with a time duration that it took. And again, what's cool here is we can capture the entire duration that this operation lasted, including the idle time on the network that we're somewhat blind to when we use just profilers. Of course, there's a little caveat here. Oftentimes the Go runtime will utilize channels to do networking, so sometimes this shows up on a clock profile as well, but you can never be quite sure if that will be the case, depending on how the libraries that you're using are implemented. There's various forms of tracing, but what I think they all have in common is the recording of time-stamped events. The distinction with logging can be a little bit muddy, so it depends on context what people tend to call tracing or not. Where it becomes very clear is distributed tracing, which is basically the idea of tracing requests and latency information like we've just shown, but doing it through an entire system of multiple applications by essentially passing request IDs from one system to the next, so you can connect all these sub-requests of a user request together and understand how long they're taking. I highly recommend this to understand performance from a system perspective. Then there's runtime tracing, and Go has a built-in tracer that does this, which basically emits a lot of events about runtime internals. And this one is also really cool because it can shine light on profiling blind spots such as I/O, sleep, GC, scheduler, backlog, etc., that are difficult to understand with profiling. And another form of tracing that currently doesn't exist in Go is tracing profilers, which would basically trace every function call and capture how long it takes to execute. Yeah, this doesn't exist yet, but I'm working on a prototype for something which I might release at some point because I think it could be an interesting addition. It's probably not going to be for production usage, but some people might be interested regardless. A little bit more details on the runtime tracer because it's so useful. It basically captures scheduler events, GC events, contention events, syscalls, etc. So it actually also has some overlap with what the clock profiler does, for example, when it comes to contentions. And if you want to have a full list of everything that this thing can capture, go to source runtime trace.go. This is also my favorite file in the whole Go source tree, because it can show you a list of the most important things that the Go runtime is doing, and you can jump from there to the locations where those things are happening. So it's a really good index to Go internals. One thing to note about the runtime tracer is that it's a very high overhead way of instrumenting your Go applications, because it produces a lot of data and you can't filter what data you want. So be a little careful in production with this, or actually be a lot careful with this. We'll look at this in more detail in a moment. But again, it's a fantastic way to track down latency when nothing else seems to have the answer. So you should have this tool in your pocket when you need it. Also worth noting, of course, is that it comes with a really nice UI that can show you your timelines from a thread perspective, i.e. how did Go routines get scheduled on operating system threads, but it can also show you the same view how Go routines are executing by themselves. So you get a timeline for each Go routine. You can click through various ways in the UI to get to the different views. Next up, let's talk a little bit about something that I don't hear discussed very often, which is profiling and tracing, a Faustian bargain. Essentially, profiling and tracing can gain you a great amount of performance knowledge, but just like in Goethe's Faust, our Mephisto gopher is a little coy about the price. The Go documentation for profiling generally states that most profilers are okay for production usage, but doesn't go into any quantification of this. So today, for the first time, at least to my knowledge, I'll try to share some research on what the overhead is for the various Go profilers. The way that this was set up is to essentially run different workloads in a loop for 1 minute with and without various profilers enabled, to then measure the average latency for that workload. I've repeated each of those experiments for 5 times and performed all of this on an AWS instance. The total duration for this benchmark was around 6 hours. Very important, this is very hard stuff. It's very difficult to get this right. This is just an early sneak peek of this research. The environment used is bad, the statistics are not great, the workloads are pretty naive. So do not trust this too much, but I thought it was still interesting enough already to share a little bit of what I found so far. So here's one workload that I started with is basically simulating a typical web application workload of running a SQL query in response to an HTTP request, perhaps. So here we see a SQL query being executed against a PostgreSQL instance. And this SQL query basically just asks the database to sleep for 10 milliseconds, because we don't actually want to put load on the database because it was running on the same host. But even if it wasn't, we don't want the database performance to be more prominent on our results than the actual performance of our Go program. So this is a reasonable compromise for now. So what I found doing this was that essentially you see very little overhead for any of the profilers, even including the tracer, when you run this in production. So just going through this table a little bit, you basically have the first column is the profiler, and the second column is concurrency. So I've ran each of these profilers with a concurrency of 1 or 8 Go routines executing the same workload. And then I basically measured the change in average latency for this workload. So yeah, as you can see, not much overhead here, especially for the normal profilers. Only when you enable the tracer or the tracer plus all the profilers do you see a tiny little bit of overhead, but I wouldn't read too much into this. Then the next workload I looked at is an HTTP Hello World workload, which basically is the most important benchmark in the world, according to some people, of just figuring out how fast can you serve HTTP requests that essentially do nothing. I would say this is quite an artificial workload, but it's the most fun one people tend to go for. So here's some results for that. Good news again, CPU, MEM, and mutex profiler, no overhead. A little bit of significant overhead for the block profiler, but again, I was using a block profile rate of 10,000. This might go down a little bit if we choose an even higher rate, I don't think this is very representative of a production workload, so I wouldn't say that this should worry you about the block profiler. What we then also see is that the tracer, as well as the tracer plus all profilers, starts to show a lot more overhead, especially with a concurrency of 1. For some reason, the overhead is less when it's a concurrency of 8, which is interesting. We'll look at this a little bit in a second. Which we'll do by looking at the next workload, which is a JSON parsing workload. So this is basically parsing a small JSON document and then actually marshalling it back into a byte slice, which again is a very artificial workload, but it's a fun one to look at. So here's the results for that. And those are a little interesting to say the least. First of all, we don't actually get any overhead in the sense that our program runs slower. Our program only runs faster if we throw profilers at it. So in particular, the CPU profiler makes this workload 13% faster, and the tracer can make it up to 40% faster. Obviously, this is very worrisome for the quality of this research, so I decided to take a closer look of what's going on here. In particular, I was looking at the 3 different configurations of either having no profilers enabled, as you can see here, or having the CPU profiler enabled, or having the tracer enabled. So let's look at this data for a second. What we can see here is basically the x-axis is the time of the benchmark running. Each little square is one execution of this benchmark, and then the y-axis is the latency of one particular iteration of that workload. And what we notice here is that our benchmark is getting faster over time. So the longer we run this workload, the faster our program is executing. That obviously is a problem because clearly something is either warming up here or interfering with our workload in a way that basically makes these results hard to compare to begin with. Because the samples we are collecting here are not statistically independent from each other anymore. So that's always a little troublesome. But it's even worse. When we look at the next one, which is the CPU profiler, what we can see is the same kind of pattern in general, but we start to see this little band of outliers down here, where towards the end of our program's execution, we get some very, very fast iterations, which is, yeah, again, a little new phenomenon that we haven't seen yet with no profiling. And then when we see the tracer, where we saw up to 40% gains of performance improvement, the pattern becomes even more stark, where we see 2 bands where request latencies or workload iteration latencies are starting to cluster here, one sort of in the middle and one at the very bottom. And what I think is happening here is that basically we're seeing some amount of turbo boosting or otherwise frequency scaling that the CPU is doing on this machine, which is causing some of our requests to accelerate. What's not quite clear to me if this is really turbo boost is then why does our workload with no profiling not show the same pattern? Because we're already putting 8 Go routines on heavy CPU duty work here. So you would expect turbo boost or whatever additional performance the CPU can squeeze out to kick in. I'm not really entirely sure yet what's going on there. So definitely more research is needed. The one thing you should definitely take away from this slide is don't trust anybody's benchmarks and data unless they show you pictures like this, because only when you look at the patterns in the data can you tell anything about the quality of the research, which is still very hard to do, but this really makes it easier to see if you're looking at bad data or not. I don't think this invalidates everything I'm talking about here, but it should show you that you have to apply great caution and not jump to too strong conclusions from this. Another workload here to validate our methodology perhaps is to look at channels. So here we have a message passing situation where we send 10,000 messages from Go routine A to Go routine B, and that's our workload. And for this workload, we actually get to show the block profiler and the tracer to give us huge amounts of overhead. And the reason for that is pretty clear. We're basically doing a lot of channel contention events that are causing the block profiler to kick in. And the tracer is just going nuts because there's a ton of Go routine scheduling and contention events that the tracer all has to admit. So that's just a lot of work for both the block profiler and the tracer. And this is probably the most pathological kind of workload that I can think of. This shouldn't tell you that all hope is lost for using these tools, but it should tell you if your workload is very pathological in the way that what I've just shown you, you should be much more careful with these tools than maybe for a normal application like the SQL queries that I've first shown. So a little bit more error analysis of all the things that could have gone wrong here or definitely did go wrong. Yeah, dynamic frequency scaling is definitely one candidate that I'll investigate more. Noisy neighbors is another. This is a cloud environment, which is not the best place to do this research. There's human error. So I could have just done some bad things during the setup and execution of all of this, which I will have to continue double checking. But hopefully by the time you watch this, either new results have already come out or new results will be on the way. So the quality of this will go up over time, and I'll probably publish it somewhere online. But what I'm willing to say already is that I think for the CPU, memory, mutex, and for the most part, block profile, I think unless you have a very crazy workload that is really skewed to make those profilers look bad, I think these are pretty safe profilers for production, and you can turn them on most applications in a way that you probably can't measure the overhead on your programs by just looking at request latencies. Some programs will be different. The utilization of your CPU cores and stuff will also play a role thanks to Little's law, but I still think that most of these profilers are pretty good. The tracer you should definitely be careful with. Now let's talk about metrics. We'll only do this briefly, but I want to highlight a few things. First of all, Go 1.16 and later has a new package called runtime.metrics, which is a new place to get all your runtime metrics from. And I, in particular, want to highlight some of my favorites here, which is the GC pauses and schedule latencies. Both of these are histograms, which is something you couldn't get before Go 1.16. The first one shows you the stop the world pause latency histogram for the garbage collector, which in recent versions of Go generally shouldn't be a problem anymore, but hey, you can check it anyway. Maybe you find some new issues with it. And then the second one is the schedule latency, which basically tells you how much time your Go routines are spending in a runnable state, which is allowing you to look at one of those profiling blind spots that is difficult to get at. The last one I've highlighted here is one that is near and dear to my heart because it can tell you something about profiler overhead, which is the profiling buckets bytes. And that basically tells you how much memory the profiler for the block, mutex, and memory profile is allocating off the heap. So this does not show up in your heap usage in order to keep those profile statistics for those profiles around. Generally speaking, this is very small, usually a couple megabytes, but there are some pathological applications that will have maybe 100 megabytes in here. So this is a fun one to keep an eye on as well. My recommendation is to generally try to find a way to capture all the metrics that come out of the runtime metrics package because they're really great and useful. Now let's talk about third-party tools to round out the picture of things you can use to observe Go applications. There's Linux Perf, which can capture CPU profiles. This works very well thanks to frame pointers and dwarf information emitted by the Go compiler. Currently, this can definitely be a little superior to Go CPU profiler up until Go 1.18 due to the limitations I've mentioned earlier. And of course, Linux Perf can also do much more and produce all kinds of other interesting profiles and traces. So if you want to go really deep on something, it's definitely worth checking out in addition to the built-in profilers. BPF trace is one of the cool new tools in the eBPF universe. One of my favorite ways you can use it is to do dynamic tracing of any Go function at runtime. So this little program shown here says put a uprobe on my program called example, that's the name of the binary, on the function main.foo. Please note that this is a private function, which would otherwise might be more difficult to observe or hack into. And then when this function gets called, the BPF program here prints out main.foo was called. Yeah, BPF trace, if you're familiar with dtrace, it's basically the same thing. They're both inspired by Arc, and they're really powerful tools to build custom little scripts to observe applications with relatively low overhead. So you can often use this stuff in production. But a big warning here is if you ever see the keyword uretprobe mentioned in one of those scripts, do not let it go near your Go programs, because this will generally crash Go programs due to the way that read probes are implemented and the fact that the Go routine is using dynamic stack resizing of Go routines. So they'll be very careful here. Delph is also worth mentioning. It's a debugger for Go. One cool thing is you can script it using a scripting language called Starlark. Most people probably haven't played with that, but I've done it and I think it's very cool. And they're also working on eBPF integration. There's already some experimental tracing functionality available today, which is why I'm mentioning it in the context of Go observability, because I think there's potentially ways that Delph will become an observability tool that you might be able to use in production in the future. Today, it's probably still mostly debuggers that you should prefer for development environments. And last but not least, a little project of mine called FGProf, which is a wall clock profiler that is implemented by collecting Go routine profiles 100 times per second. And it's really that simple. It's also only like 100 lines of code. And that can also show you various things that the Go profilers cannot show you because it gets to look at all the Go routines regardless of what state they're currently in. The only problem with FGProf, or the main problem, is that it causes these stop the world pauses because it's built on the Go routine profile. So you should not use it in production. But perhaps it's useful for development and test environments, especially if you want to spot uninstrumented I/O latencies or time.sleep, etc. And who knows, maybe in the future, upstream will be interested in proposals for allowing Go routine profiles to be taken in a sampling fashion, which would put an upper bound on the stop the world pauses. So tools like FGProf could become production tools as well. All right, that basically brings us to the end, but we have time for a quick recap. The recap is on the scheduling and execution side of observability. You've got the profilers, especially the CPU, block, mutex, and Go routine profiler. You've got tracing, especially runtime execution, tracing, and distributed tracing. Then you've got metrics, such as scheduler latency and Go routine count. And one thing we didn't talk about, because it's, well, not clear if people would call it observability, but you can get information at compile time, for example, about function inlining by passing the -m flag to the GC flags option of the Go build tool. Similar for memory management, you've got the memory profiler. Tracing can be used to get information about GC events. You've got various metrics such as GC counters, pause times, heap statistics, even stack statistics. Many people don't look at the total size of their Go routine stacks, which can also add up if you have a lot of Go routines. And again, there's a little bit of compile time information you can get on the escape analysis performed by the compiler, again, available via the -m flag. So the summary of all of this is that essentially the Go runtime offers great observability out of the box. And most of these tools play really nice with production workloads, in my opinion, even though that research will continue. And there's also a lot of great third-party tools and custom instrumentations that you can use to close any gaps. This is the end, but not quite the end. I will continue writing stuff online. I've got this thing called Busy Developer's Guide to Go Profiling, Tracing, and Observability that you might find interesting. I'll continue with the benchmarking. I'm looking forward to releasing more standalone tools, such as the tracing profiler. And I'm also always interested in contributing patches upstream. Currently got one in the works, but I'm always looking to find more stuff to help out with. So this is the end finally. And thank you so much for listening to me. Thank you so much for the organizers, and enjoy the rest of GopherCon 2021. Goodbye.
Hi, everyone. Welcome to GopherCon 2021. My name is David Justice, and on behalf of Microsoft, I would like to welcome all the Gophers out there to this great conference. This is a conference that's near and dear to my heart, and one that I've been attending since 2015. And thankfully, at Microsoft, I'm grateful to be able to build this thing. If you don't know what this is a Cluster API. It's a Kubernetes SIG cluster lifecycle project that is for declaring infrastructure in Kubernetes, and then it builds it out for you. It's all written in Go, just as much of Kubernetes is, and I'm really proud to work on it. I'm also super proud of what this conference has meant to my family. My wife Dea loves to make gopher art for my whiteboards, and my son has enjoyed coming to the conference as well. It's a really amazing community, and I am so glad to be part of it with you. I hope you enjoy this conference, and on behalf of Microsoft, I want to say thank you, and I look forward to meeting all of you, even if it's virtually. So thank you so much. I can't wait to see you.
Alrighty, we are back, the trusty MCs. So yeah, I just want to thank you, Felix, so much for that content. And David, also, it's awesome to see what you're working on, awesome to see what you're doing in the community too.
That artwork was
Artwork,
pretty
yeah.
sick.
Indeed, yeah, we love that artwork, so thank Dea for us as well. So a little housekeeping note, this was mentioned in the Peanut Gallery as well, so just a reminder for everybody, the speakers each have their own channel in Discord. So they're going to be in there, most of them are going to be in there at least right after their talk to answer questions, have discussions on the content, really what have you. So do feel free to go take advantage of that and have those discussions with them.
Yeah, and some of them, if it's one of the recorded talks, the couple that we have, they may actually be in there to answer questions during the talk. So definitely check those out when that's happening.
Yeah. Yeah, and then one other thing, I was told by folks smarter than me that the pronunciation of Felix's last name is Geisendörfer. Felix, if you're watching, hit me in Discord, give me a grade, a letter grade, how I did there. I would love to.
F.
F.
Or an L.
What about a G for German? Can I get one of those maybe? Anyway. Again, thank you so much, Felix, for that content. That was like really super interesting to hear about this topic from someone who's been in the trenches and doing that stuff. So yeah, I hear we have a plaque. Is that right?
We do not have a plaque,
Oh, okay.
and that's
This is aspirational.
it's kind of the problem.
That's the
All right.
problem, okay.
So been hanging out here in the studio, and Microsoft has one of these 100K plaques for Microsoft Developer, and I'm a little jealous. I think GopherCon needs one.
Yeah, I saw you eyeing that earlier.
Yeah. So for Christmas, I want one of these, and I'm just going to need like 75,000 of you.
Of your closest?
To go subscribe.
Of your closest bots.
Yeah, and we're not going to encourage you to build a bot, but if you were,
We're not saying to build
I hear
a bot.
Go can do this very efficiently.
Yeah, I mean, we've got Go routines. We're not saying to use them to build a bot.
But if you were going to, there's no better tech.
Yeah, exactly. Yeah.
we're not going to encourage you, but we may turn a blind eye if there happened to be a bot.
Yeah, and if you're watching this on the YouTube stream and it goes black,
You know what happened.
hop on over to the Learn TV channel. But seriously, that support would be great if we get that plaque one day. Well, if you get that plaque one day, that'll be. We'll really have a disco ball in the studio to celebrate.
Oh yeah,
that.
this thing reflects some light.
Yeah. Right.
So all right, yeah. So who do we have up next, Johnny?
So whenever I think of banks and banking systems, the first thing that comes to mind is mainframes. Like hospitals, banks, I'm like mainframes. Like what comes to mind for you when I say bank? What do you think?
Yeah.
Money? Just money?
After money, though.
After money.
Yeah.
Well, I mean, money depending on who you are, right?
Right. Yeah, exactly.
Enterprise Java beans.
Oh man!
Throw it
No! Flashbacks. No, but seriously though, there is some innovation going on in that space. Especially with Go, right? Novel uses of Go on the mainframe, and who better to talk to us today about that than Kaylyn Gibilterra. Sorry, I butchered your name, and she's a tech lead at Capital One, where so that's a bank for those who don't know, and surprise, they have mainframes. Who'd have thunk it? So
Do they have Go?
but well, thanks to Kaylyn, they do, and she's definitely going to talk to us about basically what she's been doing with that stuff on those mainframes. Take it away, Kaylyn.
Awesome, yeah, thank you so much. So I'm excited to be here. I've been around Go since about 2015 and always was really excited about there's so much potential here. This is such a great language. I am a little biased. I came from a C++ background, so eventually I learned Go was written for people like me, but it really resonated. And I've been at Capital One for almost 9 years. And the very first project that I joined was a mainframe project where I was mostly doing those Java Bean applications that Aaron was bringing up, but we were even connecting those to COBOL, and that was the first asset I came in on. And since then, have seen the company try different strategies for how do you work with mainframes, how can we modernize them, and want to share both how that works and like understanding how a large legacy type system operates, and then covering how you can use Go and the language, both from the technical standpoints and also the principles that are guiding it to build at that scale at your company. So this is a bit of an outline. To give a warning, if you thought, you came to this Go conference and we were just going to talk about Go code, unfortunately, I'm going to be asking all of you to like really dig into like what is a mainframe, what are legacy systems, and like how do you hopefully learn some of these strategies? Because if you have not worked with modernizing legacy systems very often, a lot of the obvious answers that you will try fail, and I want to share that experience to hopefully help you. And then for those that after you've kind of tried and you've potentially failed, what's going to work and how do you use it to build large teams that are going to tackle this problem, ideally in Go. All right, so to kick it off, I'm going to assume not everybody really knows exactly what a mainframe is. If you do, if you've worked in mainframes, especially if you've written COBOL, I absolutely want to talk to you, so please reach out in Discord. I'd love to share some experiences. But mainframes were created 77 years ago. So that's when the first one launched, the Harvard Mark I. It was created by this guy, Howard. This is the original kind of squad that led the launch of this massive mainframe. And I've added here a picture that almost encapsulates the entire size of the mainframe. It's in fact 55 feet wide, so like much larger than my New York apartment, probably two of them side by side. But what this mainframe was for is you can see at the very first section, this has a 30 down by 24 across set of switches. And there's actually two of them, so you've got 60. But those are all going to be used for tracking the values inside your mainframe. And what you can do is you can do up to 72 numbers. They can be 23 digits long, and you can do a bunch of math. So I've included some of the metrics, how fast you can do these math equations. And at the time, this was just absolutely mind-blowing. The Howard, the guy who created this, was all over saying, this is it, we've solved this problem. There's going to be 24 entire mainframes used in the entire world, 24 or 27, something like that. He's like, that's it. We're going to do all of our math problems and solve the world's problems. The second picture I want to show that I really like is this is a picture of the punch codes that they would put in to this mainframe system. And there were two things when I was like pulling up just some images around mainframes that stood out for this picture. So the first was I could really picture us at like conference talks today if we did not write with human words and instead wrote in punch codes. I can totally picture the like slides and wave analysis of writing our code, and I think that would actually be a really fun exercise to do at some point in time. But second, something that's very not necessarily well known is there's the story of Greisemer and the mainframe team finding a bug in their system. And it was one of those, like they couldn't figure out why it wasn't running. And eventually they actually physically looked in that 55-foot mainframe and found a moth sitting inside. So from then on, whenever they had issues with their code, even if it was in fact their punch code, they would say, it's a bug, it's like, it's not me. With these pieces of paper that were punched, eventually, you're doing your calculations and you're running through all of them. And it doesn't take you long to say, like, I want to run this again. I want to run this with different values, but I want it to be the same set of instructions. And so what they ended up doing was they taped the paper back to itself, creating a loop that would run. And that's literally why we call it for loops today. That's why you reference, oh, you're going to run this code again in this loop interface. And it's because we taped this paper back on itself. And so I just found that kind of fun and interesting to see how that terminology is absolutely what we still use today. But the mainframes of right now are definitely not that like 55-foot monstrosity. So first of all, like 70%, I don't think everybody realizes, just 70% of Fortune 500 companies are using mainframes. 90% of credit card transactions. I don't think this data is too old, a few years old, just incredible volume of business transactions go through mainframes. On the right, I've got this picture of like an IBM modern mainframe. They've got their like nice, looks more modern, it has the blue stripes. What's interesting and important to kind of know about these mainframe systems is there's 40 terabytes of memory on here. So what's compelling about mainframes is when you're building something in like the cloud, if you're using, I glanced at AWS sizes, and in memory, the largest I saw was about half a terabyte. So when you're comparing half a terabyte of data to 40, you could have a very, very different conversation about how you're going to save your data and how you're going to make sure you have a consistent read. And if you can just dump like that, 40 terabytes is much larger than the entire volume of transactions that we are generally monitoring. You can just put it all in memory, and that's going to obviously make it so quick, so fast. So there's that speed that comes with mainframes that's really, really hard to beat. And then the final bullet that I just brought up, because it's actually a really fantastic read, is that they have a fun fact where it definitely can survive at least an 8.0 earthquake on the Richter scale. And the reason they know that is because they absolutely created a like very serious test where they went rigorously through and like tested out these earthquakes with these mainframes. So you know it'll sit around forever. So this is a modern mainframe. Most companies are using something in between. Now I pulled on this slide. We know banking, banking and governments tends to be where people think of mainframes. That's where they tend to bring it up. It's definitely everywhere in that in these domains. But I added in a bunch of other ones, kind of just like threw in some names. I scanned like that link at the bottom. You can just pull it up, and there's a huge list of companies that IBM is tracking that use mainframes, and it's across all these industries. So there's also healthcare and insurance. There's probably some surprise around like most airlines are still using mainframes and are actually pretty passionate about, I think in the mainframe world, they like really know what they're doing and have strong opinions, but you can see it all over the place. Even I added the New York Times news more quickly than other industries, but it's just everywhere. So this is to help essentially explain how mainframes are used today, where they came from, and all of that information. Now, 9 years ago, that's when I was introduced to mainframe development, and I joined a team where we were tasked with, we've got multiple mainframes, and we want to merge 2 of them. That's a common strategy if you're working with legacy systems and you've got your data inside of them. You don't want to have tons and tons of different backends because things will get confusing. You've got to maintain all of them. So a natural request is to take all of these things and merge them. So how this kind of looks and how this came about, because I don't think many people would think this all through, is if you started a company in the 70s and 80s, you used a mainframe. Every single, it was the only option. You had a mainframe. And you had all these smaller companies, whether they were banks, insurance, whatever, all backed by one mainframe. And then over time, you'll see companies merge. And so then they're left with this conglomerate of a bunch of different backends. And they are like, well, I don't want all these backends. So the natural reaction is to say, let's just start merging them. And that makes a lot of sense in theory. I heard the project idea. I was like, yeah, sure, that sounds right. That's what we should do. I want to break from this idea of this assumption that you're just going to merge these mainframes easily and talk a little bit more about what actually is a mainframe. So I just added this GIF for 2 reasons. One, the guy is kind of fun. But 2, if you look, so this whole stereotype of hacking that you see in TV of the black screen with the green text comes from mainframes. But also the picture here, if you can see it, is not the most unrealistic. It's not actually showing you a mainframe, but it does really show a similar UI. Because this one, I just looked around at random pictures of mainframes, and this one I found, and this is something I worked with. So you pull up a system, and you're going to see this menu. It's going to have different options, but you're going to see this okay, select 0, 1, 2, 3, et cetera, et cetera. This makes a lot of sense. You're like, no problem. It's a terminal interface. Not a big deal. I kind of looked around, and the second picture just kind of gives an example of when you're going through, it's not so much a clean flow of steps you're going to run through. It's actually pretty complex. You need to remember all of the characters you put through, because eventually you're going to get to this journal entry was what they've described it. I've seen that before. And you're going to want to update it. Maybe you want to change the balance. This isn't a testing environment, but you're going to want to update, you're going to want to refresh, you're going to want to run a batch, something like that. And I remember when I joined this team early on, it was a bunch of very seasoned mainframe engineers and me, right out of college, and they were like, we don't know, really nice to meet you, but have some fun with COBOL. And I was primarily on the Java app, but we would run this batch. So every day you got to get the data over to the mainframe and back, even for testing. And eventually I kind of worked my way through so that I could run that by myself. And I figured all of that out. Really proud. They were totally praising me. It was like, this is wonderful. You know, we didn't expect this of you. They had much lower expectations of somebody coming in cold. And after a couple of weeks of this, maybe a month or two, I can still remember, you know those memories that are burned, like you know exactly where you were when this happened? This is one of those memories where one of the mainframe engineers walks up, real cheery, such a nice guy, and he's like, I think today you should write some COBOL. And like, it was like I froze. Like that whole meme of the woman with the math equations above her head, I'm sitting there like, wait, and I'm trying to work my way backwards from like a real mistake that I made. And I quickly get there. But in that moment, was like, what do you mean I should write COBOL? I was like, what have I been doing? And now I don't say anything out loud, but I was able to trace like, oh, I'm just using a UI. That's very obvious. But the complexity of when you are working through trying to figure out what you want to update just through this UI actually feels so similar to programming that I didn't even realize. Like I wasn't actually doing anything. I was just using the system. So I play it cool. I pretend like I did not think I was already writing COBOL, and this is just a random sample. They actually show me how to access the COBOL code for this mainframe system. And I kind of look through it. I'm like, actually, okay, like this seems all right. It's a little bit dark. I don't know what you can see or not see. But you can see it's similar looking to assembly, but you can see there's variables. So you can kind of reason about it. You're like, okay. And the task that they gave me was we need to update this field value from this type to another type. Sure, no big deal, because we're doing a data migration. So it was this, we need to update to another. So I should have known something was up because the other mainframe engineers were all like peeking their heads over like, oh, this is interesting. We're going to have her actually go do something. And they kind of give me that task and I work through it and I'm reading and you know, I really underestimated how long in a terminal you can be scrolling because there's not much of like a UI to tell you how long the files are. But eventually I'm like, okay, I see where this field structure is and I kind of see how you update it. So I would go update it here. And it was at that point that I realized it was like a total joke to give that task to me because they were then like, yeah, no, you can't do that. You can't do that. You definitely cannot. Because if you update it here, you're only updating this parent value. And in fact, there's all these other values of these like children representations of that field that you need to make sure are correct. And if you miss any of them, your data migration is going to fail. So they were actually attempting to teach me why their job was hard and why they were frustrated. And it mostly worked. And then I was like, well, now I know what COBOL is, apparently, after a while. But what I want to bring up, the last point I want about mainframe merges, is it's not that they are impossible. It's not that you can't do it. But it's very, very, you need to be very serious about how you're going to take this activity when you go into it. This is a fantastic, it's not a long read, something by an airline mainframe company that's an expert. And it really digs into like, okay, this is what you're gonna run into if you're trying to merge data. And so their comment here, the migrating the required data out is not even remotely similar to migrating data out of any other database system. They do a really good job of being to the point. And that's what engineers who have not experienced mainframe systems will chronically underestimate. So a couple points here that I'll bring up briefly, but just kind of useful if you ever run into this. And if you're ever thinking about not even mainframes, legacy system merges, you need to very much understand the database structure. And so mainframes, they do not have references. There's no like primary keys. There's nothing like that tracking data. If you have a parent-child relationship and you change the parent field, the child's not updated. If you change the child, parent's not updated. The other children are not updated. It's just all a reference. And then there's something called COBOL copybooks that if you do not have access to that copybook when you're trying to run and compile and run evaluations of the data, you're going to migrate and it's not going to be correct. It's not going to have the right representations. And this is all, I just remember these mainframe engineers like saying these words over and over. So if you want to check it out, this blog post is just fantastic. But this really articulates how difficult it can be to migrate mainframes together. So I have this experience. I'm now actually a COBOL programmer in some form. And what do you do? Oh, sorry, this got a little messed up. But what do you do when you see something like this? You see this merging, you see it's not going anywhere fast. I was trying to learn COBOL, I was trying to learn mums, and then I was like, I need to get out of this. This is like not the life for me. So naturally, any person in this role moves into somewhere where maybe you could try something new. So I immediately run into the Capital One labs, and they are just absolutely wonderful, really like tolerated my intensity, and was like, we gotta restart. We gotta build another mainframe. This is insane. You wouldn't believe the horrors that I have witnessed. I've since learned it wasn't as bad as I thought, but coming in junior, I was like, this is insane. And so I go to this lab group, and it's like, we gotta fix this. And somehow, there's a group of us in engineering that are like, let's we can do this. Let's go build a new mainframe, which was bold, which was just incredible. So we actually go through and we're like, we're gonna try to reason about how hard can it be. We're gonna try to do accounting for your like credit cards and your bank card. That's not that bad. Two things were important. So first, I love this XKCD. It has just like really stuck with me and like helps me when I'm trying something new and being like, I'm gonna be the one that's gonna fix this problem. This XKCD helps me a lot. So two things happened when we did it. One, were we really solving the problem of like narrowing down the scope of back-end systems in banking? Or were we contributing to just one more system? But two, we had two pretty big assumptions that we were wrong about. One, the business logic is reasonably complex. We built like a small team of just engineers. We didn't even have a business person. We were like, we'll figure it out, no big deal. It's a little bit of a bigger deal than we assumed. And then second, there's a lot of different problems around like you need to understand all of this data really, really well. And eventually, I was just talking with a coworker that I worked with about this, and he reminded me we found a like 20 to 30 page like master document from somebody that had been working in mainframes for a long time, and it was essentially just like a 20-page warning label of like, are you really sure you want to do this? Because everybody's tried and everybody brings this up. And this post is one of like, it's just incredible. Around how they've tracked just from last year, 74% of organizations fail to complete their legacy system modernization efforts. Do they need to all fail? Absolutely not. This post, I did include a piece of it, just like really roasts like leadership teams, like executives, which I found fun. I don't think that's the only reason though. I think there's chronically underestimating how challenging it is to ensure that you fully understand a legacy system before you try to replace it, and just not understanding all of the resiliency that was built up over time. So often when you're in a situation like this, if you don't want to fail, there's a couple of things that you really want to pay attention to. So these were my biggest learnings. These were my biggest takeaways, both from attempting to merge mainframes and attempting to build another. The first piece is they are really fast. So if you want to build something that's even going to keep up with mainframes, you do in fact need to be really thoughtful both about how you're going to scale your code and how you're going to scale your architecture, because they are fast and they don't generally fail. We've been seeing some more issues across the industry, but for the most part, they're very, very stable. They're always going to give you your answer, and you're just going to keep running with them. The second is this like relational way of recreating data structures. Both second and third is this really big surprise kind of to me around how, yes, the business logic is kind of interesting, whether it's banking and you're making accounting, or maybe it's airlines, whatever it might be. That part is interesting, and that tends to be where you're like, oh, I want to understand how this works. In reality, you need to invest a ton of time into making sure that what you're pulling from another system or what you're creating is actually going to be right all of the time. And then the fourth has been a longer learning. I didn't quite figure this out until later, recently really, is that I can talk a lot about code quality, and as an industry, we tend to be like, oh, this is where we got to, idiomatic go. Some of my favorite conversations that I overheard was them talking about idiomatic COBOL, and I was like, what? And that's like absolutely a conversation they would have, like where you have hard-coded variables, absolutely. And that is important. But in reality, if you are building your system in such a way where you are just unlikely to make bugs, you are unlikely to introduce something that's going to reduce resiliency, that's something that's going to last for a very, very long time. Not to say that the biggest challenge with these legacy systems is adding more features. But if you think about the fact that I worked on programs running on the mainframe that, no joke, were actually written in 1971. And like that code was still there, and you didn't touch it, because if you did, like everything, it's like it's there. But when you think about, I want to write code that's around for a long time, and 20 years, that'd be a delight to know that my code is something a person's like cursing out, because that means it worked. That means that it provided a lot of value and was hard to get to that same scale. So that's kind of where I got after like 3-4 years, I don't know. Now the next phase, quote unquote, that I've got here, this is a common strategy when at a corporate level, and also for people dealing with legacy systems, is you've done this enough, and I was like, this is a nightmare. I don't like this job. So I stopped. I'm like, no. So I'm like, I don't want to deal with this anymore. I'm going to go work on all these other projects. And so I started moving around. I'm back in labs doing like newer ideas. I do some security work. I do web layers of like middleware, stuff like that. Anything. I don't want to deal with this. I don't want to do mainframes. That is until 3 years ago, somebody approaches me. Now, the organization that had been attempting to merge those mainframes back when I started, I left. I was like, well, I can't help you guys. This is way out of my depth. They kept going, obviously. And they were observing the challenges that they were seeing. And so they started to say, well, what can we do? What else can we do? Do we have to merge mainframe 1 and 2? Do we have to get the data together? They have actually almost entirely completed the merge, but they realized correctly in that process how hard it is. It's not something you can easily underestimate. Or actually, you can very easily underestimate it, but you shouldn't. So they start looking at this oversimplified pattern that I've got here around, well, what if we create a communication layer? And instead of trying to change the mainframes, or instead of even trying to replace them, what we're going to do is we're going to start building pathways to talk across all these different mainframes. And we're going to make translations between them completely transparent. So if you have any systems that need to call an account that exists on one mainframe or an account that exists on another mainframe, they don't care. They're just like, you figure that out. That's for the communication layer. I just need you to get me the account information from whatever mainframe it's in. And this design was brought up to me, and it was one of those, I was like, well, I'm trying to stay away from this. I'm like not sure. There was like the split of like, do I want to? I want to, but where do I fall? And in my head, I was like, well, that sounds not bad. That sounds like it could help. It sounds like it could kind of work. And then the person at the time said, well, I know you really like Go. So if you do this, we'll build all the systems in Go. And frankly, the idea could have been bad, and I probably would have been like, that sounds great. So just to give some context before I move into the Go section here, is I went through, partially based on this mainframe experience, I first was introduced to Go while evaluating what language do we want to write this bank in a box that we were creating back in the day. And I had such a delightful experience creating my first APIs in Go that I just anybody that knew me from 2015 to 2017, 2018, I was always ready. Do you want to talk about what the best language is? Do you want to have a conversation about this language versus that language? Absolutely. I was all the time very, very into it. So essentially, up until the pandemic, I used to travel around, and in fact, I actually brought physically with me this really embarrassing laptop that I've got, where I thought that because they were white, I could add all these gophers and it would be very subtle. And about halfway through, I was like, this is not subtle. This is not as subtle as I thought. And it did help me realize that I needed to calm down a little bit on the language. But for years, this laptop just died. I would walk around and everybody would be like, you seem to really like the language. And it was true. But that's where I was like, okay, if you're gonna let me write in Go, I have been writing some systems in Go at Capital One, but they were internal tooling or they were proof of concepts that weren't going anywhere. There were some teams, very small, but there were a couple systems that had gone to production in Go, and I was dying to get that opportunity. So I say yes, absolutely. That's fantastic. And I have this whole vision of how we're going to go about this. Like, oh, I've been doing this mainframe stuff. I've seen all these ways that you think it's going to be easy and it's not. So we're going to do this right. We're going to have all these trainings. We're going to really talk about design. We're going to talk about our data. We're going to like have all this like great conversation about what we're trying to do, how we're going to do it. All the engineers are going to have like everything they need to like feel really good about their code. And that definitely did not happen. Like, not very little of that happened in reality. And I felt a lot of stress for a long period of time, a lot of kind of guilt. Like, I did a couple trainings and then it was like, what? I feel like I should be doing more. So the surprise for me is, actually, I'm just gonna step, I'll keep going. So the surprise for me is I've got a couple skills in here that I learned based on this experience that are not what I would have expected to do, where I would have thought like we've got to write really strong code immediately, or we are going to have all sorts of bugs, we're going to have all sorts of like concerns when we're launching, we're just going to become mainframe 2.0. And in reality, what I saw was after about a year we launched, and I had to have a moment of reflection that was essentially like, everything's fine. Like, it worked. Like, we found some issues in non-prod. The code was fine, Go code. It was not like, I wasn't gonna, advertise it, but it was totally fine, and the system was scaling. The system was working. In fact, it was working pretty well. So a lot of this talk is around, I'm gonna just show you a little bit more of what I'm gonna cover. What I would have found the most helpful, some what kind of did when I was starting, but what would have been the most valuable to seed across teams, especially if you are working in some sort of like legacy type environment where you're building something new, but you need it to work across specs that you may or may not fully understand. And with an assumption that you probably don't have a full squad of Go teams that are just like ready to go, a bunch of experience, because we aren't a high enough volume of engineers, so you're most likely going to have people coming from different backgrounds. So these 4 steps should hopefully help if you're in this situation or you want to be in this situation like me, where I was begging for that Go project to work on. This should help you see what you want to invest your time in, whether you're like a lead IC like I am, or you're a director, or you're a senior, like a principal engineer. These are the things that I at least noticed that have been the most helpful, or where people just would get the most confused. So the first step is actually evaluating what the backgrounds are of everybody across your team. So this is not an exact, I didn't really go through and like count every person, but this is very close to accurate of the number of people with prior professional Go experience compared to those that didn't. Now they had professional experience in other languages, but the volume was so low. So that's where like I joined at the very beginning, and that's where I just assumed like, if it's me, and there's nobody else, I was like, that's not a good sign. I don't feel great about this. And I was like, well, then we're kind of in trouble. We're gonna need to like really fix up a lot of our code. And we've added some more people with Go experience. We're actually getting more now, which is fantastic, and definitely going to help with writing better code and like the nicer idiomatic Go code. But we have just had very few incidents, outages, bugs that probably would surprise you, and I'll walk through some of the areas to avoid, but just actually really speak to Go being such a strong language for learning, for teams that are learning, where if you are hiring people who have prior engineering experience, even like just out of college, or even if they're newer, you're gonna see that they look at it and say, I see what I can do with this, and that's what we found. So I have a couple notes on here. It's a little bit about like different languages, and so people might disagree. But this is what I saw trip up engineers the most when they came in from different backgrounds. So if they came in from Java, we have a lot of Java engineers, but also C# a bit, where they immediately start going is they look at your system and your problem statement, and they start building a bunch of interfaces. They're like, okay, so you want to connect to a database, so you're going to need like this whole section of interfaces, then you're going to have your getters, and then you're going to have like updating your data, okay. And then they start building a bunch of packages, and they start having a bunch of files that are in all these different packages. And that's where they start going. They're making like their little web. And it's similar to Java, but you'll see that it kind of spreads out, and then all of a sudden you're like, so where is that code? And that's where they focus. And now in Python and JavaScript, where I've seen, it took me a bit to realize that's what was kind of happening. They would they would say, oh, I like this speed. This is cool. That's nice. It is faster than what I was using before. But they would say like, oh, what do you mean? I'm gonna write out all the fields and like their data types? And they're all like, no, I don't want to do that. And they just are like, I know we're talking about generics and they will be helpful, but I would see consistently people with Python and JavaScript backgrounds be like, I don't like the sound of this. This is going to take forever. And then Ruby and functional programmers generally had a hard time with both interfaces. They'd want a bunch of interfaces and they would want few validations of their data. And then everybody, no matter what your background, frankly, even if you've been writing Go, everybody really focuses on writing libraries in different forms. Everybody has like a new idea of how they could make a library because Go doesn't have like the sheer volume of libraries in other languages. So you immediately have that like, I'll go build one. And everybody wants to add concurrency. So what I'm going to do for the next couple sections is walk through where I saw these people, whether they actually came from this background or just would get stuck. But these are the places where I would see programmers kind of deviate from idiomatic Go and start doing their own kind of setups. And it was frustrating at first to watch and feel like, oh, this is not great. And then it was actually really validating to realize it's not that big of a problem. We can pull back, we can refactor. And that's essentially what you can hopefully train on if you're in a similar situation. But before I dig in, I really want to bring up back to Greisemer with the mainframe. I don't know if people caught this, but she's the one sitting next to Howard on this picture. And a lot of people know her. She's reasonably famous, technically did not create COBOL. She created a theoretical language before, but was the advisor for COBOL and was heavily guiding on write something that humans can read, make this readable. And I found at one point a quote. I should have looked for it, but I loved it. It was like a really serious quote of, why would anybody want to write in COBOL? They can just write it in assembly. Like, what? Who needs that? They're not real engineers. If you're a real engineer, you're going to write in assembly. And you can see it a lot in programming. So then it became COBOL and C. Why are you writing in C? You need a header file? Please. They did need header files. Like, it's very helpful compared to COBOL. But they would have this debate about like, oh, you shouldn't have that. And then you see it was C in all of these languages today and similar across different languages. And the major point in what I saw when I saw these people with different backgrounds come in to working with Go wasn't so much that like, oh, you shouldn't do that language. If you're a real engineer, you would use Go. I haven't really heard that sentiment. But more that by using a language that actually is pretty agnostic in experience levels, so you can bring in people with a Java background, you can bring in people with a Python, JavaScript, Ruby background, and they are all going to have things to learn to write great Go code, but it's all reasonably similar and it's all reasonably manageable. It actually means you can start creating these teams with more confidence. You are going to want to make sure you've got a couple people with production Go experience. I would recommend a few more people than what we had in our project, but as long as you've got enough people that can make sure to be guiding, you're gonna see pretty decent code, and you're definitely gonna see it's functional. You're not gonna see like issues of bugs of like it's broken. So this is like, I just love that Greisemer really pushed this whole like, it's okay, use whatever language is the best for you and the best for your systems. And I wanted to share that before covering the last part. So these are some of, besides language background, these are some of the things I kind of look for when I'm working with an engineer to see kind of where their perspective is and where they're coming from and what they're going to be thinking about when they're writing code. Because all of this is actually really important when you're working with legacy systems or next to them or replace whatever. So there's 4 kind of things I'm watching. One area is like, have they been working in production with customers? So have they gone through that exercise of like, all right, you got to be deploying, you have to make sure it actually works. If you do not, somebody's gonna yell. Or maybe have they been working in internal systems? Because if you've been working in internal, you tend to have a longer buffer for, oh, it's okay, we'll just try again. We're just bothering our own employees. On the flip side, there's this nuance around new development and legacy systems. And if you are trying to modernize anything, both of these skills are incredibly valuable and incredibly useful. And most people are not going to have both. Most of them will have kind of a mix. But when I say legacy systems, that can include maintenance work, which is very common. People that have had already established systems and they were contributing features onto it. So it could be a mix. This can fall in between, but you could just be saying like, okay, here's your setup, follow this template, and you're going to launch something. And you're not going to get the experience of, okay, I'm telling you to go create something that didn't exist before. And the thing that exists right now is frustrating, but very functional. And your thing also now needs to be not frustrating and functional. And all of those 4 skills are helpful to kind of see where the engineer is at, see what's going to freak them out, see what's going to make them stressed, and then you can use that to evaluate how you guide them towards strong Go production systems. So the next section. So this is probably my biggest learning, that if I could just go back to the start, I would probably just start on these couple topics, frankly, even just the top 2. Probably the third, probably all 3. But either way, what I would go through in like a minimum viable training course, and what I mean by that is you're trying to give them enough training that they can go be productive. You don't want to give so much training that they're just like, I don't know what to do. Like, that was a lot. I feel like I need to go read a textbook. They should. If they want to read the textbook, it'll be very helpful. But you want to make sure they don't feel like they have to go get like a minor or like a degree in Go to be productive. And you also want to watch like how much rework is this going to take later? And is the rework something that we can just release as we're going? Or is the rework something where we're going to need to kind of really step back and say, how do we want this service operating? Worst case, do we need to start over? Type conversation. And then the bottom 2 are probably the most helpful that I saw, where you just kind of want to encourage learning and testing and drafting, because a lot of times engineers, I've felt this, feel a lot of pressure to get it right the first time. And that's not how programming works. You're going to write your code. I write my code it's functional, and now I'm going to go refactor it. And what I've found over time as I've gotten more senior is it's not so much that I just like spit out the right code immediately the first time. Sometimes, sure, if I've done it recently. But a lot of times what I've done is I've just gotten faster at going from this is functional to this is idiomatic. This is something that I can explain all the types and stuff like that. So what I've really focused on is encouraging that kind of cycle of iteration. So that's kind of what I would focus on when training a new org. If they don't have a lot of Go experience, I would watch and see where I can help them out. Now the first piece. So this is just straight copied from my absolute favorite in the entire world reference for Go. And it is the wiki page for Golang code review comments. I'm going to just throw this out there. I do not know why it's so hard to Google for this page, but if somebody could fix the SEO on it, would be phenomenal, because this is I actually was looking at it this week. I haven't read it in a minute. I think they've added some more stuff to it, but it's probably like 13 to 15 pages if you print it out. And it just hits. All of these comments are very, very valuable. If you go through and read them multiple times, you're going to start learning things about what do we mean about idiomatic Go. And you're probably not gonna, if you're coming in cold, you're gonna be like, I don't know, that's nice. But when you write code and read it again, and write code and read it again, and you hear somebody say, oh, you're gonna wanna do this or that, and go read it again, things will start making sense. So interfaces. This one is the first thing I would focus on, and it was actually, pat myself, it was the thing I did focus on at the start. I was like, wait, whoa, we have to define these interfaces decently between systems. And what this code shows, first of all, love that they put in all caps in a comment, do not do it. Hilarious, just incredible, whoever wrote this. But what they're saying here is they're saying, this is common in a lot of languages, definitely common in Java, is when you're making a class, you're gonna define an interface that has every single method listed. You're just gonna, these are all the methods that you could use. And it kind of looks nice. It kind of looks like, it sort of reminds you of like C header files, but it's just a list of things you can do. And you're like, look, it's like my home page of like, these are all the methods for my interface. Fine. That's actually in no way, shape, or form valuable for the consumer. Why not just make the whole thing public? You just listed all your methods. And what it forces the consumer to do of your package is every time they want to create something that you've defined, they need to define every single method that you listed. And it's actually very annoying. And so what Go is bringing up in this section is don't do that. Don't do that. Actually, just have your methods as a part of this thing that they've defined, and then at the consumer level, they're gonna define the interface. So you see that top right section, they just say, hey, this is the interface for Thinger. You're gonna call this method thing. Wonderful, everything is fantastic. And then what you see here, you see consumer.go, consumer.test. What you've allowed the consumer to do here is define their own alternative packages that are the same interface as your package, but it only has the methods that they care about. So you have just saved them an incredible amount of time. Say I am writing a system that all I want it to do is add values into the database. I do not want it to delete. I do not want it to update. I don't want it to do any of those things. I'm going to define a consumer interface that it just only lets you add. And so what that will tell programmers who come in after me is you can't delete it even if you want to. Yes, certainly. If you're writing to a database, they all have ways to delete data inside of there, but I don't want you to do that here in this code. And that's what this is getting at. And so when people start to understand this, they start to see some of the freedom in interface design, and they start to see how they can set up their systems to be very specific and intentional and clear about what they want to be doing at their consumer level. Now, the second thing that I will be bringing up is around typing. So this is the one where programmers come in from untyped languages or things that just sort of let you flip around between all your types. And they say, I'm sorry, what? I just want to save this into their database. I just want to I just want to get it in. And there's actually some content from Bill Kennedy that's incredibly, he tends to open his courses with this and have resonated well with me and really resonate with all the mainframe learnings from earlier around the entire job of software engineering, generally speaking, is taking data from one location, transforming it, and saving it somewhere else or getting it to another person. That's kind of the job. And a lot of times when you start saying, I'm just gonna throw the data around, what you end up with is very much like a mainframe type scenario where you have all these references to data and you have no idea what's gonna be used where. So the thing to think about that I've seen kind of calm down engineers when they're in this situation is to not think of it as a massive list of fields that you need to all of them are different, they're all unique, you're really oh geez, this is frustrating. And think of it more like, this is a JSON representation. In many cases, that's what we do. There's only so many data types. You can have an int, you can have a string, you can have a Boolean, you can have a collection, but there's only so many things you need to be working with. And breaking your structures down more programmatically tends to help them see that they can actually work through definitions quickly, get all these validations going, and feel very confident that their data is really correct and safe at the end of the day. So, oh man, I got a bunch to talk about. All right, I'm gonna speed through a couple of these slides. The last thing I'm gonna bring up is library development. I'm just gonna bring in this section. A piece that comes up if you're in a larger company and you do not have well-established Go practices is everybody's gonna say, build me the libraries that we've got for Java, that we've got for Python. I need you to just make the same libraries. We already got it for Java, we must have it for Go. And on the flip side, newer engineers, they're gonna say, I need to write this library because I'm writing code and nobody else should have to write this code, we'll make a library. And a huge opportunity here when if you're new, if Go is not a well-established language at your company, is to really rely on your senior engineering level to think through how do I learn from the libraries we've created in the past, and how do I ensure that when we create libraries, we're being very diligent to make sure that it's good quality and we've done enough testing in it. So I would just encourage relying on those people there. All right, testing and code review. Man, I want to talk about everything for a very long time. I'll speed through this. This is a cool one. This just talks about systematics. This is the mainframe system that I worked on. Again, it's a program that's installed on these mainframes. And this is from a couple years ago, but it's still in use today. It's pretty popular. One thing when I worked with these systematics engineers that they would talk about was when they were creating this, some of them worked at this company back in the 90s and 80s. They said the quality of code, the care that everybody put into it, into the system back then was so high that there was never a doubt that every engineer really understood what they were building and why the data needed to look a certain way. And that's what built something that lasted for so long. So I'm gonna highlight just a couple of the things that are really, really valuable in breaking down testing. we will probably reference it throughout this conference, but testing tables, fantastic, really, really helpful. Defining your testing tables to look like the function definitions that you're calling is actually really helpful. So thinking about it like you've got your input and your output to whether it's a function, whether it's a handler, you want to define your testing table to look a lot like the function you're calling. That tends to simplify things and make it really clear for input and output and validations, and I've seen programmers build tests a lot more quickly with that. Now the last part though is a really good sign, you want to like a smell kind of, is and I've done this, you're building test tables, they're getting pretty long, now you're trying to build, like you're trying to do data validations, you're trying to check if your dependencies are working, you're trying to check if your business logic is working. That tends to mean that you want to split up that function. And it's a great way to start writing more idiomatic Go code is to see when your testing tables are like trying to test a bunch of things at once. And if that's happening, see where you can split things out, see where you can simplify and shrink down the scope of a function. It's a really good place to look for. The last thing I'm going to bring up about testing and code review, so I would personally, I just consider this like the poor person's code review. So you've got a ton of code reviews that you want to do. You'd love to do all of them. You know you can't. What are you going to check for that's most impactful? I tend to do like, I'll kind of line up like 15-minute reviews to see like if I could just check through and see and notice anything, whether it's actually a bug or just like you consider this or that. These are the things that I'm looking for in order. And I'm going to just move to the next slide. What's nice about this is you can actually kind of split. A lot of times you have two code reviewers. If you are, I tend to work with engineering managers, and what we'll try to do is have the engineering manager more focused on the use cases and saying, have you tested all of the ways that our system could actually be used? I'm more focused on the code quality. We're both looking for both, but it makes it in a way where we've got two eyes and we're kind of specializing on different areas, and it makes the code review less overwhelming and faster to do. You can do this with anybody, but I have found this to just having a checklist of the minimum stuff I'm going to look for be really helpful. Now finally, I'm just going to show a couple of pieces of what we've built, and I'll just kind of end on where we've gone. So this got formatted when I changed to Keynote weirdly, but this is what we are actually building. So when I talk about mainframe scale, you have to get all these daily updates for every single account that's gone through, every single transaction. We do not have incredibly high volumes of traffic going through 24/7 yet. It's going to get higher over time, but it's still not overwhelming. The interesting part about banking, as you guys know, you spend your money and then you are in like it's like in processing, pending. And then the next day it updates to be, it's good. What's happening there is you're going through the Federal Reserve, you're checking if like money transferred between all these people. So what we get is essentially like this big dump of all the updates. Like, okay, we've processed, update everything now. And what we want to do is do it as quickly as you can. So we see, I'm going to skip towards the end. Actually, I don't have it all in there. So we've seen up to about like 5 gigabytes per second come through every day that we're trying to process as quickly as we can to update all of our systems. And that creates this interesting load that we've got to handle. And the piece that I will end on, I guess, is I fully expected when building this system that at some point I was going to need to like slow down the team and be like, okay, I need a couple days. We're going to need to refactor and add in some concurrency because at some point we're not going to scale. And to my disappointment, that didn't happen. We actually just scaled. And in fact, where we saw issues had nothing to do with our code, and it had a lot to do with our infrastructure. They are not bad issues, but it had to do with we're gonna slam you with a bunch of data. So the load balancers actually have a certain level of capacity that they allocate. And if you start, this is our traffic pattern, so you can kind of see we've got some real-time data going through, reasonable volume, and then we've got every single update that's coming for every single account across Capital One. And what you see is okay, here's everything happening. And learn some cool tricks around how to scale the load balancer, not particularly hard, but you need to do it. You're gonna see it at your database level. You're also going to see, what we've found is we've seen it when dealing with other people's systems, like in the company, way more than our own, which is kind of disappointing when you're like, oh, I really wanted to go through and add this. But also really fantastic from a language standpoint that you often don't have to add concurrency. You will sometimes, but you tend to not. And my tip here, though, is if you do not have advanced performance testing systems, that's actually a very fun you'll probably want concurrency built in there, thing that you can build that will be really, really valuable and help you out. So the final thing I want to bring up is this is sometimes what our traffic patterns look like. So we'll just kind of see tons of requests, and the request volumes themselves are not that high, but the volume of data coming through can be incredibly large. And I remember pulling up production and seeing that this was our traffic pattern and being like, oh no, like this, what was this? And the like pause to realize that like actually everything was perfectly fine. Didn't matter. Nobody was getting alerted to anything. This was just like absolutely what we can scale to. Was really comforting. And at this point in time, over the last like year-ish, we've gotten over 33 million requests, and we've processed. I was hoping we were at the petabyte scale, only at 841 terabytes of data, but we're getting pretty close. And that's just what we've been running so far in this system, all written in Go. And the last bigger thing I wanted to bring up is we did in fact shut down one of our mainframes back in June, which was like my personal, like I was real excited to do it. There's a bunch more to do. But just based on scaling up the systems, writing them all through, had a lot of success. Okay, so the last tiny things I'm just going to mention. First, really quickly, I really want to say hi to my mom. She's watching this. She's not an engineer, but she's actually got really sick over the last month, and she's watching this from a hospital where she just had chemo treatment this week. So I want to say hi to her, and if anybody's watching and you want to just say like, hi mom, I think she would really appreciate it. She was so excited. She kept saying like, you got to do this. You can still go through with all of it. And I think she's just loving seeing everything that we're doing in engineering. You could say hi mom to my mom or your mom, whoever's around. But the final couple updates is we were talking about this last night, and I was like, I'm pretty sure you can write Go on mainframes. If you can't, you could. It's just not supported. And I went and looked, and like for sure, we could definitely be writing Go systems on IBM's mainframes today. So just throwing that out there for anybody who wants to do that, I would be interested. And in fact, next September, there's like a actually pretty legit looking conference in Philly. So if you are interested in these like mainframe modernization efforts, it's alive. There's a lot of people engaged. And I'm so excited and happy to be here. I hope this was helpful for some of you. And if you have questions, if you have ideas, if you just want to talk about legacy development, I would be thrilled to. And I will just end on this final, one of my favorite quotes from Grace Hopper, where they said, you know, computers would only do arithmetic. That's what they said when they launched mainframes, like we're just going to use it for math. And she really looked at that and said, I think we can do a lot more here, which I find fun and I hope happens for a lot of you in your careers. But that's everything. Thank you. And I will hopefully see you guys all on Discord.
Awesome.
Yeah. Hi, Mom.
Shout out to Kaylyn's mom. Awesome. Thank you so much, Kaylyn. There's a lot of awesome takeaways from your talk, and yeah, it's something I'm looking forward to.
You're not alone. There were people talking about mainframes, so
Seriously,
there is more than just you.
Yeah, and yes, GoBall is getting generic. She's just gonna have to use a lot of redefines.
Yep. I saw a couple mainframe startups getting started, so you inspired that for sure.
So next up, we're going to have lightning talks hosted by Mark Bates, and I just want to highlight like how much of like an integral part of GopherCon the lightning talks have been, and it's
Mark has put in a super huge amount of work to make these amazing.
Every
They're
year.
Really going to be.
Yep.
They are every year. Yeah.
Yeah, there's always really amazing talks. It's a great opportunity, as we kind of talked about in the opening, for you to dip your toes into things or to try out new material before you write a bigger talk on.
Yep.
And so I just, I can't thank Mark enough for doing this for us every year.
Thank you, Mark.
And if you tell him I said nice things about him, I will deny it, I swear.
We love you, Mark.
We love you, Mark. Yeah.
All right, so with
I want to do a quick mention of the VMS, the virtual meeting spaces. You got to go on the platform, gophercon.com, to sign up for these. It's free. It's just part of the platform. We've got Brad talking about a financial services lakehouse. And we've got two sessions from Microsoft, one about Azure for Go developers, the other about gRPC. Feel free to jump into those. You can jump in there and the lightning talks and switch back and forth if you want to see both. Totally fine. That's all for me. That's my spiel.
All right, now I got to go wash my mouth out for saying nice things about Mark. All right, take it away, Mark.
Hey, everybody. Welcome to GopherCon Lightning Talks 2021, Day 1. Oh, it is so great to be back again this year. I just wish we could all be doing it together. Um, Hopefully next year, I miss you all in person, but that doesn't mean we still cannot have a wonderful time this year. So far, I think you'll all agree, the programming's been amazing. And, little secret between you and me, it's only going to get better. Why is it going to get better? Because we're going to have lightning talks 3 days this year. That's right. Not 1 day, not 2 days, but 3 days of lightning talks. It's an amazing lineup of talks. Seriously, I'm so excited to see it. You know, every year I have the honor and privilege of being able to introduce these new voices and new ideas into our community. And I really take that to heart every year, and I treat it as the honor and privilege it really is. So thank you all for joining me. I think you'll agree that these are truly some spectacular talks this year. So before I bring on our first contestant on the game, as I like to joke, let's go over the rules of the game. The rules of the game are quite simple. Each speaker will have 7 minutes to present their idea to you, the viewer. Whether that be an idea about a package they wrote, and a concept they had, or just how to perfectly grind and roast those coffee beans. They have 7 minutes. If, however, they start getting a little long in the tooth, at the 1 minute left mark, they will hear this. There we go. Gotta be faster with that, Jose. And of course, if they run out of time, the infamous curtains will close on them. That's the only time the curtain ever closes on Mark Bates, is when I'm demonstrating how the curtain closes. Anyway, with that said, I don't want to keep going on too long. We have such a great amount of content here to present to you today. So we're going to bring up our very first speaker here today. Alan, I believe you are with us here, correct, Alan?
Hi, yes.
Great. How you doing?
Doing great. Thanks for having me.
Great. Well, it's great to have you. Where are you joining us from?
I'm here in San Francisco, California.
Very, very nice. You have a lovely painting and then a lovely piece of acoustic tiling over there.
Thanks. Yeah, that's my wife, and I made that thing.
Lovely.
During my COVID pandemic project.
Fair enough. I love it. Well, awesome. Alan, I'm going to let you talk. You're going to talk a little bit about a new Redis implementation, if I believe. So take it away, Alan.
Okay. Hi, everyone. I'm Alan, founder of Wakatime. Wakatime provides dashboards and automated metrics for programmers using open source IDE plugins. I'm going to talk about how you don't need Redis. With Redis, you can only store as much data as you can fit in RAM. Today, I'll show how we can use disk space instead to cache much larger data sets. Feel free to reach out and contact me by email or find me on Twitter. So here's the Wakatime dashboard, or leaderboard, sorry. Loading this leaderboard used to take over 30 seconds because we had to query the code stats for over 10,000 developers. That's unusable, actually, 30 seconds. So we definitely had to figure out how to fix this. So let's solve this problem together. We start by caching the page in Redis, the awesome in-memory data structure storage server. Wakatime uses DigitalOcean, so I'll boot up a $100 per month server and set up Redis on it. This gives us about 16 gigabytes of RAM to cache the leaderboards. And we write a function get leaderboard from Redis cache. We pre-cache the leaderboard page in Redis. It's a simple get by key for the leaderboard. We can't just cache the main leaderboard, however, because we have permutations of leaderboard by language, by hireable badge, by country flag, and we have up to 100 pages of each of these permutations. Each permutation is about 140 kilobytes. So times 622 languages, times 250 countries, times 100 pages, that's a total of 2 terabytes of data that we have to cache. Thankfully, we can compress that down, though, to about 24 kilobytes per page. But still, that's about 363 gigabytes of data that we have to cache. 300 gigabytes is much more than that 16 gigabytes of RAM we have. So on our DigitalOcean droplet here, the RAM that we have available won't be enough to cache all of those leaderboards. So what do? We could upgrade to a $2,000 per month instance that gives us 256 gigs of RAM, but our 373 gigabyte data set still won't fit in that 256 gigabytes of RAM. So the solution is something called SSDB. SSDB is a drop-in replacement for Redis that uses disk space instead of RAM to store your data set. SSDB uses LevelDB from Google, but it can also use Facebook's fork of a LevelDB called RocksDB. And LevelDB and RocksDB use SSTable key value library or key value table that is written by Google based on Bigtable. And using an SSTable, you can SSDB is able to look up keys on disk with a single seek. So it makes its performance on par with Redis, actually. So now we can use this storage optimized instance from DigitalOcean for $155 per month instead of $2,000. And it comes with 450 gigabytes of SSD NVMe storage, plenty of room for our 300 gigabyte data set. And we just saved about $1,800 per month by not using Redis. And because SSDB works with your existing Redis clients, you don't need to update any code. You just change the IP address of your server and point it to the SSDB instead of Redis, and nothing else needs to change. There are some limitations, however, with SSDB. There are some differences between SSDB and Redis. So SSDB can only expire simple keys. Actually, let me start with there's no Lewis function support. There are some command changes, like some commands are renamed zadd and zset and some others as well. And probably the most cumbersome thing is that SSDB can only expire simple key value strings, not HMAP or lists, but you can always manually delete them with one command, same as Redis. So bearing in mind those limitations, SSDB is very simple to configure. It has less config options than Redis, and therefore it's extremely simple to set up. Just make sure to increase your Linux machine's file max settings so that SSDB can open enough sockets and file handles to be performant. And also remember to run the SSDB CLI compact command to reclaim disk space from deleted or expired keys. And I've included a handy one-liner for that compact command here that makes it easy to run from a cron script because normally it blocks on user input. But this gets around that, so you can run it automated. These are the two things you have to remember with SSDB. And if you're wondering if using SSDB instead of RAM, or SSDs instead of RAM, SSDB actually performs better on average than Redis when writing keys and about the same when reading. And that's it for me. And thank you for having me. And mic drop.
Well, thank you very much, Alan. That's the virtual mic drop for you. Love it. Awesome. Well, thank you so much. I'm definitely going to be checking that out. Okay, so let's bring up our very next speaker, Marcus.
Yes, hello.
Hey, how are you? You can hear me then, I take it?
Yes, I can, definitely.
Fantastic. How are you doing?
I'm good, thank you. How are you?
I can't complain. It's GopherCon.
I know,
Nothing
right?
to complain about. So where are you joining us from?
I am calling in from Aarhus in Denmark.
Denmark. Awesome.
Yes,
interesting.
right.
And you're going to be talking about HTML components?
Yes, exactly.
That's
HTML
far out of
components
my
in
pay
Go.
grade, so I'm going to let you talk about that. Go for it.
I know, right, right. So yeah, this is my lightning talk about HTML components in Go, or why I sometimes miss React. Because the thing is, I really like React. I've been a full stack developer for a long time. I've been working, with JavaScript, doing web UIs, and what we all know and love. There are two main reasons why I really like React, and none of them are actually technological. So the first thing is the mental model. It's just nice that it's so simple. It's quite elegant. It's easy to be productive in it, but also it's really easy to communicate to team members about how you put these components together in the front end, how you compose them together to build a greater whole, whether you're building a web UI or an application or whatever. So the second reason is the ecosystem. So no matter what component you really need, you can fire up your favorite search engine and then try to look up whatever component you need and find something pretty quickly, and then basically get it running with a fairly high percentage of probability. So that's why I really like React. But now I'm a Go developer, right? So how do I do this in Goland instead? So I've been writing Go since 2016 now. And I was really missing that way of writing components. So I thought to myself, well, I'm a developer, I could do something about this. So of course I did. So I'm introducing components. Of course, this is a wordplay between components and Go. And if you look closely, there's a tiny bit of DOM in there. So pretty good. Oh, and then wait. So let's go back to my reasons for why I like React, and how does this apply to components? Well, one thing is it's the same mental model. So it's all components that are composable. It's the same idea, basically. You can build these components together until you have a web UI that you're satisfied with. So, and the basic premise is that you have some data that you put in, and you want some HTML out, right? So that's how we build our UIs. So in components, the components, they are just Go functions. And I'll get to that in a minute. But before that, a little disclaimer. When I'm talking about this is all the classic web, or whatever you want to call it. So server-side rendered components that are from the classic request-response cycle. So there's nothing fancy about WebAssembly or anything going on in the browser. This is all just, we want to generate some HTML, do one thing and do it well. So with that said, let's have a look at some code. So we have our imports, of course, we import the package components. And then also you'll notice I'm using a .import for the HTML package inside components. So I know this is generally frowned upon, but bear with me for a second. So here we have our actual function, the component, which is a navbar in this case. So as you see, it's a Go function that we know and love, and it returns something called a node, and I'll get back to what that is exactly. But it returns this nav thing with a class, an ordered list, some list items, some links that have an href attribute and some text in them. So basically, if you can read HTML, you can pretty much read this as well. But this is only one component with some HTML components underneath. So how does this look when we refactor it? So let's take our navbar and extract the navbar item, so basically the list item. And then add some properties, the data in and the HTML out I was speaking about earlier. So there's nothing really surprising about any of this. If you've ever written React, this is basically how you would do it as well. So now you have a navbar and a navbar item, two components. Let's have a look at a slightly more complex example. So we have some authentication going on, maybe. We have a logged in parameter that we pass to a navbar component, as well as a current path on where we are in our web app. So we can use the if function that's also provided by components, which is a really simple function that just takes an expression. And then if that expression is true, you basically return the component. And if not, you don't. So you get these nice inline declarative ways of describing components. Also, another helper is the classes helper, which is basically a map from CSS classes to, again, a Boolean expression. And if that's true, the class gets included. If not, it doesn't. So pretty simple like that. So how does this render to whoever is viewing it? Well, also, again, our basic HTTP handlers that we all know and love from the Go ecosystem. So in this case, we have a response writer, W. We have a home page component, and we call render on it, and then pass it that writer. And that's basically it. Of course, in this case, it returns an error, but as you remember, you should always just ignore errors. So this node interface I was speaking about earlier, what does it do? Well, it's really simple, like most good interfaces in Go. So it has one function in it. It's called render. It takes a writer and it returns an error, and that's basically it. So if you want to do a component, you have to implement this interface, and that's it. And of course, in components itself, as you saw, a lot of the HTML elements and attributes are already included for you, so you don't have to write them yourself. If there's anything there that's not included, then you can use some functions for that as well. To basically, so there are some other helpers as well. Map for mapping data to components, group for grouping elements, raw for injecting HTML, and textf for string interpolation, and some other stuff as well. So the ecosystem is components, and hero icons is something I created. So icons are by the excellent Steve Sugar of Table and CSS fame. But yeah, this is something I built, and of course I can't build all the components myself. So this is where you come in. I'd really like for components to take off, and then people start building these components. So if you want to join in on the fun, go to gomponents.com, check it out, download it, have a go at it, try it out, publish whatever you find, and that's basically it. So yeah, thank you very much. This was a talk by me. You can find me on Twitter, MarcusRGW. And I also build online Go courses at golang.dk. Thank you very much.
Thank you, Marcus. That was awesome. I told you it was going to be above my pay grade. HTML, it ain't what it was when I started doing it in 99, kids. That's actually 96. Sorry. Anywho, I was getting ahead of myself there, making myself a little younger than I actually am. All right, so enough about me. Let's bring up our next presenter, Tom. Tom, you there?
Hi there, Mark. How you doing?
All right, and yourself?
Very good here. Yeah,
fantastic. Where are you joining us from?
I'm joining from Zurich in Switzerland. And we've got
Switzerland, yes, you can tell by the accent.
I'm British, actually, but I've been here for a few years.
Nice, nice. Awesome. And you're going to be talking about chez moi, is that correct?
Yeah, you got the pronunciation right. You're French.
I have no idea what that is, but why don't you let us know? Thank you very much. Go for it, Tom.
Cool. Thank you very much, Mark. So, hi, I'm Tom Payne. I'm a developer at Isovalent, but this is a personal project called Chez Moi. It's French for at my house. It's a .file manager, and it's only been made possible by Go. And basically, if Go didn't exist, Chez Moi wouldn't have been successful. So this is interesting if you're writing CLI applications for users and you want to get them into as many users' hands as possible. Firstly, what is Chez Moi? It's a cross-platform .file manager, your .files, your config files for Git, Bash, ZSH, Vim, whatever. It generates them for a single source of truth across a massive range of platforms. With multiple install methods, it's super secure. You can store your secrets in your password manager so they never appear in your .files repo. You can encrypt whole files using GPG and Aggie, and it's become really popular. And this popularity is really thanks to the decisions that the Go team have made. It's got 5.4K stars on GitHub, 87 contributors. The link there is you need to check it out, github.com/tloop. Why should you use it? And it enables you to maintain a familiar, customized environment. All the effort you put into configuring your tools, you can now have that across multiple diverse machines, whether it's your home laptop, your work development machine, a Windows box. And what we're seeing at the moment is that although we'll hang on to our laptops for a long time, we're increasingly developing in ephemeral environments like GitHub code spaces or dev containers. And it's really nice to be able to bring in all that work you've done setting up your system into a new system very quickly with a single command, or from a single version controlled branch, so you get backups and history and all sorts. This is a graph of Chez Moi's popularity. It's the yellow line here. You can compared to the other top 4 .file managers at the moment, And you can see that in 3 years, it's gone from nothing to being the #1 doc file manager. And I think this is only possible because of Go. How has Go brought real advantages to users? The first thing is it makes it really easy for users to install. This decision from the Go authors to have a single static link binary is massive. There's no language runtime you have to install. Imagine having to install Python or Ruby from scratch on a machine, particularly if you don't have root. There's no dependencies. Actually, everything gets built into the binary. So it's just a single file that you can copy on within curl, SCP, whatever. Go embed allows us to include lots of other files, and Chamois uses it for documentation. So even though I'm distributing a single binary, there's a Chamois docs command that gives you all the documentation embedded in. The cross-platform by design, the Go authors really supporting Windows as a first-class citizen is a fantastic win, because most doc file managers don't run on Windows. Windows is very different from the classic Unix systems, but thanks to Go's efforts to include Windows, we get first-class doc file manager on Windows too. And Go's text template library is fast becoming the standard for configuring many systems now, particularly on templating YAML. But also, it's not just for users. It makes it really possible for developers. It makes it an easy project to contribute to. The high-quality platform standard library means it's just less work that you have to do as a developer to get cross-platform compatibility. An interesting thing as well, compared to other languages like Rust or Python, the concurrency built into the language means that all Go libraries are compatible. They all use the same concurrency primitives. In contrast with Python, where you have to choose between gevent, twisted, or in Rust, which version of async, whatever you're using, they fragment the ecosystem. But Go doesn't suffer from that. Of course, you've got excellent cross-compilation. There's some fantastic tools from the community. I want to particularly highlight TestScript, which is actually pulled out of the Go internals project, which is this fantastic integration testing, a project called Go Releaser, which if you're distributing your Go binaries, it builds you packages for everything. It's absolutely brilliant. Go check it out. But another thing I've sort of observed when learning the Chamois is that it's not just shared libraries that matter, it's also the tools that you might have to depend on. So for example, Chamois allows you to encrypt whole files with Akhil, which is a new GPG-like encryption tool. But rather than relying on an age binary, as this is distributed as a Go library, I can embed this directly into Chamois. Similarly for Git, thanks to the great GoGit project, you don't even need to install you don't need to install Git on your machine to be able to check out your Git repo. And I'd like to encourage people as a pattern to use that. If you're building a command line tool, please do make a library version of it so that others can embed here and avoid those dependent on external binaries. That's it, very quick. The lessons I want you to take home. If you want to build a popular tool to get maximum user reach, you want to minimize your external dependencies, you can make your tool available as a library. And of course, please do go check out Chamois. Thank you very much indeed.
Well, thank you very much, Tom. I appreciate it. It was wonderful. Just to double down on something Tom said, I agree. Make your CLIs available as importable libraries. I was just telling some of my students last week that exact same advice. Make it so that us tool developers don't have to have dependencies in external binaries. That was an excellent talk. So up next we have Yuri. Yuri, are you with us?
Hi, Marek.
Hey, how you doing?
I'm okay, and you?
I'm doing great. It's GopherCon.
Yeah, awesome.
Where are you joining? Exactly, where are you joining us from?
Yeah, I'm joining from Kraków. It's in Poland.
Ah, very nice. Yes, exciting. And you're going to be talking about doing front end work. Is that right?
Yep, right.
Oh, all you people in the front end work. Okay, you're far better than I am. Go for it.
Okay, thanks. So, hi everyone. Today I'd like to present the library named Kyoto. It's an SSR-first Go front-end library, and if it's not so interesting for you, feel free to take a cup of coffee during these 7 minutes. So, but first, let me introduce myself. I'm Yuri Zinitz. I'm software developer at Akamai, but also a core developer of Broker One real estate platform on part-time. And the overall story I'm going to tell is actually related to Broker1 development process. So before I start to talk about Kyoto itself, it's really important to know backstory because we are not creating technologies for technologies, but for solving different problems. So, long story short, in the beginning of the platform creation, we decided to create a prototype first. We took a well-known JavaScript framework with a set of ready-to-use material components. And as usually happens, the prototype became the main project. Over the time, we began to feel the impact of this decision. It was hard to keep overall project setup clean and tidy. We had a lot of difficulties with SSR, memory leaks on server side, and performance score issues. We completely lost control. And after this discussion, our team decided to drop this prototype and go in more traditional way, use template engine. And so why did we choose such a radical way? We had several reasons. Unnecessary complexity was one of those reasons. Not many people really understand how their project setup works under the hood. We pack with tons of configurations, Babel, tree shaking, lazy loading, and especially when it's not work as expected. You need to bring a significant runtime and virtual DOM just to render a simple things like articles or pages with minimal dynamic behavior. Template engine reduces overall complexity and allows taking full control over front end. Also, this approach reduces amount of bugs and quirks because we can find most of the problems on the so our project became much better with this migration, but we faced some common inconveniences. We have started to use more copy-paste. Our handlers became a spaghetti because of asynchronous API and database requests. And we all have to admit vanilla JavaScript is quite verbose for simple dynamic things. That's why Kyoto was born. And we are going further. What future Kyoto provides? How it solves these issues? First issue solved is called organization structure. For each page and component, you have separate Go structure and template definition. You can include data fetching and display logic just right inside the component. Second thing I provided is page rendering lifecycle. This allowed me to solve asynchronous calls issue. You can implement asynchronous method for components, and it will be called with own Go routine under the hood on page rendering. As an example, you have 10 instances of the component on the page. In that situation, 10 Go routines will be created for each asynchronous call. And the most interesting thing in this library I've implemented is a built-in dynamic functionality inspired by Hotwire and Laravel Livewire. It's pretty simple and limited because it's created for simple things, but people really liked it, and I'm extending functions over the time. And as the project has solidified its core idea, I'm able to make some plans for the future. We are already working on UI kit based on Tailwind UI and already using it for our internal tools. Anyway, it still needs a lot of work. Also, one of the features I'd like to provide is a server-side state. This approach will reduce unusual amount of data to transfer between server and client. And last, but the most interesting thing and crazy idea I'm experimenting on is bringing the whole rendering process to the edge workers. It's giving to us a serverless setup, insanely fast responses. Unfortunately, Cloudflare edge workers have a lot of restrictions, like 1 megabyte executable size limit, and don't have official support for Go. I was able to run Go and on the edge workers with tiny Go compiler and Wasm, but it's not enough to be able to use Kyoto as expected. And so here is a quick summary for this talk. I think Go has a big potential and it's not limited by current domain. Otherwise, it would be impossible to create tools and libraries like this. And I'd like to note that Kyoto is not framework by its own. On my opinion, combination of UI kit, project blueprints, and best practices are actually became a framework. And I'm not creating Kyoto opposite to JavaScript solutions. Even more, it's possible to integrate them. I just believe that every solution has its own purpose, and I hope the solution will have someone too. So you can find all the needed links on this slide. Don't hesitate to contact me directly anytime. And that's all from my side for today. Thank you for your attention.
Well, thank you very much, Yuri. That was
Yeah.
wonderful. Awesome. So much great content. Well, we've got to just keep going here. So I'm going to bring up our next speaker, Ron Evans. Ron, join us on stage.
Hello, GopherCon! Yes. All right. It's so great to be back with you, Mark. But Mark, what happened to your beard? You were supposed to have a beard. I trained the targeting computer for my drone to look for you with a beard. So
well, that was the plan. I figured I would grow the beard, fake you out, then shave it off.
Clever.
You like that? Hola, mi hermano. It is lovely to see you.
It is great to see you as well, my friend.
Again, wish we could be doing this in person.
Well, we miss you all. You can see I'm wearing my retro GopherCon t-shirt, and I'm wearing my GopherCon hack session pit crew t-shirt.
Love it.
Shirt. So yeah, we're ready.
Okay, well, give us the update on TinyGo.
All right. So this is a small update about TinyGo. So I am Dead Program, aka Ron Evans in the real world, but that's not really that important. Technologists for hire, that part is always very important. At the hybrid group, where we're a bunch of technologists for hire doing software for hardware companies. So I'm here with GopherBot. So GopherBot joined the universe 2 years ago at GopherCon. And so you can go get the source code and the 3D models to build your own GopherBot. I've also got my Go badge. So we never actually got to introduce this, unfortunately, because the COVID happened right then. But this is a Go-powered badge. So yeah, next time we're all together in person, then we can hack on those together. So those were both made using TinyGo. So if you've been living in a very remote place, you don't know about TinyGo, but it's a Go compiler for small places like microcontrollers and WebAssembly. Yes, you don't need to use Rust for WebAssembly. You can use Go. So let's take the current stats. Over 9,000 stars on GitHub, 495 forks, with the latest dev branch having over 2,400 commits, over 100 contributors. Thank you all so very much for making TinyGo what it is. Over 74 different hardware boards supported and 74 different sensors and displays. And since our last release about 3 weeks ago, 2.75 commits per day since the last release. So the project's going fast. So let's talk about a couple of quick highlights from that last release. Lots of runtime and standard library support improvements. So, your garden variety Go code will maybe just work now. Lots of work done on WebAssembly, especially the WebAssembly systems interface, and we'll see some examples of that. And then Windows. Yes, you can actually build a Windows executable with TinyGo now. It's absolutely amazing. So let's take a look at some TinyGo out in the real world. So here is a really cool tweet from Matt N, known for the MJPEG package as well as the TF Lite package. So Matt N in Japan is very excited about being able to build Windows executables. And we can see here that the normal Go compiler, about 2 megabytes in size, with TinyGo only just under 300K. So also from Japan, Takasago-san, who is a longtime contributor and done lots of cool work in TinyGo, had a really awesome TinyGo workshop recently featuring the Wio terminal from Seed Studio. So that's a very cool workshop. Content's online. Speaking of WebAssembly, so you can actually use TinyGo with the Envoy proxy, and there is an SDK which is available from Tetrate Labs. It's the proxy WASM Go SDK, and it works with TinyGo and only TinyGo. Since you can't write WASM WASI applications using the regular Go just with TinyGo. So check that out. So speaking of more WebAssembly excitement, so recently the WASM 3 runtime project released the embedded WASM apps, which you can actually compile WebAssembly code and run it on embedded microcontrollers. So it's a different way of achieving the same sort of thing you could do just with regular TinyGo, but it supports assembly script, Rust, C++, TinyGo, and Zig. So another awesome place for WebAssembly and TinyGo. So the IOTA project, if you're interested in blockchain stuff, recently released support for using TinyGo as the programming language for their smart contracts. So that's pretty interesting, if that's a new space for many people. And then the Astro project recently, jumping ahead of myself here. The Astro project has got a front-end development package compiler that you can compile the WebAssembly using TinyGo. And in fact, their online astro.build/play website uses the TinyGo compiler. Then, speaking of interesting and cool content, there was a great series that was put together by this blogger, and they wrote a whole series of learning Go. This particular article talked about how to create a Game Boy Advanced game in Go using, of course, TinyGo. So then back to the businessy sort of stuff. The legendary Ray Ozzy's company, Blues Wireless, is using TinyGo for a bunch of very interesting things. Go check them out at blues.io. Then we've got, there's so many things. So Tobias Thiel gave a talk recently at Embedded Fest, which is Eastern Europeans' biggest Linux and embedded conference. So that was a really cool talk. You can check that out on YouTube. Also, Tobias published a book about TinyGo earlier this year. Yes, there is a paper and electronic book for TinyGo. Check that out. So earlier today in Australia, there was the Australia IoT Christmas edition. So yeah, time for the Christmas edition lights from GopherBot. And what is his name? Leon Champton gave a talk, and actually Leon is going to give a lightning talk, I think tomorrow or the next day, about TinyGo. And we've got the suborbital dev recently on the Atmo application server, which is back-end Go, using TinyGo and WebAssembly. So there's going to be a talk by Connor Hicks after this, a full-length talk. So check it out. More info at tinygo.org. You can follow us on Twitter at tinygolang. And thank you so very much. It's been great to be here with you.
Thank you so much, Ron. Awesome. Can't wait to see you in person at some point. Awesome. Well, thank you all so much. Thank you, Ron. That was excellent. And you know what? I survived. Not a mark on me, Ron. Try again next year. Anyway, okay, we have one final talk for you today. They've all been so amazing, and I can only imagine this one's going to be amazing too. Let's bring up our final speaker here. Ryan, are you with us?
Yep. Hello.
Hey, how are you?
I'm doing great.
Great. Where are you joining us from?
Denver.
Denver, Colorado. Fantastic. Home of the original GopherCon. Did you ever attend any of the ones there?
Unfortunately, no.
Oh, real shame. Yeah, the first 5 were there. They were really, that was, honestly, I loved having it in Denver. It's one of my favorite places. So awesome. You're going to talk to us a little bit about memory usage today. Is that correct?
Yeah, I just have a little story about memory optimization.
Fantastic. Go for it.
So, hi, I'm Ryan Hitchman. I'm a software engineer from SourceGraph. And today I'm going to be talking about some work that we did this year. So SourceGraph is a universal code search engine so that every developer and company can innovate faster and find their code. And most of our code is open source, including Zookt, which we use to provide regex code search for 2 million repositories. And this year, a large part of our work was scaling our sourcegraph.com search engine from indexing 300,000 to 2 million repos. And a large part of that effort was reducing the RAM usage for Zookt, for the Zookt servers responsible for handling most of the code search backend. So Zookt is a Go program initially created by Hanwen Niens at Google that performs trigram-based regex search. And that means that it builds an inverted index that has a map of every 3-letter sequence of characters or trigram to its location in a repository. And then by iterating over the locations of each trigram, you can pretty efficiently implement most regex searches. So initially, these are some graphs of our monitoring. The large purple area on the left is the RAM used by the different Zookt replicas. So it's taking about 500 gigabytes of RAM, and the tiny lines under it are all of the other jobs. So by far the majority of our spend for cloud servers was on Zookt. And then the drops are implementing these changes that I'm going to describe. And it brought it down to about 150 gigabytes of RAM instead, which let us scale up a lot more. So Go has some really good profiling tools with deep runtime integrations, and it makes it really easy to collect memory profiles to show you exactly what's occupying the heap. There's lots of blog posts and good documentation about them if you look for it. So as a first step for optimization, I built a test corpus from all the files that one of the backend servers was indexing. And then I collected a memory profile for that. So this shows precisely where it was using memory and gave me the first indications of what needs to be looked at. So the corpus represents 19,000 different repositories from GitHub mostly, 2.6 billion lines of code, and about 166 gigabytes of disk space. So this memory profile has 22 gigs of live objects on one server. The total RAM usage your Go program uses does depend on other garbage collection things going on, but it's pretty decent, and we do set a slightly more aggressive garbage collection threshold. So in this case, we set a threshold of only using 50% more space than live objects instead of twice as much, which is the default. So digging into the code, 2/3 of the RAM usage is by this one function, which is building effectively a map from 64-bit to 64-bit ints to 64-bit structs here. And Go maps are very fast, but they have quite a bit of overhead per entry, 40 bytes. And when the actual data we're storing here is only 8 bytes, that's or only 16 bytes, sorry, that's quite a large overhead. So it's worthwhile to implement a more compact data structure for it. There's many different kinds of dynamic maps you can implement, but all we really care about is being dense and static. So sorted arrays and binary search works really well. So as a first pass, just switching from a Go map to 2 slices, got from 15 gigabytes to 5 gigabytes. And this has logarithmic lookup speed instead of O of 1, but it did not present any problems for our particular use case. And there's a few more things we could do for our usages where instead of an array of 64-bit ints, we can do 2 arrays of 32. But and there was another switch for and that reduced it down to 3.5 gigabytes. And yet a more complex one shifts ASCII trigrams because we're indexing Unicode and ASCII is much smaller. So that got down to 2.3 gigabytes. So we've slashed this one data structure from 15 gigs to 2.3 with no real problems. And a lot of these could be generified now, but at the time generics were not available. So as we shrink the largest problem, other pieces start to dominate. So a lot of pieces of metadata that were loaded from disk into memory, we changed to be memory mapped and accessed on demand. And some other things were left compressed until needed, which shaved off another 2 gigs. And I think the easiest takeaway here is if you have big static slices, you are probably wasting memory because the excess capacity you have that you're not adding to is just using memory. So if you simply copy them into a precisely sized slice, you can save a lot of memory. This was worth 500 megabytes of improvement here. So putting it all together, the memory profile looks like this, which is a 5 times reduction overall, which means that with the exact same resources, we can serve search queries for that many more repositories without requiring more servers. And it went from about 1,400 kilobytes of RAM per repository loaded to 310 kilobytes with no measurable latency changes, which is the really important thing. And I guess in summary, memory is really expensive. We've had a few other talks already about how RAM is expensive and getting giant RAM servers is costly. So have you profiled your applications? You can find some really big wins with small changes if you look with the profile. Greenfield memory optimization is very satisfying, and it's a good distraction from all the other feature work you're doing. So go out and optimize some code.
Well, thank you very much, Ryan. That was wonderful. I'm definitely going to make some of those changes. Well, with that said, everybody, we've come to the end of our program. Thank you very much for joining us. We'll be back again tomorrow, Thursday, and also Friday at the same time with more incredible talks. So with that said, I'm going to throw it back to the studio so we can hear more great content. Thanks for joining us.
Thanks so much, Mark, for putting all this together. Thank you to all the speakers who took the time to put together their lightning talks. I'm looking forward to seeing some of the additional lightning talks that will happen over the next couple of days as well. This is always fun, and I'm kind of glad we get to do it every day. I also, it was great to see Ron Evans too.
He's one of my favorite people in the
I always love that. Yeah. And I heard him mention that we don't need Rust for WebAssembly anymore, and that's a little disappointing because I like Rust. And hey, you all want to hear some interesting uses for Rust?
Wrong conference, bro.
You gotta go somewhere.
Yeah.
All right.
Over town is not.
Is there a Rust channel in Discord?
No, you cannot have Rust at this conference.
Peanut Gallery weigh in though. Should we? Should we or shouldn't we? Rust
I think we should talk about Rust.
No. Hey, did you know we have a mainframes channel? And you don't have to use Rust in there either. Yeah.
By popular demand, we have a mainframes channel.
Wait, so we can talk about mainframes, but we can't talk about Rust?
That's correct.
That's correct. It's a language conference for Go. We got to stick to Go. Yeah.
But we talked about COBOL.
Well, we talked about
Go
Go
Ball.
Yeah.
I mean, yeah.
Okay.
That's different.
All right. I'll concede. No Rust.
Yeah, fair enough.
No Rust.
All right. Well, we've got some content coming up. Of course, there's another talk coming up. We also have some other sessions as well. So I'm going to list them off. I'm the guy who lists them off now. So you just focus in and get ready. All right. So we've got Praetorian. They're a security company. I think they've got some new Go stuff going on. Their new project is called GoCart, which is a next-gen open source security scanner. And security is another big thing that we're seeing these days coming in, especially to Go.
There's been a lot of security tools written in Go recently.
Yeah, and that's super interesting stuff because it's one of those, you don't think of it necessarily, or a lot of us don't think of it, although we should. But then on day 2 or month 2, or then you realize, I got to be secure because I'm running a business with people's data, and it's really important.
Wait, can we tell that to all of the people who have had breaches recently?
I would love to, yeah.
You mean security is not someone else's job?
Not anymore, I guess.
Not my problem, I built it.
Yeah, you got to build it in. So yeah, Praetorian is definitely one of the players in this space. We've got another one called Always Learning. This one is focused on engineering cultures at Course Hero. That should be super interesting. And we've got Buff, a newer company that's doing protobuf stuff, hence the name.
I thought they were just saying, I'm Buff.
They're Buff.
No.
They are a weightlifting company powered by Go. The one's called Buff Helps You Go Faster. We've got our friends CockroachDB doing a live quiz show. Tune into that. That's going to be pretty cool. And then we've got Microsoft coming back at you to talk about GitHub Actions, specifically, of course, how you apply them to your Go projects. So that's going to be
another quiz show.
I guess so.
Man, that's a popular format, isn't it?
Yeah, and speaking of quiz shows, if you've not gone and filled out the survey for Gophers Say, you should do that.
Yeah.
So tomorrow we're going to have a Family Feud style show with Go Time, and they need the survey says answers for our Go Team contestants to guess.
Prove them wrong. Make them think twice about what they thought they knew about this community.
And so you can do that survey at gotime.fm/gs for Gophers Say. We should do that.
I'm going to do that after. Just to get stump some people.
I'm a troll some people.
I'm trolling people. After the episode of Go Time, we're on it.
It's my turn.
That was great fun. It's going to be again. It's gonna be,
And then if you want to attend any of the VMS sessions that Aaron mentioned, you do need to register for that. So just go to the GopherCon.com website to register. You'll need to have a ticket to get in if you're not already registered.
Yep. It's pretty easy to register, a couple clicks, no big deal. But yeah, do that. Definitely check some of these out. They're going to be pretty cool, great fun.
You said do. As a father, I have to
Yeah,
call out
that dad joke.
that has
Okay.
that has dad joke potential to it.
Okay,
Yeah.
fair enough. All right. Do we have a dad jokes channel?
We
I
should.
think we do.
We might have to, yeah. Peanut Gallery, again, weigh in.
Chime in.
Let us
But I mean, if
know.
it's a dad jokes channel, then it has to be a database.
Oh.
Oh, grown. All right. Well, let's get into our next talk. This is a talk by Connor Hicks, who is the founder of Suborbital Software Systems. Again, working on security and distributed systems. They have a family of open source projects. And this one today he's going to talk about is focusing in on WebAssembly again, which, as we've learned,
But
you
in
don't need
Go,
Rust for.
not in Rust.
Yeah,
Not in Rust,
exactly.
okay, yeah.
So with that, take it away, Connor. We're excited to see what you got.
Hello, my name is Connor Hicks. I'm the founder of Suborbital. I founded Suborbital to bring about a step change in how we think about and deploy cloud compute by using WebAssembly as a new technology for packaging our software. So this talk is all about WebAssembly and why you would want to run it inside of a Go application. We're going to cover what WebAssembly itself actually is. Then we're going to look at why you would want to do this in the first place. And we're going to talk about how you can go about doing it if it sounds like something you want to do. And then we'll talk about some use cases and cover some things that you would want to do in the real world with this combination of technologies. So we'll start with, what is WebAssembly? Well, WebAssembly is a binary format. It is a standard that describes an executable function. You can take a high-level programming language like Go or Rust, and you can compile it to WebAssembly so that it can run in a platform and architecture independent way. Now, Go has really good cross-compilation support, so you might be wondering why you need this at all. Well, with WebAssembly, cross-compilation becomes a non-issue entirely. You can compile a single .wasm file, and that exact same file can be run on all the different platforms and architectures that you may need, like ARM, x86, mobile devices, IoT, whatever. And it can be embedded. So this is probably what's going to take up the most time during this talk, is talking about embedding WebAssembly within another application. And there's a bunch of great reasons why you'd want to do that we'll cover in a minute. And I want to touch on the difference between WebAssembly itself and the WebAssembly runtime, because these two things are often conflated and they are actually distinct. So WebAssembly itself is actually a specification that describes the binary format, whereas the WebAssembly runtime is the thing that actually executes that format. So a WebAssembly module can be run in a number of different kinds of runtimes, such as the browser, standalone WebAssembly runtimes on the server, or others, and we'll talk a little bit more about that as well. So people often ask, why would I want to use WebAssembly on the server? I thought that it was something designed for the browser. Well, you're right in that it was the first thing that WebAssembly was used for, and all of the major browsers started supporting WebAssembly quite a while ago, actually. It's one of the most common things that you probably see on the internet about WebAssembly is these, powerful browser applications that were built using WebAssembly. But people quickly realized that the WebAssembly format and WebAssembly runtimes themselves aren't intrinsically tied to the web browser, and so there are a number of use cases that we came up with that make it pretty unique. So, why does WebAssembly make sense to use outside of the browser? Well, it has a couple of really nice properties that make it useful in the web browser, because the web browser is sandboxed and all of these other things, but we find ourselves wanting to use it on the server side for a lot of the same reasons. So the three tent poles that we very often talk about when it comes to WebAssembly is performance, security, and portability. But when it comes to the server, I also like to talk about hot loading as the fourth major point as to why you would want to run WebAssembly. So to quickly touch on performance, because we're going to go into it quite a bit later, the performance of WebAssembly is often billed as near native. So this means that you can get close to, if not the same performance as a native binary compiled for the individual platforms, but you get the benefits of all the other things you see on the screen. So we've already touched on portability, so let's talk about security. Security in WebAssembly is somewhat unique in that WebAssembly is a sandboxed execution model, and it is a deny by default sandbox model. So when you are executing WebAssembly in a WebAssembly runtime, you cannot by default access anything in the outside world. You cannot make arbitrary syscalls. You cannot just willy-nilly make network connections, access the file system, things like that. The WebAssembly runtime intercepts every syscall or every host call that the module attempts to make, and the runtime is in control of what is allowed through how those syscalls are handled and all sorts of things. This has really great impacts when it comes to supply chain security because you can theoretically and actually in practice run untrusted code in a safe way as long as you're careful, and it really limits the impact of malicious code in a lot of cases. And then when we're talking about the server, I like to mention hot loading because I think it's fascinating and I found it very useful in a number of actual real-world scenarios. And so this is the ability to actually swap out a WebAssembly module without needing to stop a host process, without needing to drop network connections, without needing to stop serving HTTP requests, for example. And this is really useful because when we are deploying or rolling back code that's running in our cloud environments, we really like this property of not having to drop network connections so we can continue to serve traffic. Some of them just might have to pause for an extra beat to wait for the WebAssembly modules to reload. But actually, if you do it correctly, you can continue to serve requests with old versions and then start immediately using new versions of these WebAssembly modules to serve your requests once the swap is completed. So there's some ways to do it in a really, really nice way. So one of the comparisons that often gets made in the industry is WebAssembly versus Docker. And I want to touch on this because on the surface they do look fairly similar, but they do have some significant differences that, makes it kind of an apples versus oranges kind of scenario. But they can be used for some similar things. And people sometimes ask, will WebAssembly kill Docker? And I think the answer to that is no, because they serve different purposes. So if we look at WebAssembly, it's a compiled program. You have taken some source code and you have created what is essentially bytecode. Whereas with Docker, you are packaging a lot more than just the code of your application. You're packaging other binaries like curl, like shells. You are adding other files. You have a file system. You have user accounts. You have all these things that make it OS-like. But WebAssembly, on the other hand, is really just a single program. So you can actually think of WebAssembly as just one program that could get embedded into and run inside of a Docker container. So while the comparison on the surface does make a little bit of sense, I think in practice there's actually enough differences that these two technologies both have a place in the world and even in the future. So performance, we kind of touched on this for a quick second, but we're going to go a little bit deeper on it now. I talked about near native performance, and this is the line that we like to use when we're talking about WebAssembly, but it can actually be true, and we'll look at some performance stuff in a minute with the code. But I want to talk about what we actually mean when we say near native performance. So the term near native performance, it has a lot of undertones to it. There are a bunch of different factors that come into play when we talk about near native performance. So one thing to note is that when a WebAssembly runtime executes a WebAssembly module, it is actually doing some translation between the WebAssembly format and the platform-specific bytecode that it needs to actually execute on the machine. And so it can do this in a number of different ways, and somewhat similarly to the V8 engine, for example, it can do JIT compilation, where it is interpreting and compiling parts of the application in real time. But we can also do ahead of time compilation. So you can actually take the entire WebAssembly module and you can convert it to an x86 binary if that's the way you want to do it. And depending on which of these methods you use, and most WebAssembly runtimes will allow you to choose, you can actually get different performance characteristics. So for example, if you're using just-in-time, you will often get faster startup times, but the sustained performance over time might be less. Compared to if you use ahead-of-time compilation, your application might start up more slowly, but the performance over a sustained amount of time would likely be higher and closer to that of a native binary. So we look at different languages slightly differently when we talk about WebAssembly, because in fact, languages often need to package their own standard libraries, their own internal runtimes into these WebAssembly modules, and that can actually affect the performance of the module, especially when it comes to cold starts and quickly bringing up new instances of a WebAssembly runtime. So when we look at something like Swift, for example, Swift has a very large standard library and a very large runtime implementation, and all of that gets packaged into a WebAssembly module when you compile it from Swift. And so loading that module and doing AOT compilation, for example, is very slow. So you can actually have quite long startup times compared to the other languages when using WebAssembly, even if it's the same runtime. And then you look at something like TinyGo or Rust or AssemblyScript, they have quite small runtimes and quite small standard libraries, and so the modules are several orders of magnitude smaller after being compiled, and that translates to faster startup times. And sustained performance can actually be comparable no matter the cost of the runtime or standard library, but we will look at the exact numbers in a minute. So let's kind of summarize quickly what we saw. Why would you want to reach for WebAssembly as a tool? Well, the multi-language support is an important one. It is a format that can be compiled from multiple different programming languages, which is nice. In our open source projects, for example, you can have an application that comprises several different languages all in one, and it can seamlessly switch between them without you as the developer needing to do any special work. The WebAssembly runtime is just executing WebAssembly after all. Hot reloading, I think, is an important one to remember because you can swap out business logic, you can roll out new versions, you can roll back versions of your software in single-digit milliseconds. It's a very powerful tool for managing software deployments in large architectures. And the security model is one of the most exciting things about WebAssembly. And this is, the deny by default sandbox, the ability to more safely run untrusted code, protect yourself against supply chain attacks, and all those kinds of things is really, really attractive about WebAssembly. All right, so we're going to dive in a little bit deeper here, and we're going to look at some actual code examples. We're going to look at some of the internals of how WebAssembly interacts with the host, and we'll look at some performance. So this is a snippet of AssemblyScript. AssemblyScript is a WebAssembly native language. It is roughly based on the syntax of TypeScript, so it should be somewhat familiar to all the web developers out there, which is a really big benefit to this particular language. And as you can see, it looks fairly normal. We're not having to do anything crazy to get the benefits of WebAssembly. We are writing code at a very high level. We're not doing any low-level memory management. Things are looking fairly normal. We are making HTTP requests. We are working with JSON. All of these things are great. And I'm going to use this to illustrate the fact that WebAssembly doesn't have to be scary. You don't need to learn some crazy new language. You don't need to do low-level like C-like memory management. You can get into it fairly easily with languages that are pretty familiar to you. So flipping over to the other side, say we take that AssemblyScript code and we compile it to WebAssembly. How would we actually go about running it? Well, we have an open source package called Reactor. It's a Go library that allows you to very easily run WebAssembly modules in Go. And we provide a lot of the utilities, tools, and frameworks that you need to make this happen. So Reactor is fairly low level. It is something that you would reach for when you want to do something relatively custom. You want to run WebAssembly as part of an existing Go application, for example, and you want to be able to execute user-submitted code or hot swappable code in a very performant way. Internally, Reactor is a scheduler, so it can have many, many instances of the WebAssembly runtime instantiated all at once. It will automatically manage pools of WebAssembly instances to make sure that jobs are handled in a very efficient way. So in this particular example, what you're seeing is a WebAssembly module getting loaded, in this case from a mysterious cloud bucket, and then that WebAssembly module, which is represented by the ref variable there, gets loaded into an instance of Reactor by registering it, and then the module is executed by passing it an input. Now, something to note about WebAssembly is that the data types are very primitive, we'll say. There are not yet representations of higher level structs and strings and things like that. Currently, we're limited to things like bytes and I32s, F32s, and other fairly small, low-level variable types. Now, Reactor handles converting most of these things on your behalf. So we will manage the inputs and convert them to WebAssembly compatible memory, and then make that memory available inside of your WebAssembly module in a fairly intuitive way. So you as a developer don't need to care about some of these specifics, but in general, you are going to be passing fairly simple data types around when you're working with WebAssembly. And usually we like to say, just use JSON because it simplifies a lot of things. So when Reactor loads the WebAssembly bytes, it will create an instance with an underlying WebAssembly runtime. Reactor supports several different WebAssembly runtimes like WASMTime and WASMEdge, so you can choose which low-level WebAssembly runtime is actually executing your code. And then it makes those instances available for execution immediately. So there's nothing that you as the developer need to worry about in terms of instantiating and setting up the actual runtime or module itself. So now I want to take a look at how the WebAssembly module actually interacts with the host. And when I say host here, I mean Reactor, or the Go program that is using Reactor to run WebAssembly. So when a WebAssembly module, like the one that I showed in the last slide, makes something like an HTTP request, or tries to access a file, or open a socket, or anything like that, that request, that syscall or host call, is actually caught by the runtime, and the runtime is allowed to handle it in whatever way it likes. And in this case, with Reactor, we have added a special set of capabilities to the WebAssembly runtime that give you the common actions that you would need to build cloud applications. So making an HTTP request is a fairly common thing that needs to happen, and so we added capabilities to the WebAssembly runtime to make it happen. Now, the actual runtime that is executing the WebAssembly is actually swappable when you're using Reactor. So you can choose between WASMTime, WASMEdge, or others, and Reactor will create an abstraction over those runtimes, and they will make the exact same APIs and capabilities available no matter which one you choose. Now, what you're seeing here is actually a screenshot from the Reactor codebase itself, and it's illustrating how when the WebAssembly module makes an HTTP post request, that request is actually caught by the runtime. The runtime is able to then evaluate it, determine if it's allowed. It can do filtering, it can do security checks, and then it will actually use the Go implementation of that call to complete the request. So we're actually using the Go HTTP library and Go's amazing networking capabilities to do really efficient HTTP requests on behalf of a WebAssembly module. So there's no actual HTTP client built into the WebAssembly modules. They are simply interacting with an interface, and that interface is defined by Reactor and mounted to the WebAssembly runtime when it instantiates that module. So I wanted to show this to illustrate the fact that we are actually being very explicit about what we are allowing these WebAssembly modules to do. And it's important because we want to prevent malicious activity. We want to allow ourselves to run this, user-submitted, untrusted code and be very sure that what is actually happening in the real world is safe and there is no risk to our infrastructure or other parts of our application. All right, so we're going to dive into some code, and we're going to take a look at actually writing and running some WebAssembly. So we're actually looking at a repository here that you saw the link on the slide, github.com, Hicks, GopherCon-21. This is a very simple example of writing various languages, compiling them to WebAssembly, and then executing that WebAssembly using Reactor in a Go program. So on the side here, you'll see a number of different programming language names. Each of these is a single function that has been written to demonstrate compiling to WebAssembly, and then we are going to execute it in our main.go function. So in the effort of keeping this very simple, we're just going to be calculating factorials. It's a pretty classic way of demonstrating, the performance of something. We're going to do it with some, relatively large numbers to show that we're doing some real work here. But at the end of the day, we are going to be just comparing these different languages to see what the performance differences are between them. So I'll quickly walk you through how we set up this application. So the Reactor instance is created, and then 3 different modules are registered onto that Reactor instance. We have one for Rust, one for TinyGo, and one for AssemblyScript. And it's going to reference the .wasm files for each of those compiled functions. And then what we're going to be doing is executing that function that has been loaded with the input of 5,000. The module for each language is going to calculate the factorial of the number 5,000, and then we're going to do that 100,000 times for each of the languages. We're going to calculate the amount of time that it takes in milliseconds, and we're going to see what happens. So let's start by looking at the Rust function. This one is fairly straightforward, as they all are, and we're simply using a recursive function to calculate factorial. Nice and straightforward. So as you can see here, this is where some of that abstraction that I was talking about before takes place. So Reactor has both a host library to run WebAssembly, but we also have guest libraries, what we call the runnable SDK or the runnable API, to interface on both sides of that boundary, which we call the FFI boundary or Foreign Function Interface boundary. And these 2 libraries, the one inside of your Rust module and the one outside running that module, collaborate to manage memory and pass data types around and all that kind of stuff. So at the end of the day, what we end up with is this run function, and it takes in bytes as input and returns either bytes or an error as output. And so we're just going to be taking that 5,000 as a string that we inputted. We're going to be parsing it as an int32. We're going to calculate the factorial and then just return that as a message. Very straightforward. Now we're going to use our Subo CLI tool, which is a wrapper around the various language toolchains that you might need to work with WebAssembly. And it includes Docker images that will automatically build your code. So you don't need to install the Rust toolchain or the AssemblyScript toolchain. It will just manage that for you. So if we build the Rust runnable right here, you'll see that we are using that Docker toolchain. It's going to go in, it's going to grab the code that we've written, it's going to compile it down to WebAssembly, and then we'll be ready to go. So now that it's built that WebAssembly module, we can go ahead and run it. But I'm going to take a look at the other 2 first. So let's take a look at AssemblyScript now. There's a bunch of code that gets automatically generated that you don't need to worry about. And then there is a fairly similar looking run function that takes in bytes and returns bytes. And we're doing something very similar with a recursive factorial function. And then the last one we'll take a look at is the TinyGo version. So TinyGo, as you may know, is a variant of Go that is designed for small spaces or tiny spaces. And we use this because the WebAssembly modules generated by TinyGo are much smaller than the ones generated by the regular Go toolchain, and we actually get slightly better performance. Now I know the Go team is working very hard to have full and complete WebAssembly support, and I really look forward to the time when that is complete because I'd love to be able to use a single toolchain for everything. But for now, we use TinyGo. So once again, we're using something very similar, recursive factorial function, and we are calling it in much a similar way as the others. Now that we have all of these, we're just going to compile the other 2. So we're going to compile the TinyGo example. Which is going to download the Docker image to do so. I'm just going to run it natively. And now that we've built the TinyGo version, we are going to build the AssemblyScript version. So now we have 3 WebAssembly modules that can be executed. And we're going to go back to our main.go and we're going to actually execute them. So in this repo, there is a makefile, so you can simply execute make run, and it's going to go ahead and run that factorial function 100,000 times with the input of 5,000 for each. So as we go through here, we can see the amount of time that each of these languages is taking to calculate that information. So with Rust, about 1700 milliseconds. TinyGo, also very close to 1700 milliseconds. assembly script, 4,600 milliseconds. So you can see that there is a difference between the different languages depending on a bunch of different factors. Now, all of these are using various kinds of optimizations, and the tool chains are different, and the WebAssembly modules that they output are different because they contain different runtimes and standard libraries and all that kind of thing. But as you can see, out of the box, we have slightly different performance. And I do also want to try running with a different WebAssembly runtime under the hood. This is the exact same Reactor program, just using a slightly, using a different low-level WebAssembly runtime. And as you can see, we're getting pretty much comparable results. So the actual difference between the runtimes is fairly minimal, but the differences between the languages can actually be more pronounced. So I highly suggest you go take a look at this repository. You can try it out, and you can actually go ahead and start messing around with it yourself. All right, now getting back to the slides, we will move on from code time, and we'll talk about some use cases. So why exactly would you want to use WebAssembly to build applications? Well, there are a couple of pretty major ones, and a couple of these we as Suborbital have been working on for quite a while now. So we've been focusing on user-submitted code because we think that using WebAssembly to power plugins and user-submitted functions and modifications is a really powerful use case for the technology. But even without any of that, you still get a lot of benefits like hot reloading. So you can be writing your own code and deploying your own code, but still get the benefits of hot reloading, for example, if you allow your application to quickly load and execute new versions directly from your CI/CD system, for example. And then there's a particular use case that I think is really compelling, which is using WebAssembly for FAS, or functions as a service. And the reason why I think it's pretty compelling is because of that performance story that we talked about earlier, particularly the fast cold starts. We're finding that you can spin up WebAssembly functions in single-digit milliseconds or less. You can actually sometimes do it in microseconds because of the tiny binary size, the fact that they can be JIT or ahead of time compiled. All of these factors, if you tweak them, you can get these things starting up an order of magnitude more quickly than a container, for example. So there are a lot of use cases where you can quickly scale up and down your ability to handle traffic. You can emulate things like AWS Lambda and actually get similar or often even better performance than these, really large scale professionally developed systems just by using a different technology. And you don't have to worry about any of the inherent performance problems that come with technologies like containers or micro VMs. So I want to touch on a couple of different caveats because, WebAssembly is a young technology. It's not fully emerged, and there are some things that you need to keep in mind when you are looking to adopt it. And this starts with being very careful about WASI and capabilities. Now, what is WASI? We have never heard this term before in this talk. Well, WASI is the WebAssembly system interface. And in much the same way that Reactor adds, cloud native specific capabilities to the WebAssembly runtime, like HTTP clients and accessing databases, WASI intends to be something more similar to POSIX and giving common operating system type functions to WebAssembly modules. So accessing file systems, accessing Berkeley sockets, those kinds of things. And it's a young standard, it's still emerging, but it is already available. You can try it. The runtimes that Reactor uses under the hood all support it, so you can give it a try without changing any code. And you need to be careful with these kinds of things because if you are intentionally running user-submitted code that could potentially be malicious or mining cryptocurrency, you want to make sure that you are setting up the WebAssembly runtime in exactly the way you need and limiting those capabilities as much as you need to ensure the safety of your infrastructure. Reactor has a lot of things to help you do this. You can very granularly configure the capabilities that Reactor enables, and we make sure that you are able to keep your infrastructure and your servers safe when you are running user-submitted code. The next is multi-tenancy. Now, sometimes being a bad tenant or being a noisy neighbor is a problem when you are running even your own code, because you could accidentally introduce a problem, but especially when running untrusted code, because you could have people intentionally trying to take down your infrastructure by, running code that will bomb your CPU, take up all of your memory. So WebAssembly helps us because there are, built-in controls to limit these kinds of things, and we can do simple things like limiting memory, CPU, and execution time, but you need to be careful about these settings and just ensure that you are setting sane limits when running your user's code. Next up is data formats, and this is generally differences between programming languages. When compiling to WebAssembly, you can't always expect that everything will work perfectly. Like I said, WebAssembly is still a young ecosystem, and so there could be some compatibility differences. Doing something simple like parsing data formats can be a little bit more challenging because WebAssembly has very strict data types, and so this can cause problems when you are trying to infer data types, such as when you are parsing JSON, for example. We will look at the package ecosystem just a little bit, and the thing I want to say about it is, you can't just take any old package off of your common package registry like NPM or Cargo and expect that it will just work. Because of the way the WebAssembly sandbox is architected, because of the way that the WebAssembly modules interact with the WebAssembly runtime, code trying to make arbitrary syscalls is not going to work. The WebAssembly runtime does not conform to the Node.js API or to any other common API. It is its own set of capabilities and host calls, and just expecting any old off-the-shelf code to work is probably unrealistic at this point in the game. And so this is something to keep in mind. It can often be circumvented. You can often port, or you can often make small tweaks to make things work just as well in WebAssembly, but you do need to be a little bit cognizant and don't expect everything to work right off the bat. Next is cold starts, and we already looked at how performance can vary between different languages, and I touched on the fact that Swift, for example, has a much larger runtime and standard library than some of the others, and this can affect cold start greatly. So when you are choosing languages, either for yourself or for your users to write WebAssembly modules with, you should keep in mind that you probably want to start with something with a very small runtime, like TinyGo, Rust, or AssemblyScript. And then finally, if you are going to be allowing your users to write code that is embedded in your own architecture, I would highly suggest communicating with them, making sure that they know the capabilities, the limitations, and the expectations of what this is able to do. It's not yet a silver bullet. One day I think it will be, and we're rapidly approaching that time, but for now we still have some work to do to get it to the point where, for example, any Node.js application could run within WebAssembly. We're not there yet, but with a healthy dose of documentation, communication, and expectation settings, it's absolutely possible for everybody involved to have a really good experience. So at the end, let's summarize. We'll do a wrap up by covering the what's, whys, and hows, because that was, after all, the title of this talk. So what is WebAssembly? It's a binary format that high-level code can be compiled to in order to execute on various platforms with near-native performance and really nice security sandboxing properties. Why you would want to run it include things like hot swapping code without dropping network connections, running untrusted code, running user-submitted code, or running multiple programming languages seamlessly within the same project. And how you can go about it is by using our Reactor library. This is something that is quite mature. It's been around for a long time now, and we're really happy with the way that it turned out. You can use the runtimes themselves, you can use V8 in a web browser, but for this purposes of this talk, running WebAssembly in Go, we believe that Reactor is the best way to do so, and also the easiest. That's all for now. Thank you for listening. I hope you learned a little bit about WebAssembly, and I hope it sparked some ideas about how you could use WebAssembly in your own Go programs. Please do feel free to reach out to us. We're happy to answer questions, help you get started, whether it's with Reactor or not. We love to help with anything to do with WebAssembly. We have some very seasoned WebAssembly veterans on our team, and we're happy to help in any way that we can. Thank you very much.
At the end of the day, it's being proud of the work that you do and building cool projects with people that you enjoy spending time with.
Thanks so much for that fascinating talk about WebAssembly in Go.
In Go.
Not Rust.
Yeah.
So I've made some promises behind the scenes that I would do WebAssembly in Go now.
that. You sound really excited. You're just ecstatic.
Yeah.
No, I mean, I really am going to start doing that stuff. But yeah, it's really fascinating to see how much this has come along in Go. Rust has typically been the language that most people are writing WebAssembly in, so I'm great to see us make strides.
Yeah, I mean, we've seen novel use cases of Go almost all day now, and this is just added to the list, right?
Yeah, it goes better than Rust. Just
yeah. Well, we don't have a Rust channel, but we do have a dad jokes channel.
Yes.
Now.
And there's already some premium content in there.
Am I missing out?
You're missing out.
You are all missing out if you're not in the dad jokes channel. Like, that's just, I didn't even know there was content yet because we just created it. So that's awesome to hear, for sure. Yeah. Yeah. So we've got a couple of virtual sessions, and focus in here because I'm your guy. If you want virtual sessions, I'm the guy. All right. Here we go. You ready? Everybody ready?
Yeah. Ready.
All right. So we've got Lightstep coming at you with some distributed tracing office hours. Distributed tracing is pretty interesting, I think. Not as new on the scene anymore, I guess. It's been a couple of years since it really kind of hit us all.
Pretty hard. Yeah, I took it pretty hard. Yeah.
Yeah.
It hit. Yeah.
Hit you real hard. It came in with some power, hit Johnny really hard, and Lightstep is here to talk to you about it in their office hours. Also, Buff, their office hours are continuing. They are, contrary to popular belief, not a weightlifting company. They do a lot of stuff with protobufs, hence the name. Protobufs is also not a new technology, really. A lot of us have probably heard of them, heard of protobufs, that is. But Buff is doing a lot of new stuff with protobufs, and they're here to talk through all of that.
Yeah, and if you're watching us through any of the other platforms, if you want to access the virtual meeting spaces with the sponsors, you do have to be registered. If you're having trouble actually getting in, if you are registered, make sure you're not running like an ad blocker, Pi-hole, or running through Brave. For whatever reason, these things want you to look at ads. So.
Yeah, it's all written in Rust. It's really secure, so they don't let you look at ads because Rust.
Aaron, I thought we talked about this, bro. Like, what are you doing, man?
Oh, and also in our last segment, I had mentioned that the Gopher Say was tomorrow. There's a different Go Time segment tomorrow. That's the AMA with the Go team. The Gopher Say contest will be Friday, but the request still stands. Let's get in a bunch of submissions so that we can make that a really fun game and troll them as hard as possible.
Yes, please do.
Oh, also, I checked the stats on our Gopher Academy YouTube. You've had hours. We haven't even got one of those 75,000 subscribers we need for my plaque.
Come on, let's get on top. I mean, must you write this in Rust for it to be like?
That's it. I think if this was RustCon, it would have happened.
I think we're being punished for pushing Rust so much. Actually, I think that's what's happening here.
Oh man.
So who do we have up next?
So up next we have Mr. Daniel Selans. So let me tell you, Daniel and really a few of us were just talking shop yesterday, and this guy is passionate about distributed systems and messaging and event-driven systems and the like. And
do you think he was hit hard by distributed tracing?
I would have to say. I mean, yeah, we're gonna find out how hard he was hit, But yeah, for sure. I mean, he's the co-founder of a company. I'm so tempted to call your company Batshit because it's batch.sh. That's the name of the company. But yeah, I will hold that. I will hold that in. No, we're in good terms.
I
it's all
think
good.
you already said.
I think I might have already jumped the gun on that one.
How do we feel about maybe asking him to change the name of the company just for you?
No, but it's such a cool. I do hope you own the batch.sh domain name, though, Daniel, because that would be awesome if you did. And you're nodding, so I'm gonna say yes, you do. So yeah, you're gonna talk to us about reliability Nirvana. What is this place? Like, my interest is piqued, man. Like, tell us about reliability Nirvana. Take it away, Daniel.
Thank you very much. That was an incredible intro, as a side note. I am not that amazing, but it is true. I am quite passionate about distributed systems and distributed tracing, and all things that are related to essentially high throughput stuff. I do own batch.sh as well, only because batch.io is not available. And batch.com costs too much money. So, all right, let's get into this. So, the first thing I want to begin with is I want to say a big thank you to the GopherCon organizers for putting all this stuff together. That's super amazing, and for really giving me a platform to talk about this stuff because I am super passionate about it, and I think it's really important. So thank you. I've been trying to get into GopherCon for a long time to actually have the chance to present about stuff, and now on the 5th year, I think I finally got in. So yes, I did this. So that means that you can do it too. So with that said, let's jump right into this. So the obligatory "Who am I?" slide that everyone has. So first things first, I am from Portland, Oregon, a sunny, beautiful Portland, Oregon. It's not sunny. Side note. I have been working in the backend for about 15 years, give or take. I've been writing Go for about 6 years. I've been really lucky to have the chance to just work in Go pretty much the last 5+ years and barely touch any other languages. It's really cool. I really like working on distributed systems, and I've spent a lot of time at data centers. I've been at New Relic, Envision, DigitalOcean, Community, which is a startup that deals with SMS stuff. And most recently, I co-founded my own company called batch.sh, which focuses on essentially observing data streams. That's really what it's about. And like streams of data that may appear on various complex message buses and so on. And a cool fact is that we managed to get into YC, which is pretty awesome. Kind of came out of nowhere. And a final tidbit is that I am actually from Latvia. So now you can say that you know somebody that's a distributed systems engineer that is very cold, by the way, just like it is in Latvia. All right, cool. Let's get started. So I'm going to start with a small disclaimer here. So this is totally not a hypothetical talk. There's really no theory in this. This is about stuff that I have done in production. It's real, and it's stuff that I am doing right now in production. So that's something you can take away from that. The other part is that I'm going to try to keep it real, as in just mention the things that are actually hard, the things that are actually not so hard, and I'll put it right out there. And then ultimately, I really want to make sure that you level up after hearing my talk. In general, there's nothing worse than, I think, listening or having somebody talk at you for 45 minutes and you having to walk away. Thank you. You having to walk away with not having learned anything at all. So the goal here is that you walk away with something. So let's start with, what are we trying to solve? Well, what we're trying to do is we're trying to take reliability to the next level. And by next level, I mean how to improve a system that is already pretty good, right? So if we look into that, the first thing that might come to mind is, of course, utilizing microservices. So you are going to split up your monolith. You realize that, like, oh, it's much easier to actually manage this entire beast if you have microservices. Great. If you have microservices, you want to be able to actually reproduce them somehow and deploy them and do something with them. So you would probably utilize containers and some sort of orchestration like Kubernetes and so on. Great, makes sense. Then you would actually want to make sure that you're able to deploy this stuff in a reliable fashion, right? So you would use blue-green deploys or canary deploys or some sort of another deployment strategy. You also might utilize a service mesh. And the service mesh is going to enable your services to talk to each other easily and be able to discover your services easily. And then you might also add circuit breakers, basically patterns that will ensure that your code is able to deal with network hiccups and so on and so on. So you might be saying from all of this, like, first off, is this the talk where this dude is just going to talk about all these things again? And no, I am not going to talk about all those things again. I am actually going to say that we could just do better than that, right? All those things right there are already good. It's just the fact that we could do a little bit better. We can just add some things and just adjust it a little bit. And I would even go so far as to say that we could probably remove some of those things as well from that entire stack, which would reduce our complexity in exchange for some complexity. So the thing that I'm talking about is event-driven and the concepts of event-driven. So since everybody's super smart and everybody is able to pick this up really quick, I'm going to try to do this in about like 5 minutes or so. Has never worked out to be 5 minutes, but I'm going to try anyway. So event-driven is an architectural and system design pattern. Think basically like a microservices pattern, right? In event-driven consists basically of 3 actions, which is emitting something, consuming something, and reacting to something. And you might actually not react to anything like after you even consume it. So it doesn't necessarily mean that if one of those happens, then all the other 3 actions have to happen as well. Now, I mentioned, I say the word event, and really it's synonymous with a message, and that is synonymous with essentially a unit of work. I think it was Honeycomb, speaking of distributed tracing. Honeycomb wrote an article, I think like 2 or 3 years ago, and it's super awesome. It talks about what is the difference between a log entry and an event. And the thing that it came down to was that essentially an event is actionable, right? And they define it as a unit of work. And that's all that it is about. It's something that you can actually guarantee being able to perform an action off of, right? Where a log entry might be more of like an informational thing. So the event must be, or the events and where they're coming from must be the source of truth. All events must be communicated through an event bus or a message bus. And that could be, the definition of an event bus is really kind of loose. We could be even using Redis. It might not be the best choice, but the point is some sort of a method to actually send messages through. All the services must be idempotent. And that's really just a big word for the fact that we just want to make sure that that our service is able to deal with duplicate events. And we want to make sure that our service is able to deal with out-of-order events. Which is, if you add state into all of this, it's not really that terribly complicated. So, and then we also must be okay with eventual consistency. This is kind of a big one, because getting everybody to be on the same page and agree that it's okay, that we cannot guarantee consistency, it's kind of a big deal. The whole point of that really is, right, is that you are trusting that the system will eventually become consistent enough for everything to operate correctly. The most important part of all this is that your single service, I think from all of this stuff, all of these points are important, but the one most important point is that your service should only care about its own state and nobody else's. That's it. It shouldn't even know about anything else that is happening on the system at all. I think that's a really important building block of this entire thing. All the stuff is quite easily achievable, but the moment that you violate this rule, you kind of lose the benefits of actually even doing anything event-driven to begin with. So, so what are the components in event-driven? So of course you have an event bus. That's where all the messages are going to be passing through. I would suggest in this case for an event bus to use RabbitMQ. It is not written in Go, it is written in Erlang. However, it is still very, very good. And specifically, it has an extremely versatile routing config, meaning that instead of having to update your code to implement some sort of functionality, you can just utilize stuff that's already built into RabbitMQ. It is medium fast. It does about 20,000 messages a second, about 2 to 4 kilobytes in size, I think. And it is extremely reliable. I have used RabbitMQ for many years now, and there is practically no babysitting associated with it. Some cons about RabbitMQ, though, are that it is not distributed, and I don't think it ever will be. but it does have various failover options and high availability options to a point where it's okay to have this idea of introducing essentially a single point of failure. But that single point of failure is extremely unlikely to actually fail, which are generally the famous last words, but you know, for the most part, it's okay. So the second part is caching in a config layer, and really it should be also kind of like a state layer. And this is a piece that you never hear folks talk about at all when we're talking about event-driven or the various like umbrella architectures of event-driven. This is what I think enables building really stable and really scalable systems to begin with. So a config layer is essentially some sort of a way for your service to retain its state and be able to get its state back after the service has been restarted or it comes back from a crash or whatever other sort of thing. And that config layer, there's still all the components that we're talking about here, they need to be centralized dependencies. And so you want them to be extremely reliable, right? So in this particular case, I think there is really one massive contender, and that is etcd. And etcd is distributed. It's a distributed key value store. And the biggest thing about it is that, or the best thing about it is really, is that it's extremely rock solid. It just works. I have used etcd for an extremely long time, and I've had clusters of sizes of 5 to 9, I think like 11 nodes or so, and with links between all the cluster nodes having an excess of 200 milliseconds of latency or so, and it still survives without a problem. The other part is that, yeah, it's written in Go. It is used by Kubernetes right now. It has been used now for quite a while. It is medium fast, meaning that it can do about 20,000 messages a second as well. But again, the most important part of it is the fact that it's so ridiculously stable. So with that said, that's actually all the components that you need to build an event-driven system. It might not be amazing, but it's going to be enough. So with that said, there are some bonuses that you can add into all this stuff as well. So you can have a long-term event storage, and that's essentially a way for you to say, I would like to see keep a history of every single event that has ever happened on my entire system. And for that, you would need to put it into something, right? Like store all of these events. And unless you're running your own object store and you're comfortable with running Ceph, or you're comfortable with running Minio or something like that, I would just suggest for the mere mortals to use S3 because it's really cheap. It is quite fast. It is quite reliable as well. There's really no reason not to use it. And on top of it, it gets exposed in so many different ways. You can use Athena to access it and so on. But of course, you also need some way to actually get all of these events into the object store in the first place. So you would have to potentially build some sort of a way to, like some sort of a method to archive all of these events that are coming there. So you could use all kinds of stuff. You could use Debezium, you could use Spark, some sort of Spark jobs, or you could just build something. And in that case, I would totally suggest to just build something. It is much easier because you could just, you're probably going to have some sort of custom logic in there that you're going to want to basically expand this thing. And generally, it is pretty simple to begin with. So I have now worked with practically, I think, every supported message broker library in Go, and they're all pretty good. They all work really well. So there's really no reason to say like, oh, I'm not going to do this in Go. I'm going to do this in Java or something like that instead. You don't really need to do that. There are plenty of client-side libraries that do all this stuff. So cool. Congratulations. You have now learned event-driven. That was not 5 minutes. I'm pretty sure it's probably more than that. So. All right, so how does all of this actually translate to improve reliability? Well, the first thing here is that we are talking about essentially async. Everything is async. Everything is becoming async at that point. So what you're gaining by just doing things the event-driven way, you gain automatic recovery. That's actually built into your code purely based on the fact that you have written a consumer that is going to consume your messages. That means that if your service is down at the time, when it comes back, it is going to just automatically consume all the messages that it has missed. That's it. It's as simple as that. It doesn't know that there are messages that are missed. It doesn't know that it was down. You haven't added any sort of additional logic into your code or anything like that to actually know that, oh, I need to recover now. No, that this all comes by default, just from the fact that, like, well, your service came back up and now it's consuming everything. So the second thing is that your failure domain has now been reduced dramatically. You now have a situation where, if we look back at one of the previous slides where we're talking about the service should only care about itself and nobody else, that means that your service is no longer talking to service B, C, D, or E, and so on in your microservice stack. You only care about yourself. That means that you have practically no dependencies except these centralized dependencies, right? Like of RabbitMQ and etcd or whatever. So basically, yeah, less things to fail. There's true service autonomy, the fact that from an organizational point of view, you're no longer depending on another team, and thus the reliability of team B or C does not impact you in any way, shape, or form, right? Just because service C has a poor response time or something like that, your SLAs are not going to be affected by it. There's also going to be less infrastructure. So when we're talking about a service mesh, specifically for the fact of to add the functionality of being able to discover where all these other services are at, you no longer care about other services. You no longer talk to them. You're just talking to an event bus, so you don't actually have a need to discover anything at all. And on the same page, you no longer need to actually even care about some sort of encryption methods to enable talking between services. That stuff is gone. You no longer need it, really. So we could just take that out. And finally, the biggest one of all of these is the fact that you have a dramatically lower attack surface, because now you have the ability to basically put in an ACL, which is going into your network stack or whatever, that says that nothing can talk to anything. You could basically put in a deny all for all outbound traffic that is on for your internal network, for your even external network, and say that, well, there are only two places that the services can talk to. That is the event bus, and that is the caching layer of etcd or whatever else. And I think that's amazing. That's what I have done for quite a while now. And it's just an easy checkbox that you can get, right? To say like, yep, we are significantly more secure because we do not have to punch holes really ever to say like, oh, service A actually can talk to service, G or whatever. So let's talk about what this actually looks like. As in, we're going to look at some code. Obviously, this is not production-ready code, but it generally gives you an idea as to like what this will actually look like, and it'll prepare you for when we do a brief demo of some of these concepts to begin with. So from the top, what we're looking at is we are going to be setting up an event bus, and the event bus is going to return an instance of the event bus. In this case, it's going to be Rabbit. You can see right here that there's already an import there. After that is done, all the event bus, by the way, all that it is that we're just defining where we're going to connect to and what kind of messages we care about. After we receive an event bus, we're going to call on the consume method, and we're going to pass to it a consumer func. And consumer func is essentially going to be executed every single time that a message actually comes in, or comes into RabbitMQ, and RabbitMQ passes it to our service. Finally, we're also going to run a producer in here as well, which is essentially just going to periodically produce some messages. So what does setup event bus look like? Pretty simple. We don't have to go into each one of these, but the idea is that we're using this Rabbit library. It's a wrapper that we wrote for RabbitMQ. It actually wraps the AMQP, I think it was Stredway? Yeah, Stredway AMQP. It wraps that library and adds reconnect support and some other quality of life things. So we're using that to connect to localhost, and we're basically saying, because of these binding keys, we're saying that if any producer writes any sort of messages to the events exchange, then forward a copy of it to my queue. And that basically means, right, that because we have a consumer set up here, that RabbitMQ is going to forward a message when it comes into my queue, which is ultimately going to fire this consumer func, because we have that here. So what does the consumer func look like? Consumer func receives a copy of AMQP delivery. AMQP delivery has a bunch of different metadata about the message itself. It'll have the body, it'll have various headers, all kinds of things related specifically to RabbitMQ. The thing that we care about the most, though, is the body, right? The actual payload of what was sent in by somebody that produced a message. So in this case, we're going to assume that the body is going to contain a map string interface. And all we're doing is we're just essentially unmarshalling that, JSON unmarshalling that body to that. Then we're we're just checking to see if the type key exists in this map that we unmarshaled. And if it does, then we're going to perform a switch on the message type and see if it is new order. If it is new order, then we execute some function somewhere to do something with the contents that we unmarshaled. In this case, process new order, we don't really care what it's even doing. The point is that now it has the chance to do something with it because it has identified what kind of a message it is. Finally, there's the producer. So the producer, all it's really doing here is that it's running in a forever for loop. It is generating some JSON with a random UUID for the user ID. And then the only line that matters here, really, it's not really even complex, but the only line that matters is the publish, right? And all the publish is doing is just writing to this routing key that it doesn't matter what routing key we're even using, foo or whatever, because when we configured the event bus in one of the previous slides, right, in here, because we have a pound here, it means basically it's a wildcard. So we can write any sort of a routing key and it's going to end up going to RabbitMQ and have RabbitMQ forward it over to my queue instead. So, fantastic. So let's do, now that we generally understand what it's supposed to look like, let's do a demo of building a fairly simplistic event-driven system. I have all this code available on GopherCon 2021 under the batchcorp.org. It's all in there, and there's a pretty decent README explaining all of this stuff. So without further ado, you now have the ability to look at this mesmerizing, incredible diagram. And what you can tell here is that I got carried away with an Apple Pen with an iPad. It is pretty sweet. And I started enjoying coloring things. So once you get past that point, what it's really showing you here is that what we're going to do is we have two services. We have the orders and the notifications service. And those are going to be listening to RabbitMQ. There's going to be a producer, some sort of a third party that is going to produce an event. And once it goes into RabbitMQ, the important thing here is the producer is not talking to notifications or to the order service. The producer is going to be talking just to RabbitMQ. RabbitMQ is going to forward the new order message to orders and to notifications, and the two services are going to do something based on that message. In this case, it says, hypothetically, that orders is going to be talking to a shipping service, and notifications is going to talk to Slack to send some sort of a notification and so on. For our case, there's really no reason for us to talk to these outside dependencies. We're just simply going to send some sort of metrics out. That's it, just to be able to visualize the fact that something is happening. So also, the way I've set up the demo is that so that we do not have two separate code bases altogether for the services, we are just going to pass in an envar, which is going to specify the name of the service to begin with. So that way we can just run an arbitrary number of different services, so to speak, just by providing it a different name. So the first example is going to be a no thrills example. So let's just do all of that really quick. So I am going to go into here, and this is our code here. So I'm already in GopherCon. There's a Docker compose file. And you'll see that a Docker compose has RabbitMQ, etcd, and it has a Graphite statsd setup. We're not going to be using etcd yet in this first case of the demo. We're just going to be using RabbitMQ, but we will be using Graphite statsd. All it is just basically a combo Docker container that has a statsd server, which is meant for aggregating metrics, and Graphite to actually visualize all that stuff. So you can basically think of it as a simpler Grafana plus InfluxDB. That's essentially all it is. So, all right, so we're going to start that up really quick. Let's do that. Let's do that really quick. If I had an M1, maybe this would be a little bit faster, but it is what it is. All right. Do that. And while that stuff is starting up, we can already start looking through some of this code as well. So this is the GopherCon 2021 repo. We are under the service directory right here. Okay, so let's start looking through main. It will look fairly familiar, right, to the previous example that I was giving. So the only thing here is that we are going to be looking for the service name envar. The service name, if it's not provided to us, then we're just going to bail out, right? And instead of just setting up the event bus, we're just going to have something a little bit more generic. We're going to be setting up all of our dependencies. So we'll set up the dependencies. After we set up the dependencies, we're going to do something similar to what we saw in the screenshots of the code, which is we're going to launch off of the dependencies. We already can tell that dependencies is going to create an event bus. So off of the event bus that's in dependencies, we're going to launch a consumer in a dedicated Go routine. And we're going to tell it to do the same thing, execute something, or execute this particular function right here, the consumer func. So, and the final part is just a forever loop, right? Or a way to ensure that main doesn't really exit. That's all it is. So, so let's take a look at setup dependencies really fast. So setup dependencies, we instantiate deps. We're going to create an event bus, same thing as before. We're going to be listening to basically, or we're going to listen for anything that is written to the exchange called events, and RabbitMQ then is going to forward that to to a queue that we registered called service name -q. So in this case, orders -q and notifications -q. Great. After that is done, we instantiate a statsd client. That's essentially the client that we're going to be using to bump basically some metrics. Have to do this sort of a thing purely for the demo, really, because the metrics do not show up immediately in Graphite. So it's easier to just simply say like, all right, here, there's some in here. So we're going to do it a little bit earlier. And finally, we're creating state. But because, again, the first part of the demo doesn't actually utilize state, and we're just going to skip over this and what it's actually doing. It does get instantiated, but it gets instantiated with a no-op state. So even when it gets called, it's not really going to do anything at all. So back to main. So in main, then, the first thing that we do is we actually start up consumer func, or the next thing after setting up the dependencies, we say that, like, okay, you need to execute consumer func. So what is consumer func? Again, very similar to what we had before, but instead of just unmarshalling it into a map string interface, now we actually have an event structure for it. So there's some sort of an envelope for the sort of event that we are expecting. Now, in many cases, this could be protobuf, this could be Avro, this could be all kinds of encodings. It could be JSON. It could be really anything. In this case, for the demo, we're just assuming that it's going to be JSON. And the JSON is going to contain an ID, it's going to contain a type, and it's going to have args. The message type is really defined right there as a string, and there are a couple of message types, which is new order and band user. Same thing as before, we're going to unmarshal it, and then we're going to do a switch check on it to see if it's in new order. If it is in new order, we're going to execute process order. So what does process order do? We do not care about what it's doing with this state stuff because, again, we're not making use of state yet. So it doesn't really matter. We can completely ignore it. The thing we should not ignore, though, is this is the part actually that is this is really the magic of what's happening here, is that we're just going to bump a metric. That's essentially it via our statsd client, and the metric name is going to be service name new order OK. That's it. After that, well, we do add this thing into state, but again, because we're not using state yet in this first example, it's going to be a no-op and it doesn't really matter. So let's start up these services. We're going to need 2 of them, right? So let's start up this first one. let's go into here. It's going to be service name equals to, service name is orders. I cannot type because it's really cold in here. Make, no, make. All right, that's one of them. And let's do the second one as well. GopherCon. And service name equals to, this is going to be the notification service. And let's just run this thing. Fantastic. Now that it's running, let's go over to Graphite. We should have it running as well. So let's take a look at Docker, what's running in here. So there's RabbitMQ running, etcd is running, and Graphite is running as well. So we should be able to just go to that really quick and just see that it is available. So let's take a look at this. We're just going to go to localhost and take a look at the metrics that we have in here. So we have four metrics rather. So the notifications metric is here. We're going to want to see that. We're going to want to see the order, the orders, metric as well. Let's change this view to have the last 5 minutes. And just to ensure that we actually have, that we can see this stuff pretty decently, let's take a look at, let's change this to a stacked mode as well. Okay, cool. So now we're finally going to write an event. We're going to be the producer. I'm going to use a CLI tool called Plumber. It's a CLI utility that we wrote ourselves, for ourselves really. And it's essentially like a curl that is used for being able to read and write to various message buses. So if you want to write to Kafka, or if you want to write to Rabbit or Nats or whatever, it doesn't really matter. And it supports protobuf. Supports Avro, flat buffer, all kinds of other stuff. So that's what we're going to use for the producer. So that's what we're going to do. So we're going to use plumber write. We're going to say it's going to be written to Rabbit. We do not have to specify the address because it's going to localhost anyways, but we will have to specify the exchange, which is going to be events. We're going to say that input is going to be, let's see, we know that there's got to be a type in there. So it's going to be new order. All right, and I think it had an ID as well in there, so let's just call it 1, 2, 3. All right, and we're going to write it to a routing, or using a routing key called foo, because again, it doesn't really matter. It could be GopherCon for all we care about. All right, so let's do that. Let's submit this message, and we can see that, great, these services automatically responded to them, or they picked up the messages because RabbitMQ forwarded them over to their queue. So if we go here and we perform a refresh, we can immediately see that, okay, cool, these messages came in. So similarly, if we were to do this a couple of times, if we were to send a couple of these messages, or a few of these messages to it, all of them are going to come through. Fantastic. So if we go back to this, and we would say now that we want to have, if we want to improve this a little bit, well, do we need to do anything actually? And the answer is really no. If we want to add some sort of recovery to all of this, the recovery stuff is already built in, right? So that means that we could, at this point in time, we could just simply take down one of these services. So let's say we'll take down the notification service. And if we emit some messages to it, naturally what's going to happen is that, hold on, silly keys, there we go. If we emit some additional messages to it, the order service is going to pick it up, right? And the notification service is not going to see it. That's why we see only that the order service is right here. So, but the only thing what we need to do in order for the notification services to recover is to simply start up. And we haven't actually added any code for recovery or anything like that. We just simply need to just start it back up. So let's do that. If we just simply start it again, the first thing that it's going to do is that it will just process all the messages because it's essentially a consumer and all those messages are sitting in its queue. So if we were to just look at this again and refresh it, there is a notification service. So by doing basically nothing, we have managed to implement automatic recovery into this entire thing. So the final part, though, is that like we don't actually have a fully well-designed event-driven system yet. For it to become or get to the next level, really, we need to have some sort of state. So at this point, we're going to be introducing etcd as well. etcd and some sort of localized state. So what that is going to look like, let's just look through code really quick on what it all means. So if we look in here, the setup dependencies, one of the parts that we do is that we instantiate new state, and we pass it the service name. Cool. So if we go in here, we can see immediately that we need to pass the enable state envar to ensure that it doesn't create a no-op entry of new state. So one of the first things that we do is we create an etcd client. This is fairly standard code for just talking to etcd, essentially. Then we're going to instantiate state, and we're going to pass the etcd client, and we're going to instantiate a couple of data structures as well. These, like the entire purpose of the state package is essentially to provide some way for you to keep state in memory and be able to periodically flush it to somewhere. And the reason you're flushing it to somewhere is so that you can actually, on startup, read all that stuff and, well, populate your internal cache and memory. That's all it is. So that is the reason why we're seeing the cache data structure and the flush data structure. Obviously, there's some mutexes in here as well because there's probably Go routines involved that are going to be reading from the same place. So mutexes are going to be necessary. So the first thing that we do after instantiating state is that we import all the cache. That is the piece that I was saying that after we have after the service starts up, the first thing that it should do is it should go out to etcd and say, hey, tell me everything that you know about, like that you know about me. And you're getting all the information. So if we look at that, import cache, all it's doing is it's performing a recursive, with prefixes, essentially a recursive lookup for anything under that prefix to give you all the data. So in this case, we're going to go through the response and we're going to populate our cache with all the message IDs that we've seen in the past, right? If we go back to here, after that, we will start a flusher. And the flusher is also really simple. The flusher is simply a Go routine that gets executed, and it has a ticker that runs every second. Every second that it runs is going to go through the flush data structure, and it's going to flush it to, or it's going to put basically something in etcd. That's all it's doing, and then it's going to delete the entry from flush, so it knows that it doesn't have to flush anything anymore. This is being used. The flush data structure is being used when you perform an add, like when you're adding something into state. It's going to put it into the local in-memory cache, and at the same time, it's also going to put it into the flush data structure too, and so that basically the flusher can get rid of it. So what you end up with in the end then is that in main, finally, when you get to the consumer function, and we're processing the order, the first thing that we will do once we receive some sort of an event is we're going to see and we're going to check to see if we know anything about this ID of this event. And what it's going to be doing is it's just going to go into state and say like, do we know about this ID? And you know that even if you crash or something happens to you, that data is going to be in etcd no matter what. Right? It's already going to be there. So by the time that another service comes back up, its cache is going to be populated with everything that was already there. And if it is not in there, if it is not actually in our cache, then we're going to bump this metric again, and we're also going to add it into our state so that the next time that the request comes through, then it's most definitely going to hit this part right here. So what we can see here is that if we are aware of this ID, then we're going to bump a different metric, which is going to be new order skipped, right, based on the service name. So what does this all look like if we are just going to start up these services right here? So if we do, I do not want to type this again. So That is the, come on. Fine, I'll type it again. So that's the order service. And we will also need to do enable state state equals to true. Great, and we're going to do this one too, and it's going to say enable state equals to true. All right, now we have both of these running. We can see that state tracking was enabled as well. So now what happens is that if we're going to execute this and we take a look over here, what we'll see is that great, both of them have received it, both of them have actually done something with this metric, or both of them have done something with this message. So if we were to do it again, what we're going to see now is that if we just need to also graph these other metrics as well, new order skipped, and new order skipped. We can see that the next message was automatically rejected, or in this case, it was we bumped this other metric, right? Because no matter how many we're going to send, it's basically not going to reprocess them again because it already knows this ID in the first place, right? And because of the stuff that we added into etcd, we can now basically shut down both of these services, start them back up, and do the same thing again. And the first thing that's going to happen is that it's going to see that this message has been already checked or has been already processed, right? So there's basically no green or blue in there at all. Cool. So that right there concludes the third part of the demo. So let's continue this stuff. So I'll briefly talk about the libraries that you just saw in here, the stuff that I think is super useful, really. So for RabbitMQ, there's of course the Treadway AMQP library. So it is super solid, and we just wanted to have some sort of a way to put everything that's in that library and make it just a little bit easier to utilize. So things like automatic reconnects, creating consumers, creating publishers, all that sort of stuff. We just wanted to make it a little bit easier. For Kafka, even though there is no Kafka demoed here, I figured that it's a good idea to actually talk about Kafka as well. For Kafka, there are two big libraries that are available. It is the Sarama library and the Segment.io library. And both of them are really good at specific things, meaning that for instance, the Sarama library is really good at managing Kafka or performing tasks that are related to management. So things like, for instance, topic control. On the other hand, the Segment.io library is really good at creating high throughput consumers and producers, and it works really well. We need both of those things, so we created another wrapper called KNG, and that's what we use at our company. Finally, next is etcd. etcd is the standard client for etcd. It is fantastic. It works really, really great. Something I should have probably mentioned on here as well is that if you're doing event-driven, you're probably doing a lot of async, and if you're doing async, you will want to have distributed locks or something like distributed mutexes. And the etcd client provides an extra concurrency package that has things for creating distributed locks, and that is super awesome because don't really want to implement it yourself. And because etcd is based on Raft, you can essentially piggyback off of that. Then for CLI debug stuff, you can totally use Plumber. I think it works fantastic for that. That's the reason we wrote it. We wrote it for ourselves to be able to work with event-driven systems a little bit easier. And also because we utilize Rabbit and Kafka at the same time for our entire system. So for UI debug, again, there's no Kafka in the demo, but CoughdRop is essentially a web-based UI for Kafka for being able to view topic contents, for being able to manage topics, like meaning add them, delete them, that sort of a thing. There's also etcd Manager. It's a fairly old project at this point, but it works really remarkably well. It's also a web-based UI for etcd, because otherwise you'd have to use a CLI to actually manage all your keys and so on. And again, something that I did not even talk about during this talk is gRPC. but I figured that it's worth mentioning as well. This is basically like Postman, but for gRPC, and it's super awesome. It works really, really well. So for local metrics, something that you probably saw in the demo is that there's statsd in Graphite, which is essentially like an influx plus Grafana, except significantly lighter and way less powerful as well. But for just being able to quickly show metrics and be able to do something with them, I think it's fantastic. And finally, there's an example service and a template that that my team, everyone uses for all of our services. It has support for Kafka, Rabbit, etcd. It has all the caching, state stuff already built into it. It's fully tested. It has Docker support, and it has I might say, a very beautiful makefile that has an awesome help output. So we use this for all of our services. We have about 20, probably 25 services or so running in production, and every single one of them is based off of this template. And we constantly keep it updated and so on as well. So that is probably the best example of an event-driven application you can go with. So really quick, let's talk about reality. So to do event-driven, I guess this is more like the hard parts really about event-driven and what makes it hard is that, so first is you need to understand your message bus tech really, really well. You need to get everybody to be on board, and that means that you're going to be doing a lot of convincing. You're going to need to convince your leadership, your architecture teams, your engineering in general. You're going to be responsible for essentially evangelizing this entire concept as to like why this needs to be the next way to do things. You're going to be writing lots of example code, all kinds of flows, docs, and so on. You will need to accept that the event bus is your source of truth. So, of course, it means that it doesn't mean necessarily that the event bus must be the exact place where data originates. Actually, it still can be a database. But the point is that once an event actually goes on the event bus, at that point it becomes the source of truth. Actually, you need to embrace eventual consistency. You need to embrace and fully understand how to implement idempotency. And as a side note, instead of leaving it to all the developers to do on their own, you should probably provide some sort of a boilerplate method to how to do idempotency, or how to implement it. And that's where the etcd stuff comes in with some sort of state management functionality. You can most definitely anticipate more complex debug because things like distributed tracing are not entirely going to work. You're going to have to do some greenfield implementation yourself, right? Meaning that you're going to have to add something on top of events to include this information. You can most definitely anticipate writing more complex Go. And then I specifically added a red arrow here because by far all these other ones pale, I think, in comparison to getting everybody on board. It is totally an organizational, potentially partly political part that you need to get everybody to agree that this is the way to do things from here on out. And that is not necessarily easy because, especially depending on the size of your organization and so on. So let's talk about the reality of Go and what does it actually look like in Go. So if you haven't done Go routines, you will most definitely have to do Go routines because you're doing things asynchronously. So you're going to want to make use of, well, pretty much like the most well-known feature of Go, which is you're going to launch Go routines. You're also going to want to learn, you're going to want to know how to actually share your workloads. And you would utilize, wait groups for this, you'd utilize channels, all that sort of stuff. You'll also want to control your Go routines, like meaning the life cycle of a Go routine, be able to shut it down, get it to sleep, get it to not do anything, that sort of a thing. You're going to make use of locks and mutexes, that is for sure. In most cases, localized locks are going to be fine. In some smaller cases, you're going to want to have a distributed lock. For that particular case, having an etcd lock or having a mechanism in etcd to perform locks is super awesome. you're going to want to be comfortable working with channels. That's a really big thing. Understanding the reason of why you would want to use a buffered channel somewhere and how is it going to affect performance versus why you'd want to use an unbuffered channel somewhere. Select is a big one, right? For select, you're going to want to care about things like how do you perform a blocking select or a blocking read from a channel, or how do you perform a non-blocking read from a channel, and why is it a good idea or a bad idea in a particular case. And then tickers and timers. Essentially, we're talking about time.sleep. It happens all over the place, even though it sounds really bad, like a go-to. It's basically one of your weapons. Of course, there's tickers and timers themselves as well, but the thing is that, yeah, don't be ashamed in using that time.sleep if you have to. So I think the most important thing from all of these, though, is like all of them are quite important, but the one thing that I continuously still run into over and over is that I wish that I made use of context.context somewhere, because at some point in time you decide that, oh, you know what, I want to actually instrument this function and get some sort of metrics for it or whatever else, and you had to go back, add context all over the place, and it's just a pain, really. So it's much nicer to not have to do any of that stuff. So who should be trying event-driven? So the cheap answer for that, kind of a cop-out answer, I guess, is the fact that anybody that's okay with eventual consistency. But I think the answer can go significantly deeper. So I think anybody that's doing already handling async workloads, that's a big one. Anybody that's dealing with high throughput, and that means like high throughput as in resources or bandwidth. Anybody is dealing with big data. In big data, you're doing so much async to begin with. You have to do batched work to begin with, that it just simply makes sense that event-driven could be introduced as well. And if your shop is super comfortable with concurrency, with concurrent concepts and parallelism, then it might be a decent fit as well. So specifically, we're talking about fintech, gaming, security, data science, communications, analytics, and travel, and there's probably many, many other ones. I put in an asterisk to all of these because every single one of them has a case where, well, like some particular area that it does not make sense to do event-driven at all. So, and that will go for the next slide the same way as well. With that said, still, it ultimately boils down to the fact that, are you okay with eventual consistency? But there's a bunch of other issues that might come in. So who should absolutely avoid event-driven altogether? So if the idea of eventual consistency really scares you, and it's your business can absolutely not function without it, which is extremely rare, by the way, as a side note. In most cases, most businesses can operate with eventual consistency. It's just that they cannot operate it with that concept across the entire stack, right? Like meaning that they could operate with eventual consistency for, let's say, 70% of their stack, and it would be totally fine. With that said, if you're not comfortable with that, and you need exactly one semantics, and you absolutely cannot lose any data, then in that case, it might be a decent choice, or it might be a reason to avoid event-driven altogether. And this comes down to really to banking, high-frequency trading, human resources. But again, there's an asterisk in there because it doesn't necessarily mean that it needs to be avoided completely. Just some particular areas, like so. For instance, for human resources, you may not want to utilize event-driven for calculating time off. Somebody will get angry at some point in time. But at the same time, sending a reminder email about something, probably okay. So the takeaway from all this is that event-driven is not really a silver bullet, right? And it's also totally okay to have some parts that still remain completely synchronous. It's not that big of a deal if there are some parts that are synchronous. It's just the fact that if you utilize event-driven, you will likely not need some of those parts, and you will improve things as a result. So while you probably have learned a lot right now and you are almost an expert in event-driven, you still may want to do some evening reading with a cup of tea. There have been a lot of articles written about event-driven and event-driven like architectures and so on, and there are some random links in there with some good material. So my observations here really are that, this is like one of the final slides here, is that event-driven is not new. Event-driven's been around for a really long time. It is just that it's become more accessible than ever before. Event-driven is now actually more doable because compute has become cheaper, and so has storage. And I think our comfort level with complexity has dramatically increased, like to a point where, for example, like Kubernetes, imagining Kubernetes 20 years ago would be crazy. It's so complicated, all right? And now we are totally okay with it. I remember when Mesos and the stuff before Mesos even came out as well, these papers that were written about this concept of orchestration, and I thought that it was really complicated. I don't think so anymore. I think it's actually pretty straightforward at this point. And I think the same sort of thing is happening with event-driven. So I guess what I'm saying is that essentially, if you want to achieve higher levels of reliability and higher levels of scale, you're eventually going to do asynchronous. And if you want to be able to contain that chaos that happens and you want to have some sort of rules around this, you need to create some sort of guardrails. And the guardrails are, well, this event-driven concept, this event-driven architecture, that provides all the guardrails. And I'm going to finally leave you with one bit of, I guess, of a prediction of sort, is that I totally foresee that in the near future, we're going to get much more comfortable with event-driven, and event-driven concepts are going to be just as common essentially as microservices as well. Same sort of thing that happened with sysadmins starting to do DevOps and having to migrate to that point. So with that said, you have achieved reliability nirvana. Yeah, all right. So my final slide here is really just if you enjoyed this talk, if you like the stuff that we talked about here, like if you like event-driven systems, if you like architecture talk and so on, come talk to me. I am on the Gopher Slack. I'm also on the Discord for GopherCon, or just ping me on email, the good old-fashioned communication device. So that said, back to our hosts.
Awesome. Thank you, Daniel. I am feeling the glow. Oh, yeah, I've reached out. Yeah, I'm there with you, man.
Somebody screenshot. right. Then go again.
No. That honor goes to you, my friend. You now have a new profile.
Yes. If you haven't been in the peanut gallery, you missed out on one of the most unfortunate screenshots of my life, of my face at least, of my life. So do check that out. Yeah.
It'll be pretty easy because I think in the next intermission we're going to swap this out back here.
Yeah, we'll be.
I'll slide over and then it'll just be you.
I'll be haunting this conference from here on out with that face.
Oh, man.
So I just want to take a moment to thank all of our sponsors again for making all of this happen. Make sure to attend their virtual meeting spaces. Go check out the sponsors page. Many of them are doing giveaways and other types of events and announcements surrounding the show. I also want to give a huge shout out again to Microsoft, Capital One, Salesforce for all coming together to help make this possible in this studio and being able to live stream this to everybody and caption it for free. So this has been really, really great.
This operation, all the equipment, the space, to make the speakers comfortable, making all of this possible. It's really been amazing so far, and we're only on day one.
Yeah, we'll have to get some either behind the scenes pictures or drag a camera out there so you can see the whole crew that's on the other side of these windows out here signaling us through the glass.
I must say they could have sprung a little more for heat though. It's a little
yeah. You might see us with hats. And
if you see everybody looking cold, there's apparently a thing in here where it's the AC and just in the studio is very cold and facilities hasn't come to fix it. Yeah. Fortunately, I would rather cold than hot. Yeah. But if by the end of the event you see us getting closer and closer and kind of
bundling together, yeah, exactly.
Yeah, so next up, something very near and dear to my heart is going to be Go Time. So we have a couple of segments with Go Time this week. The one coming up is called Go Beyond Work. So we've got a panelist with a few of the speakers from this year to talk about like Go Beyond Work and the types of things that people might be using Go for hobby-related projects and things like that.
Yeah, and I think this is, I think Go Time shines in a lot of ways, but one of the ways that I see here, and I really like that they do this, is we're not just talking about industrial strength enterprise software all the time. And they're highlighting, what are people doing when they're tinkering for their side projects and what have you. And I like that, kind of normalizing the fact that we've got side projects sometimes. We like to play around. It doesn't have to be too serious.
It's how many of us got into the language,
Exactly.
right?
Yeah, exactly.
Like it takes you a while, and then you go build something at work, and then you ask for forgiveness, and you hope they let you build more stuff in it.
Yep.
You said go build.
Oh, hashtag dad jokes. All right, so that's 2. All right, we got a dad joke on air. I'm really looking forward to that, and we've got some speakers from this year, like you said, so that's going to be really cool.
Yeah, and if you're not a listener to the podcast, I recommend you actually go listen to. There's, what are they up to, like 400 plus episodes now? So there's always great panel discussions between kind of a rotating set of panelists. They've got really interesting guests that come in and talk about their use cases of Go, projects that they're building, how it's being used inside their company. There's,
We should also remind folks about Gopher Say. That's coming up on Friday, I believe.
Yeah, so tomorrow will be an AMA session with the Go team, with Go Time as well, and then Friday will be the game show, which there have been a lot of answers coming in. So there's been a number of respondents, so I'm hoping for some good stuff. But I think we haven't hit the cap for the number of answers that they can have. So I think now comes the trolling.
We need more of that. Well, before we switch over though.
What is the most common command ran? Cargo build.
No, we shall not end on that.
No.
Aaron.
All right.
Yes,
So
sir.
with that,
Yes, sir.
We'll hand it over to the Go Time team. You all want to do it with me? One, 2, 3. It's go time!
Let's do it. It's go time.
Hi, everyone. It's so fun that you are joining us from GopherCon Europe, GopherCon US, not Europe at all. I'm not saying that as the organizer. You're all aware here. Haha. Another year of GopherCon. It's so exciting to see everybody online again. I hope you had a wonderful first day, and I hope you had lots of fun in the workshops yesterday for whoever attended. My co-host for today is Angelica. Hi.
Hello.
Joining from the overseas of New York.
Yeah, but soon to be flying to London next week.
Oh, exciting.
Finally.
Exciting time to fly.
Yeah.
And we are joined by 3 wonderful Gophers who have amazing side projects that are written in Go. And we have Sebastian Spink, who is a software engineer at InfluxDB. And also, you know what, we'll tell about your wonderful projects right after the intro. We'll keep it interesting. For those who have not attended the talk or your talk has not been aired just yet, because there's a few more days of GopherCon ahead of us. And we have Daniela. Wait, Sebastian, where are you joining us from?
I'm in the Microsoft studios here. So I'll be doing my talk here tomorrow.
Oh, wow. Nice.
Because everyone knows where the Microsoft studios are.
And said
It's in the
Redmond,
internet.
Washington. Yeah. So,
Okay. Helpful.
Washington, cool. Daniela Petrucalik, you are joining us from my side of the overseas, from Europe, but not from the EU.
Yes, I'm currently based in the UK. I'm based in Bournemouth. It's the south coast of England, basically. But yes, Europe. Team Europe, yay.
Yay. And you're a product owner at JPMC, and you're a Google developer expert for Go.
Yes. That's as people say.
And we have Linus Lee joining us. Linus, you're an independent software engineer, and you're working on creative tools. Welcome.
Yes, I am. Thank you. I'm also in the Microsoft studio. I'm across the hallway from Sebastian, but it doesn't look like it through the magic of studios.
Yeah, it looks completely different in your backgrounds, but the sound quality is amazing. Well, it's great of you all to join. We're here to talk about your fun projects. Right, Angelica?
Let's do it.
We are. But before we dive into your kind of fun projects, we want to hear a little bit about kind of when and why you started using Go. Where did it all start for you? Maybe Danielle, you could dive in. How did Go come into your world?
It's a fun thing that I usually like to tell the story as I came for the community and stay for the community, because I started to Go, it was a few years ago. When
we see what you did there.
Yes. A few years ago. Anyway, it was basically back in the days I used to work a company in Brazil, and they were heavy users of Go, and I was getting engaged with the community like in other languages like PyLadies and other groups, and they asked me to help organizing a women's group basically a Women Who Go chapter, and I didn't know what Go was about. To be honest, I was just helping to organize the community, and then I got the opportunity to go to GopherCon Denver, and then the magic happened, and I was simply in love with the language. Everything I did after that, I was trying to use Go in some way or another.
So attending the same GopherCon that you're attending now, this is all how it started. Wow.
Yes, definitely. So it's a very emotional thing to be back here and contributing to this community, this amazing community. So yeah, it has a special place in my heart.
Wow.
Well, for all of us. How about you, Linus? How did Go come into your life?
Yeah, so I actually started out in the web world. I learned to program doing JavaScript and HTML web stuff, and then Go was sort of my way to figure out how to do lower level, I guess backend programming. I had dabbled with things like Python and Ruby before, but I wanted something where I could have a little bit of a low level control over what my data structures look like and things like that without having to learn. I guess the only option back then, the only viable option was C and C++, which is great languages on their own, but more complex than I was, so that I could fit into my brain at the time. And Go was sort of this nice middle ground where there was things like the garbage collector, and it was dynamic enough where I could wrap my head around it, but still let me write programs that I wanted to that were fast enough and small enough and things like that. And so that's the way that I got into it, and I've since stuck with it because it's for all the good things that it offers.
Awesome. How about you, Sebastian? How did you come to us?
Yeah, well, it was love at first sight. I mean, the moment I saw that Gopher mascot, I was like, let's do it. This is it.
Me
this
too.
Is the language for
I
me.
had no idea what it was, and I was like,
Right.
That Gopher.
That was all. That's all I needed to convince me. I mean, before I was working with Python and C++, and it's kind of the same thing where it's just I felt a bit much doing the C++ and C stuff, and then Python was good, but it felt a bit messy, and I really liked Go's opinionated way of doing things, and yeah, so then I started using it, and I've been working on it professionally now, but before it was just project stuff. So yeah.
Yeah, and no one really wants a Python plushie. Gopher is so much nicer.
Indeed.
Right.
One of my, before I came to the conference, I was talking to one of my coworkers, and he was he asked me, "You're going to this GopherCon thing. What is a GopherCon about?" And I was like, "Oh, it's for all the people who love gophers." And we just talk about gophers for 4 days.
Oh my gosh.
Not showing off or anything, but here's the one from Singapore.
I was going to ask. That was what I was just about to ask. I was be like, I've not seen that purple one, and I want it.
It has a tail. It has a tail from that famous fountain in Singapore.
That was gorgeous. Okay, awesome. So we've heard about your start. So
yeah, are you all still working in Go now? And how long actually have you been doing this?
I can take a stab at it. So I've been using Go in one form or another for at least like 2 to 3 years. I think that's when I wrote my first kind of Go projects. I've written Go professionally a little bit. Like I've squeezed it into some projects here and there that aren't like what you'd call like production products, but that are like sort of infrastructure, like testing services or things like that. Just because it's like a nice thing that you can build, and it doesn't. One of the nice things about Go is that we value stability a lot, and so if you write a thing and it doesn't go, maintained daily for a few months, it doesn't break over time. But most of my usage of Go has been on side projects, on things like the thing that I'm going to talk about today, but also other things like little chat clients that I've written and other kinds of learning exercises.
Yeah, I can go next. I think, unfortunately, I feel like I almost like I'm trying to think of the best way to say this, but I barely wrote any kind of Go code in production. So I spent about, I don't know, 1 year back when I was working at Go Cardless, but that's about it. And most of my career in quotes in terms of Go development is basically side projects and things I like to do, and tutorials and things, as you know a little bit about. But yeah, haven't been doing a lot of Go, unfortunately. I was trying to find my way into working with Go, but yeah, for some reason didn't happen.
That's super interesting. That is unexpected. That's cool. Sebastian, how about you?
Yeah, I guess I had the good fortune of being able to work with Go now professionally for the past year at Influx Data, working on the Telegraph project. And it's been fantastic, because before that, it was also just kind of dabbling with it and just whenever I could for projects. And technically for half a year, I professionally, of air quotes, worked with Go, but just because I was just doing it on a project that nobody else wanted to work on. But who knows what that ended up with. But now, yeah, doing it professionally with Telegraph, and it's been fantastic. Open source project with Go. It's everything I could dream of as far as a career. Yeah.
Okay, so speaking of career, Sebastian, would you like to tell us about your fun project in Go?
Hey, awesome. Did you 3D print that?
For everybody who is listening but not watching, I have a little 3D printed gopher that I received from a colleague in previous company, and he 3D printed it. I don't think he planned to print gophers. I don't think his team works in Go, but he is a fan of the mascot, so that was like a nice gift.
Yeah, that's awesome. Yeah, I should have brought some myself that I 3D printed. But unfortunately, got nothing to show off here. I guess I have to wait for my talk tomorrow. Got some screenshots of them. But yeah, I guess my project. So one of the things, so during quarantine, one of the craft projects I started was 3D printing. And the first thing I did was I created a thermal detonator prop from Star Wars, and then used TinyGo to make like the LED light shine and play some audio. So that was pretty fun. And then I kind of started looking at other ways I could involve Go with 3D printing, and it was yeah. So they've got like this whole thing called Octoprint that helps monitor and remotely control your 3D printer. And I was kind of looking at ways to extend that using Go. And but yeah, it's been fun. It's kind of like, it's the 3D print. It's not like I'm writing the firmware for the 3D printer or anything, but as far as Go is concerned, it's kind of like building up around it. And also 3D modeling gophers to 3D print as well. So that's the main thing I was doing there.
Yeah, that's not an obvious choice to choose Go for 3D printing for the modeling.
Yeah, which is actually pretty cool. I wasn't aware that you could do it either, because I was mainly using like Blender and open source common open source projects for 3D modeling that use user interfaces. But there is a package out there that you can create 3D models using Go, and yeah, it's pretty cool. It's just like primitive shapes kind of glued together. So we'll show a screenshot of that tomorrow, but it's gonna end up with a very round looking gopher because it's just a sphere of other primitive objects glued on it. But yeah, it's all written in Go. So Gopher written in Go is possible with, and the open source package I use is called, forgot the user's name, but it's like SDFX, I believe. But so if you look that up, you can, model your own Gopher with it.
And you were, go ahead.
Yeah, and you're talking about spheres and just building shapes out of spheres. Reminds me of when I built, where I was looking at building ray tracers, and sphere is just the simplest shape to write a ray tracer for. And so you start just building scenes out of only spheres, and everything, like your ground is just a gigantic sphere with an infinite radius, and you're building like raindrops on a giant sphere. What does it actually look like to build a model with Go? Are you like outputting it to a file, or are you talking to an API for the printer?
Yeah, so what you output is an STL file, and it's like the standard format file what you kind of do in 3D printing. It's just like it's a file format that describes the geometry like a bunch of triangles, but it writes out, it's like magic, but they use like something called sign distance functions to define the primitive shapes in the code, and then output that to the STL file, which you can then slice into G code for the 3D printer to print out. And
so how many times did you have to reprogram it before you actually got a beautiful Gopher? Because I would assume you had a few interesting looking shapes that may have resembled a Gopher, but may not have been a Gopher.
Making its eyes and its pupils look like an actual Gopher shape is tricky, but I think I got something that looks like a Gopher. You know, it's not you got your iconic mouth and teeth, and then you're like, bam, it's a Gopher. You're done. It's a sphere with, eyes and a square, but that's all you need. The beauty of the Gopher transcends all shapes. It just,
I must say, I really admire anyone that can do 3D modeling. This is such a thing that my brain can't process. That's why when I go to my hobbies, I only do 2D things, because my brain just can't process the third dimension. I really admire that. I'm looking forward to seeing your talk, how it works.
Yeah, I did cheat and use Blender to make it sexier looking than the spheres, but yeah. It's definitely my first thing I've ever 3D modeled before. Usually I'm also just working in the 2D space. It's definitely more comfortable.
Did you use Go because it was the best language to do this, or because you write Go anyway? Or did you think about using other languages, try it out before settling on Go?
That's a good question. No, I chose it because I wanted to write in the language. Because I mean, technically, Python is what Octoprint, the software I mentioned, written in, and it's kind of like that's the ecosystem, and there's a lot of good community work around it. But I was like, no, I'm going to go against the stream, doing Go, regardless if it's the best choice or not. I'll find out at the end. I mean, it's pretty nice to work with just all the benefits of using Go binary that you can send around easily, and don't have to worry about Python versions and setting virtual environments. So. Yeah.
Interesting. You can cross-compile to all the different 3D printers.
Right.
Is there anything that using Go allows you to do that you would be able to do with a Blender? I guess you could sort of programmatically generate a bunch, like if you wanted a grid of spheres or something, you could programmatically generate it. But yeah, what have you experimented with that would be hard to do in Blender or another piece of software?
I guess so. I am pretty much a novice with as far as 3D modeling is concerned, but so I couldn't figure out. So the reason why I used Blender to like finalize the Gopher, because I couldn't really figure out how to make like a nice like hourglass shape for the Gopher, like that perfect body. so it wasn't just two spheres attached to each other. But I guess the benefit of using Go for it is the fact that you can now just send that piece of program to somebody and they can adjust it and easily shareable. Right, you could send your Blender files, share those as well. But yeah, I felt like the learning curve was also a little bit easier. The fact that it is just Go and just defining shapes, while using the user interface for Blender is tricky. There's definitely a steep learning curve there. But
it's true.
Yeah. Have you used it before? Have you done 3D modeling?
I have personally not. I've looked at it. I had some friends. My roommate in college was like a mechanical engineering major, and he dabbled in it. He would make some stuff for me occasionally, and I always thought it was cool. But again, because of that like learning curve, where you look at someone's computer when they're doing it, and you're like, I'll never be. That looks like a professional power tool kind of interface, and that scares you off a little bit. But if it's just a Go program, maybe I'll give it a shot.
Yeah, I definitely recommend it.
I feel like I need to go buy myself a 3D printer now. Give it a
I
go.
also recommend that. Yeah, and they're surprisingly consumer friendly as far as the price and the setup is concerned. You'll need space, I suppose, is the biggest thing, and patience.
Just put it right in the middle of my lounge, or be the centerpiece. Or just continuously churn out gophers.
Yes, that's the ideal setup. That's how it works in my house.
One thing that you alluded to earlier from another question was like the debug cycle, which I imagine is a little slower than just running the code. Like, I guess you can run it and then look at the model inside Blender or something like that. But do you ever have like a hardware debug cycle where you print it and you're like, oh, this looks bad, and then you have to rewrite the program?
I kind of missed that question. Yeah, that's right. I don't know if there's a better way of doing it than just building it and running it and being like, well, it's a couple millimeters to the left, like scoot it over. I'm a big advantage of using Blender if you use your interface. You can just scoot it over and you can see where it's supposed to land. But, in the world space, I was definitely just guessing the coordinates. I was definitely going to mention that in my talk, where it's like, these numbers are made up. Like, this was just me hoping for the best, and they ended up in the right spot. So
trial and error.
Right.
I had an interesting experience with that when I was writing some games. I also do a lot of guessing in terms of positioning things. So in the end, I ended up using Steve Francia's, I don't remember now if it's Viper or Cobra, the one that library that helps us load configuration dynamically. So it's basically every time I had something I need to set up a different thing in the screen, I used a dynamic configuration, and I was reloading JSON files on the fly, and you just couldn't save it because the render was just updating the screen every single frame. I was just kind of automating my trial and error just with dynamic configuration. That might, I don't know if you thought about something. I'm not sure how fast is rendering, but in my case it was just one frame, so that was pretty fast.
Yeah, it was pretty quick in the sense that there was like the slice. I was using the slicer, the program, to get it to the 3D printing format, and you can reload it in there. But it felt pretty hacky. But yeah, sorry, what were you going to say?
I was going to say, let's hear more. Let's go from 3D to 2D. Danielle, I would love to hear a little bit about, you talked about some of your in the weeds, how you got it working, how you tested it, but like, what is your project, and how did it come to be? I would say prerequisite, and I said this to the group before, I have a very, very special place in my heart for this project, because when I was but a young gopher, not even, when I was but a young newbie dweeb looking at the computer science world for a language that fit, I went to Gotham Go and saw you do your talk on this side project. And it got me so excited. I went home and spent the entire weekend building it. And that was one of the main things. I was like, this is my language. This is so fun. I'm ready. Let me be a gopher.
I'm ready. I love this attitude, and I'm really happy that it had such an influence, because getting from the start, the beginning, since people don't know my project yet. Basically, I wrote this tutorial, which I call Pac-Man from scratch, or Pac-Go for short, because not a man is a gopher, maybe. And the idea is to rebuild the classical game of Pac-Man, only using Go and the standard library, no external like fancy packages. And in order to abstract the drawing function, because this tends to be the most complex thing in games, like how you render to screen, and I didn't want to expose people to this level of complexity, we ended up using like the terminal as your screen. And since Go supports Unicode, you can actually print emojis in the terminal. So the entire board of the game is rendered using emojis and using some clever tricks with ANSI escape sequences. You can put colors and draw walls and things like that. And there are some things that Go makes really easy to do, like especially, for instance, you want to separate your input handling from the main program. You can use a Go routine and channels. So there's things like this in other languages. I tried to do this before, like C++ and others. Kind of you need to learn threads, you need to learn synchronization, all these more advanced concepts, but Go makes it really easy for a beginner to have like, oh yeah, maybe you don't even fully understand what a Go routine is or a channel is, but it's enough for you to get started and do something. And the whole idea of this project was to give the community something in terms of tutorial, like a starting point, a bit more interesting than building APIs, because I know APIs we ended up doing this for work, but why not having something more fun that has visual feedback, like so you can see things moving on the screen? I don't know, for me it's magical. And yeah, but maybe that's because also the only reason why I'm in this industry now is because I love games and I always want to work with games, and that was kind of like my, oh yeah, I never worked with games before, but this is my opportunity. I'll make something with games and Go. And yeah, that's how it started.
Yeah, and I think the beauty of it is exactly what you just said. For people who are learning Go, whether from another language or completely it's their first language, you go through that phase where you're like going through all the like Go tutorials and you're trying to do this little like app and you're trying to print hello world, but then you hit this ceiling where you're like, what do I do now? I know the basics. I want to build something that feels like an accomplishment, that feels exciting, that feels like, oh, this is something I want to like show my friends, show my family, be like, look, I can code now. And this is fun. It's colorful. As you say, it gives you that visual feedback. And it gives you, as a beginner, that feeling of accomplishment. And like, I did this. I made it through that tutorial and I accomplished this thing. And I think the beauty of how you framed it is that you've really paid attention to making sure it is truly step-by-step. And it really does guide everyone through why you made a decision, how you did it. You provide the code so you can look through. I think it's wonderful. I'm like waiting for your next game to come out. Like, what's going on?
Yeah, I've been a bit busy with life and things, and but definitely there are more things coming on your way. Yeah, stay tuned. I did actually talk at GopherCon UK about my next project, which is now it's a card game. I'm rebuilding an old 80s card game that it was very. I can't even say it was popular where I came from. It was just like the game we had when we were a child and we played that game. So I couldn't find an international version of it. So I only had like a scan of the cards that I used to reference the game. But basically I'm rebuilding it. But now I'm trying to be a bit more professional, if I can say that. Definitely I can't say that. Nothing close to being a professional. But I'm using this library called Abitan, which is a proper game development library within Go by Hajime Hoshi. This guy is amazing. Really thanks for writing Abitan. And yeah, so this work in progress. It's not very pretty now, but I have a functioning prototype, and the code is open source. But I didn't advertise that much because the game is ugly now. It's not very beginner friendly. I was just kind of like a proof of concept, trying different things, learning everything as it goes. I did that again.
It's hard not to say it. It's very easy to fall into the pattern. So, I mean, as you've been iterating on this project, as you've been building, and as you've been delving more into like the world of kind of games and programming for games, is Go a good language for these kind of projects? Or was it that you already liked Go and it was fun? Or in fact, is Go interesting, good to play with, but there are other languages that may serve the gaming function better?
I think Go is, Go is a very good language with some asterisks, like some side notes maybe. Because the traditional language for writing games, like from if you are old school like me, is like C++ and C and things like that. And in terms of Go, I tend to see Go as an improved version of those languages because it abstracts so much. You don't need to worry about so much about memory management. You still need to worry a little bit about memory, but not as much as you had to do in the past with these other types of languages. Of course, they also evolved, but I really like how Go is pretty straightforward, has a simple syntax, very consistent across all different features of the language. So it makes gives almost that feeling of a scripting language. Like, it's very simple to do simple things, and this is, I think that's the beauty of it. So it also becomes very productive. The problems come when because Go is traditionally a systems language, it's not very popular in the gaming industry. You don't have a lot of library support and things like that. You have the basics. You have SDL bindings, you have AB10 and a few other gaming libraries, but it's not widespread, so you don't have a large community that can help you support it. But essentially, everything that you need to build a game, you have there. So I think that's kind of like, I love the language, and I think that's almost like as Sebastian said as well, but maybe Go was not the best option, but that was the language I want to work with, and so that's kind of why I decided. But I think overall, I think that you can do good games with Go, and even AB10, they're just recently publishing their first game on Nintendo Switch, so you can see it can be used for like real games, like real commercial games.
Production grade.
Awesome. Daniela, I'm super curious, as somebody who knows nothing about game development. When you say gaming libraries, what kind of tools do they give you? Like, what do you need in a gaming library?
A lot of things actually, but I'd say the most basic ones are, how do you handle inputs? Like when you're writing a game, you don't really want to care if the player has a keyboard, a gamepad, or anything else. You don't want to worry about specific drivers for different types of inputs. You want the game library to give you this for free, and you just want to know key was pressed, and you'll do your mappings, you do the thing. And the second thing is drawing to the screen. Another good example, you don't really care about the low level part of drawing to the screen. You just want to say, plot my pixel there, and that's it. Or
so like relative 10% down from the beginning of the screen, kind of.
Yeah, and that and I'm talking only about like 2D. And 3D gets way more complex, but like scaling operations, rotation, all the kind of transformations you can do in an image, and also sound is a huge thing. Like I don't want to write like a music player. I should get this for free from my gaming library, things like that. So maybe sometimes you have some kind of artificial intelligence processor that you can just write an AI as in a script, and the engine will load that script as and control your enemies and things like that. So this is kind of support. So you can focus really on the content creation, because what makes or breaks your game is really not necessarily the code, is the art, is the sounds, is your assets. I like to say it's all about your assets.
Yeah, that resonates with me a lot, actually. I've tried to, occasionally I've come across, I'm not a big gamer, but occasionally I've come across little like Steam games that I thought were really beautiful and well done. And at times I've had the thought of, oh, maybe I should try to build a game of my own. And the thing that I always bump against is I can write the logic. I can probably learn to use one of the game engines and try to make something that's interactive and do the things that I want to do. But the things that make a video game really compelling is all the art and all the sounds and the design. And like that requires me making 3D models, which, as we discussed, is difficult, and doing art and having even just building a storyline behind it and all the character design and things like that. And that's a whole other art that's outside of software.
There's a huge like iceberg of game development that's about you think that the presentation is just like a thin layer, but you have assets like in terms of art, sound effects, and music. It also either kills your game or makes the best, will give amazing results. But also the whole part about game design, of how your game mechanics work, like what are the winning scenarios, what are your objectives, how can you make that thing rewarding for the player so they will be engaged and really enjoy playing your game. How can you balance your game so you're like, this is has a decent amount of challenge plus reward. So these are the hard parts, and also my brain is kind of I'm really bad at this, and I'm trying to get better. But also partnering with the right people can definitely help a lot in this.
I have a great idea for your game, Daniela, to make it really rewarding. You can use Sebastian's work and 3D print the cards.
I think that will be great. Great idea.
You know, you always feel paper cards in the hand, and once you'll feel like more chunkier, like reminding like a phone, it will be very interesting. You know, you have to pay more attention when you do that.
Revolutionary.
Well, talking about something that's very challenging, engaging, and rewarding, Linus, let's hear a little bit about your awesome project.
Yeah, so my project is called Oak. It's a toy programming language. So what that means is it's a programming language that you can use to write things like web servers and little apps and command line interfaces and things like that. But it's a toy language, so it's not something that you're going to use at work or to build a production service for lots of reasons. But it's a dynamically typed scripting language. It looks a little bit like JavaScript. It works a little bit like Lua if you've used it. But it's a Go program. So it's a language that's written in Go. And what that means is that when you run the Oak CLI to start up a REPL or to run a file, that thing that is running the file is a Go program. But the program source code that it's running is written in a language that I made up called Oak. If that makes any sense. It's a little bit sort of recursive. But yeah, and so part of it was designing the actual syntax and semantics of what the language is going to be able to do, how it works, what are the types, what are the values, what are the things you can do, how do you define functions and things like that. And the other part is actually implementing, in Oak's case, the interpreter that actually takes the syntax, the program you've written, and does the thing that the program's supposed to do. And also incidentally other things like telling you errors and concurrency and lots of other things that you might encounter as an interpreter.
How did you come up with the idea to do this in Go? Like, did you say, I want to learn Go and I want to learn Go by creating a new language?
It was a mix, actually. So before Oak, there was Ink, which is the conceptual predecessor to Oak. They're very similar languages, but Ink was the first language, the toy language that I made. I made it after having gone through like a tutorial on like how to make a basic Lisp interpreter. And I wanted to make something that was a little more usable and looked, frankly, like had the syntax that I wanted. Because everyone always, when they first learn programming, they're like, oh, I really like this language, but I wish this keyword said something different, or like the symbol was a different symbol. And it was my chance to like play God with my own language. And to do that, actually, at that point, I was mostly proficient with only like the really dynamic languages like JavaScript and Python. And so I needed to learn a compiled language that was a lower level to be able to build an interpreter that was actually usable. And Go is not the typical language that you would use for such a task. You usually use like C++ or more increasingly common is like Rust or other languages like that. But as I noted before, it was harder for me to wrap my head around those at the time than it was for me to learn Go. And Go was low level enough for me to be able to build an interpreter. And so Ink was my first Go, like learning Go project. And simultaneously I was also trying to learn how to build a programming language.
That's super cool. Has anybody made anything real cool out of your programming language, Ink?
I have. So, and then other people have used some of the stuff that I've built. Actually, one thing that's relevant for the Go community is if you guys are familiar with the Go by Example website, where it sort of walks you through Go and gives you kind of different examples of how different parts of Go works. So a guy named Andrew, man, his name is escaping me now, but Andrew something. We've talked on the phone before, but he made an Ink by Example site. And just as Go by Example is written in Go, and Go compiles the website, Ink by Example is written in Ink. And so it compiles itself, and Ink has its own syntax highlighter and sort of code formatter and things like that. And so the website looks a lot like Go by Example. It's inspired by Go by Example, but it's a website for Ink that someone else made that isn't me, which was super cool to see that there was like another user for the language. And then on top of Ink, I've made a bunch of my own personal apps like Twitter clients and Notes apps and things like that that I use day to day.
That's super cool. I guess the next
You
step is
mentioned Lua in your opening statement. I was just wondering because Lua is very common in the game development community, right? For AI scripts. Would you
Right.
see your language could be used for the same type of use, like writing scripts for AIs or things like that?
Yeah, that's a great question. So a lot of the domain of toy languages is actually for embedding in other programs. And Lua is a great example of that. I think there's some specific things about Lua that make it really great for embedding in a game specifically. The things that come to mind are like Lua is a really small language. It's written in C, it's pretty readable. And so you can, it's fairly easy to embed in terms of just like the technical work involved to embed it into another program. The other thing that makes Lua unique is that it has features of the language and of the interpreter that make it easy for you to fit it into another larger program. So Lua has, I forget what it's called, but it has like a type that is supposed to be like an opaque type that just wraps something else from the host program. So if you have a game and you have like a C struct that represents a character or an object or something, you can just wrap that and expose it to Lua with some APIs. It's also fairly easy to define foreign function interfaces for Lua code to be able to call C functions. And I think that's what makes Lua really great for game development. Oak in theory has those things, minus the CFFI, but because it's embedded inside Go, anything that includes Oak has to also include the Go runtime, which makes it a little heavier and is more opinionated.
How can the community contribute to these languages, to Ink and to Oak? You're looking for documentation, code contributions.
Yes, for sure. Ink is actually, so one of the reasons I made Oak was that I made Ink and then I used it for a couple of years to build stuff. And it was usable because I made stuff with it. By definition, it was usable, but it was not very good. The language is kind of tough to use. The interpreter sucks a little bit because of the particular ways. When you learn to build an interpreter in school or in a course, there are specific things that you spend a lot of time on, like parsing and compiling, and there's things that you don't spend as much time on that actually turns out are really important and hard to get right. And one of those things is like error handling. If you're trying to get other people to use your language, most of the time they're going to be spending initially is going to be writing incorrect programs and getting errors. And to do error reporting correctly, you have to gather a lot of information about the runtime of the program, like where it's happening, what's causing it, and be able to give users really helpful errors. And none of the tutorials cover that properly. And so that's like mistakes like that I accumulated over time. And eventually when I wrote Oak, I fixed a lot of those. So Ink isn't as usable as Oak. And if you want to check things out, I check out Oak. I'm still sort of tinkering away at it as a solo project, but if you want to try it, you're welcome to try it. And then if you have any like problems you find with it or bugs, filing those would be super helpful. If you have opinions on how Oak should work differently, I have my own opinions, and the point of Oak is to manifest them. But if you have your own opinions, that's a Go project. It's not that complicated. You can probably read through it and come to my talk to figure out how it works. And it's only a few thousand lines. And so you could fork it, make it into your own, change all the keywords and all the syntax, and make your own language out of it too.
That's awesome. Tempting. How about Daniela? If people want to help, want to get involved, want to live their best Pack Go life, how do they do that?
So I have the GitHub repo for PackGo, like it's github.com. I use Danicat/PackGo, and we already had a lot of contribution from the community. I think I built until step 8, and I think we have step 10 or 11 or something like that. So people definitely were inspired and started creating new content for it. It's a bit abandoned now from my perspective. I wish I could have supported it better. So things like Go modules, testing, and are some topics that we're not covering in the traditional workshop that I think if people are willing to contribute, that would be amazing. Like a chapter on Go modules, a chapter on testing, things like that. That would be great.
Sebastian, how do we contribute? How do we help? How do we get involved?
Yeah, I guess I'm mostly thinking of using Oak to write a Pac-Man game now. So, but I guess I've got my Gopher model uploaded, so you're welcome to download and 3D print that. So that helps me of just seeing more Gophers out in the world. But then, so part of the thing I worked on was a plugin for the Telegraph project that I'm working on now as a full-time maintainer to interact with Octoprint, and that's just an open source repository. You're welcome to whatever you want with that's written in Go. But yeah, maybe extend it, add more features to it.
Awesome.
Cool. Well, that's inspiring and also gives us all ideas on what can we do in our free time. Okay, time for unpopular opinions.
I actually think
you what?
Okay, so you know the rules. You have the stage to tell us what is your unpopular opinion. It does not have to be about your project, about tech, about anything at all. It can be about anything. And we will then go and ask on Twitter to see if your unpopular opinion is really unpopular or yes, popular. Linus, would you like to start?
Sure, I'll take it. My unpopular opinion is that it's actually probably a more popular opinion, but it's phrased, the way that I'm phrasing it, I think is important, which is that I think it's an accident of history that we don't expect every computer user to be able to program. I've been watching a lot of, this is gonna reveal my age now, but I've been watching what I consider to be older TV programming about computers. Computer programs that were coming out in the mid and late 80s and early 90s. And it's kind of astonishing how all those programs sort of expect the user to buy the program and then use macros or scripts to program it to fit their use case. Things like databases or word processors, or there's tons and tons of support for just, you buy the thing and then to make it useful, you program it. And to a certain extent, all these consumers of software are expected to program a little bit and know how computers work and customize it. And it's a little sad, I think, that we don't expect that of users anymore, and we expect them to just take the product and use it. And I wish there was more software that expected and taught people to think in terms of programming and try to customize their software to work the way that they want it to.
Okay, Sebastian.
Yeah, I guess my unpopular opinion is I think that if your open source project has a hand-drawn logo on it, then it's a good open source project and it can be trusted. So
Cool.
just you can judge it by the cover.
Hey, Daniela.
Okay, I think my unpopular opinion will make me the most unpopular person on GopherCon this year. Sorry guys, but I don't think Go really needs generics.
Oh.
Dun, dun, dun. What a mic drop to the end of the show. Thank you, Daniela. We have intentionally, we knew you'd say that, maybe. That's why we asked you to go last. Yeah, but that's a brave choice. To wrap this up, thanks everyone for your interesting insights and sharing about your fun projects and for talking about that at GopherCon. And thanks everybody who tuned in. Enjoy the talks and see you around the Discord.
Yeah.
Thanks for having us.
Thank you to our awesome
thanks for
host,
having us.
Natalie. Awesome as always. And see.
All right, thanks everybody for the great
Meet
panel
everybody
discussion with the Go
I know, I'm
Time
like
team
seeing
and
everyone's
panelists.
like special.
And we're looking forward to the rest of the content they have for the rest of the week. So what's interesting is I want to tell a little story here. Linus was talking about how...
Can I do a quick update on the studio status? It is now this cold.
Oh
in
yes,
the studio.
it is
Sorry
getting
to interrupt.
colder
Yeah.
in here.
Next thing you know, you're gonna see a little heater, like
Yeah.
a little space heater, hanging out here. And also a little huddle, trying to
Send
get warm.
marshmallows.
Send marshmallows. It's getting, yeah.
Sorry to interrupt, Eric. Please continue.
So Linus was telling a story about how he was talking to people who had no idea what GopherCon was and like, what is this? And he's like, oh, it's a story, or it's a conference about people who love gophers. So one of the years, I want to say it was 2015, we were in the Denver Convention Center, and we had most of the convention center, but there was another kind of event taking place in parallel in some of the other rooms. And they actually got really mad with the convention center because they couldn't believe how insensitive they were to schedule them aside. Like GopherCon, it turned out it was the Cattle Ranchers Association, and they weren't pleased with what gophers were doing.
Gophers.
And we had to explain this has nothing to do with actual gophers.
Right. Oh my goodness.
So how's the Peanut Gallery channel going?
there's some good stuff going on in there. I mean, can it live back up to the weird screenshot of me? Well, I think maybe, because we now have a screenshot of you doing.
Oh yeah,
this.
doing your.
Right. Yeah, that's true. That's true.
It looks more like you're doing a doo-doo.
A doo-doo, right. You know, dada and a doo-doo. Okay. Yeah.
We can get a slideshow of those later. Yeah. We also have a new channel, the Engineering Quotes channel. So my favorite one from there is an anonymous quote from a senior engineer. That's "This will be easy," and then there's a narrator. If we can get Morgan Freeman, we will. But I don't know his schedule. The narrator will say it wasn't. To follow up on that.
I think you should attempt the Morgan Freeman voice. I don't think we go anywhere today until you get it down.
Okay, I gotta go to the voice warm up and everything, and I'll get back to everybody with that. So yeah. All right. Well, should we head over to our next speaker?
I think we should.
All right. Well, we've got Akhil Indurti. He is a software engineer at Comcast, and he's done a ton, like I mean it, like a ton of stuff with static analysis and Go. Here, a couple of things here. He's written a bunch of static analysis that's been integrated into command vet, so the standard Go tooling. He's contributed to the standard library. He's contributed to the compiler. And a lot of the work that he's done has also been large-scale refactorings at Comcast for his team. And that's a huge use case for static analysis, right? You can do these refactorings fairly quickly and reliably without having to rerun the whole test suite and all that, because you can analyze the code. With that, Akhil, take it away.
Thanks for the introduction, Aaron. I'm Akhil Indurti, a software engineer at Comcast, and I'm going to talk about how to write a static analyzer for Go code. So this presentation is going to go over what static analysis is, why you would want to write one, what makes for a good static analyzer, and how do I actually go about writing one. And the analyzer we're going to be talking about today is one that checks that after you've opened a connection or a file or something, that you've handled an error and then you've closed it afterwards. And then there's some discussion of false positives that you might encounter along the way. So first, what is static analysis? The idea is to check that some arbitrary property holds about your program. And you want to know that without running it, hence the static part. So answering questions about your program without running it, examples of static analysis tools that you might have run before, the Go compiler itself. The front end of the compiler will parse and type check your program and report errors about the syntax of your code, or if the types are consistent. You run this all the time. And there's Go vet, or command vet, which integrates a bunch of static analysis tools into it, like checking, for example, that your format string is correct. There's static check, which is a large suite of tools that is very popular in the Go community, and that is in many project CI pipelines. If you step away from programming and consider analysis tools in general, you might consider a spelling grammar checker for a Word document to be like a sort of static analysis tool, or grepping over some text for some pattern to be a tool. Although they're not as semantically focused on a code base or a particular language, they're still checking for patterns and things. So the types of questions that you might want to ask about a program, right? Are my types consistent? So if I declare a variable of type int and I try to concatenate to it a string, well, that's going to have inconsistent typing. And so your Go compiler will complain about that. Is there a data race in my program? So this is something that's pretty hard to verify statically unless you introduce a ton of annotations. But if you use something like the Go race detector, which will introduce instrumentation so that when you run your program, it'll catch these issues at runtime, then you'll be able to find these errors a lot of the time. Another thing you might want to ask about your program, am I leaking connections? So if you have some web server that's constantly opening and closing connections to a database or some network device, you might be creating tons of connections at runtime, and you want to make sure that like over the course of your program running for many hours or days, that it's not slowly leaking more and more connections. How do you check that without deploying to production or to a long-term testing environment? Or are you using the proper units for arithmetic? So sometimes you might like multiply a time.second by a time.millisecond or add those things. And according to the Go's type system, those are just integers. They don't have separate types. And so one thing you could do here is to introduce some static analysis tool that checks that, hey, the arithmetic that you're doing doesn't really make sense. So why exactly would you want to write your own static analysis tool? There's plenty of static analysis tools out there, like in Static Check and GoVet. First of all, why would you want to use one of these outside of your compiler and testing environment in the first place? So I guess if we should first talk about how you catch issues in a project or a program. You'll often go through this pipeline of you compile your program, you test it in either do unit tests or integration tests. You might introduce logs, metrics, and traces to ingest information about related to sending alerts, and you might use that information to debug your program. Static analysis comes in very early in this pipeline, around when you compile it. You could argue that static analysis might come before you compile your program because you're in your editing environment, you're often getting a bunch of errors from your editor. And so why would you need additional tooling outside of what your compiler or your testing tool provides? Well, the advantage of static analysis, or the disadvantage of unit tests, I should say, is that it's often easy to miss edge cases. You might be checking that a property holds for everything, for all of some input or data set, and you might not be able to exhaustively test every single item in that data set, so you may end up hitting an edge case. An issue related to observability is often that it can be hard to trace back issue to the source in your actual program because it's further in it happened way later when you deployed it. And if you notice that that picture before, the further along in the pipeline you were, the redder things got, and that was meant to signify that it's often more expensive to fix an issue when you are already deployed a program. And so static analysis can be a pretty cost-effective way in terms of dollars, I guess, to catch things earlier. Although there's something to be said about the amount of work you have to put into to satisfy a static analysis tool. And really, you should just think of static analysis as just one additional thing in your tool belt. And if you can write a static analysis tool, that can often pay off if you have a pretty bespoke situation in your on your project that you can't find anywhere else. So let's talk about what makes a good static analysis tool. A good static analysis tool will provide some meaningful results to the user. That is, for many definitions of meaningful. Meaningful meaning you're getting an error that is actually real, so that it's not for example, it's not a false positive. The issue is something that occurs commonly enough that it's not just a one-time thing that you could just fix by looking at it. It could hopefully catches something that you probably don't want to see later on. Probably some big issue, and a lot of these good qualities I'm talking about apply to alerts as well. So there's a nice correlation there. Here's an example of a false positive that you might see. For example, if you use GoVet and you use fump.println and you pass in %% this is a false positive, it will show an error to you because it can't actually check that you're not using the format string with the %t in it, which is for %t is for true and false for Boolean arguments. And so some static analysis tools, if you use Static Check, for example, will allow you to suppress these errors. So you might be able to put a lint ignore comment above your code to tell it, hey, ignore this issue. It's not something that's actually real. So we know that we don't want false positives, and we want to provide meaningful results. How do we actually write a static analysis tool? So in our case, we want to find something, write a tool that checks for errors and closes connections, or checks that we close connections. So before we go into some the Go packages that might allow you to do this, let's try to use some simpler tools that use pattern matching. For example, there's a very popular tool, semgrep or RuleGuard, which are written by members. RuleGuard is written by one of the members of the Go community, where you can write a pattern about some Go code, and you can just sort of run it on a huge code base. So you don't actually have to write a bunch of code to get it to work. So this is a pretty nifty way to do things. For example, if we have this test program that opens a file, handles some error, and then it calls close twice, RuleGuard will allow you to use these $sign patterns to check that there's to refer to variables in your program. For example, if I wrote a thing that checked for double closes, or a close that happens more than once, I could write this pattern that has that checks that I've assigned something to a closer and error, and then there's this underscore thing that says, hey, I don't care what's on the right-hand side of this assignment, and then this wildcard thing that says, hey, 0 or more things in between that last assignment and this close call. That's why there's a star there, and then there's an actual call to close. And there's another, and that pattern is repeated. There's a 0 or more statements followed by a closer.close. Now, the reason why there's a $sign in front of closer and error is that it's not actually the name. You don't want a variable named closer or error. You want a variable, whatever variable it is. That's why there's a $sign. And then you can add additional constraints to it. For example, that the variable that is referred to by closer, the identifier closer, it actually it implements IO closer, the IO closer interface. And then if you encounter this situation, then you can say that, hey, we found a double close. And so running this on that test file will return an error like this. Now, if your situation is a bit more complicated and can't be captured by a pattern matching tool like this, then you might want to go into looking at the Go analysis packages. And the analysis framework is a way that all the static analysis tools are typically built in Go. Static check, command vet, Go please, they will all use the analysis tools, the analysis framework. And really, it's just a struct that you have to fill out. You declare some package, and you have some struct that is of type analyzer. And the main important part of the struct that you have to fill out is the run method, as you can see at the bottom here, and or the run function. And the run function, it just takes this thing of type pass and returns an interface and an error. And so that's the main part. This other stuff is related to documentation and what other analyzers you want to have run before it. So in our case, this close check that we were talking about, let's declare a variable in some package that I called close check. And this struct that we're going to fill out has the name, documentation, this run method that I haven't actually written yet, and I'm going to require something. I'm going to require that an inspect.analyzer has run before this analyzer has run. And that's a key thing to remember, is that we don't want to have to parse, type check our program before we run our analysis stuff. We want the program to already have been parsed and type checked, and we want to just look at the typing information that's already been reported by the type checker and take advantage of that information. So by saying that we want the inspect.analyzer to run before, or that we require it, we're just saying that that should be that we want, like the type information, the parse tree, and all that stuff. Okay. So let's think of a strategy. It's usually good to have an idea of what's the kind of pattern that you're looking for, or what are you trying to test. So in our case, we want to check for some assignment where I say L value here, but really I want the left-hand side of the assignment to have some closer, whether that's a file, a connection, whatever it is, and an error. And if there's an error, then we want to make sure that we handle that error before we call close on the connection, and that we call when we don't close the connection more than once. So that's the strategy we're looking, or the pattern we're looking for. So we start off by writing this run method. Here's some basic boilerplate you'll probably need for most analyzers you write. It's that at the top you want to actually get access to the inspector. The inspector is this object returned by the inspect analyzer that we wanted to run before our analyzer ran. And so the inspector, once we get it, it's going to have all sorts of information for us, like the type information and the parse tree and such. There's another thing we need to pass it, which we need to declare. It's called a node filter. And the node filter is just an array of the kinds of nodes we're looking for in our syntax tree, so that we don't actually have to walk the whole thing ourselves and say, hey, we want to look at like a block or a statement or an expression. Here we can just say we want to look at all the assignment statements and then start from there. So that's what this node filter is. And then at the end, I just have a return for the types that we're variables of the types we're returning. Okay, so assuming we have all that, the inspector has a couple methods on it. One of them is a with stack. There's also a traverse method. There's a bunch of just methods that it has where it runs over a program in its syntax tree. And in our case, we want to just use with stack. And the key thing about with stack is it'll pass in the entire stack of nodes or path of nodes that lead up to your current node. So if your current node is like an assignment statement, you probably want to have access to the block that it's inside. So if I'm assigning like connection error equals open a file, I want to know that the outer scope that it's part of, so that I can check that, hey, I've closed something, or I've checked that I've handled the error after it. So that's why I'm using with stack. So you could probably do some other a regular traversal and keep track of state yourself. But I like with stack because I can just directly access its outer scope. So I passed in the node filter that we created before, and this function, which is the actual thing that's called on each assignment statement. So this function takes in a node, a push boolean, and a stack. I've already discussed what the stack is. The push is really because it's the traversal goes down the stack or down the syntax tree and up the syntax tree. We want to just look at the program when we're going up the syntax tree. We don't want to look at the assignment statements twice. So we don't really care about this boolean here. We just want to make sure that we check the boolean that, hey, we just want to analyze it on the way up. So we check if we're pushing, and we just return true then to say that, hey, just keep going. Okay, so ignoring the push part, we get the statement that from inside of the node that we're given. This node represents like some node in our syntax tree, and we check that it's an assignment statement. Here, I'm not handlings, anything in the type assertion, because I know for a fact that it's an assignment statement, because that's all that's in my node filter, which is I just want assignment statements. So I can just say, hey, I got a statement here. I check that the statement has a defined token. So if you look at the documentation for an assignment statement in the Go AST package, it'll show you that there's some token associated with the assignment. It could either be a regular equals sign, or it could have a colon equals, as we know from a regular Go assignment. And the colon equals is actually a short variable declaration. And we only want to look for those. So if it's not a short variable declaration, we'll just return false and say, hey, stop going down the syntax tree. This is not what we're looking for. So now that we actually have an assignment, we want to check that, hey, we there's a closer on the left-hand side, and there's possibly an error on the left-hand side. So let's do that. We have our assignment statement, and we're going to iterate over the left-hand side of it, which is LHS is just another field on assignment statement. And for each expression on the left-hand side of the assignment, we're going to first check that, okay, it's an identifier. So already we're in a situation where, okay, what if you're assigning to some variable, some thing in an array, or then this would probably not handle that, right? And so you have to ask yourself, is that such a common scenario in my code base that I want my analysis tool to cover it? Or is every place where I'm creating a connection something, a situation where I'm assigning to some identifier? So in our case, we only care about identifiers that are being assigned to here. So if it's not an identifier, we just skip it. And then here is where we're actually using information reported by the pass. So the pass has a field on it called typesinfo, and we're accessing typesinfo and definitions, and we're basically accessing all the type information for that identifier. And so first we're saying, okay, grab the type information for this identifier and call it type, and then check that this type implements an IO closer. And notice here I haven't actually shown you how to grab the interface type for IO closer, and also check that whatever that type is, that it implements error. So as we're iterating through the left-hand side, one of these variables might be a closer, one of them might be an error. Okay, so here's how we're actually defining the closer and the error type. So there are multiple ways to go about this, but we actually want the Go types definition of this this interface, which is a little bit complicated to get. For errors, it's not terribly complicated. We just go to the universe of types in Go, and we look for something called error, and we get its underlying interface, and that's the error type that you see at the bottom. For closer, you can try to use like the packages like the importer package to actually get the IO closer type embedded in your binary or embedded in the package information. But a probably simpler way to do it is to just define it yourself, because interfaces you can just define yourself. So we will define an interface using the types package. This is kind of like using reflect, where you're saying, okay, this type, this interface consists of a bunch of functions, and this function doesn't take a receiver. It has no parameters, but it returns an error. And the error return type, because functions can return multiple values, it's a tuple. So you create a tuple, and inside that tuple you have a variable, and that variable corresponds to something of type error. So it's a lot of it's kind of gross, but it's done here, and it's not variadic either. And that's all. And then you call complete to say, here, build it. So that's how the closer type and the error type are defined. Okay, so we have our closer type and error type. We defined them, and we looked for them on the left-hand side of an assignment. And so now we want to grab the outer scope of the assignment, so that we can actually check that the connections are closed, that the errors are handled. So we grab the scope by saying, okay, well, the stack ensures us that the last element, the thing at the length -1, is an assignment statement. That means the thing at length -2 is a scope. So, well, it should be, because in Go you can't have statements outside of some scope, just by the definition of the language. So we want to grab that scope at length of the stack -2. We got the scope. And now we probably want to figure out, we probably want to only start looking for all the error handling and connection closing code after where our assignment shows up. So we can just get the index of the assignment by just iterating through this list of statements inside this block, inside the scope, and saying, okay, if the statement is the thing we're looking for, if it is the assignment statement that we got earlier, then assign this index, that to assign index, and break out of it. So we got the assign index. Now we actually want to have the logic of checking to see if there's a close after we've created a gotten a closer, or created a closer, rather. So assuming that closure var is not nil, if closure var is nil, then this analysis pass won't even be running. So we need to make sure that it's not nil from when we iterated over the left-hand side earlier. We say that we haven't found close. Now let's iterate from assign index to the end of the list of statements in our scope, and see if any one of those statements corresponds to a close operation. And I haven't actually shown you how to implement the close operation here, or checking that a statement is a close, but we just want to check, assuming we've written that function out already, we'll say, okay, is this statement a close? And then we pass in the identifier, the closer var, and if so, we say that we found it. So now we actually have a situation where we can report an error if we have not found a close. This is the first instance where we report an error to a user. There's a method on the analysis pass type called report f. And so we're going to pass in, we can pass in a position. All of these objects that we get from the AST have positions associated with them. And so we can just pass in one of those positions. In our case, we can say, we want to probably say something like, because there's no close called on this, we want to get the position of the identifier that corresponds to the closer variable. So we'll say, hey, here's a token position. The close method is not called, and pass in the name. Now, let's see if we can improve this somewhat and make it more robust, because we probably, yeah, it's important to check that we closed some connection, but we also want to possibly check that we haven't called close multiple times. So let's, instead of keeping a Boolean, we'll keep a counter saying num closes is 0. And then every time we encounter a close, we increment that counter, num closes plus plus. And so now we can say at the end of that block, if num closes is 0, do the same thing as earlier. We say that, hey, you have not called the closer. Otherwise, if it's more than 1, then you called it multiple times, which is also probably not good, and point that out to the user. You could also imagine extending this to maybe handle defer, which is not much more complicated. It's just handling another kind of statement here. And you probably would just extend the isClose method. Now let's add our error handling logic here to check that we handled an error right after we created we did the assignment or the short variable declaration. So we assert that the thing after the assignment is an if statement. Now you could be even more robust about this, because in Go there's multiple ways of doing control flow. Like you could assert that it's a switch statement or an if statement with like a predicate at the beginning of it. But you also have to ask yourself, are those the kinds of patterns that I expect to be seeing in my code base? Are people using switch to check for errors? Likely not. So you can probably just do what fits your situation the best and say, okay, if it's not okay, so if this is not an if statement, or if it does not contain the identifier corresponding to error variable, so if the if statement condition does not refer to the error, then we're probably not handling the error. So we can report an error for that. Now there's here's another situation where you could probably check, if you wanted to check that we're actually returning out of the function or exiting some area of control, you might want to use something like control flow graph. That is another analyzer you can run, or like the SSA package, which is another other analysis information you can get. So let's go back to the isClose function. How do we check that that the statement that we have is calling close on some identifier? In Go, you have when you call like a method on something, and that's just a statement by itself, it's actually an expression statement. And so every single construct in Go has a corresponding node in the syntax tree. So instead of running through every node in the syntax tree, it's probably best to think about like which of these nodes do you actually care about. In this situation, we're looking for a call expression. We're looking for a method call to close. And so we grab these method calls, okay, corresponding to we grab them like if it is a statement, an expression statement, and it's a call expression inside of there, we check that it's a call expression being on this identifier, and we check that the selector expression, the identifier associated with it, is the same as the one we passed in, and we also check that the method's name is close. And so this should be good enough to check that you're actually calling close on that method. Now, in the case of contains ident, or checking that like some node refers to your identifier in some way, remember we use this to check that our error handling code in our error condition refers to our error. That's why we wrote the contains ident function. Here we probably just want to do a generic traversal over that node. The AST package has a method called inspect, or a function called inspect, and it will just call your function that you pass in on every single node down the tree. And so you can just pass in your function and say, hey, if the node that we're looking at is the identifier that we care about, in our case the error variable, then we found that identifier inside of, it's contained inside this node. Otherwise, we haven't. So that's what this function really just does. It's just checking that inside some tree that you have this identifier. Okay, so now if you actually ran this, you would see something. Well, first we want to package it up into some sort of tool. For Go analysis, you can use something called a single checker. There's also like a multiple checker version. This is what command vet does. But if you want to use a single checker, this basically creates a command line tool for you as long as you pass in that global variable corresponding to the analyzer we talked about before. So in our case, we write this checker at the top, and we after compiling it and running it, we run it against our test program or our test package. And it'll be able to tell us, hey, you call this a close function method multiple times. And you could try running this over arbitrary code, and it will be able to report and likely catch like if you've called close multiple times or if you haven't handled an error, unless you're doing something really weird like checking for an error but not actually returning or something like that. But now you know how to actually extend your analysis tool to handle those cases as well. So I want to conclude by saying, consider writing static analysis tools. It's not terribly difficult. If you first of all, just try looking at the pattern matching ones like RuleGuard or SemGrep. SemGrep, you just write it in a YAML file, and it'll be able to test those patterns against your code. But using the Go analysis framework is also pretty useful because all of the work has been done with you regarding type checking your program, parsing it, and all that stuff. You can just use these previous analyses that have been done to build up your own, and it's usually something like check some property holds for some value in your for some node in your tree, And in terms of writing a good static analysis tool, try to provide meaningful results. So make sure that there's not too many false positives, and if there are, try to adjust this tool. Otherwise, programmers won't want to look at it, and they'll just ignore it. And try to find something that will hit a lot of cases in your code base. And with that, I will say that the code for this code and slides will be up after the talk is over, and I'll pass it back to Erik.
Thank you so much, Akhil. That was great. I learned a lot there, especially at a higher level, just how many different routes there are into getting static analysis done on your code. You mentioned SemGrep, you mentioned the static analysis toolkit. There were a couple others in there too, and that's really cool to see that kind of ecosystem is so big.
Yeah, I mean it's something that I've used a lot of static analysis tools, but not something I've actually investigated implementing on my own. So I think this is something I'm going to have to play with.
And it's always good to
Go.
see how.
For Go.
You keep yanking my chain. Listen, as I was saying, in Go, it's always good to see how easy the tool chain and obviously the Go standard library makes it to actually be able to write these kinds of tools. So yeah.
I love that you're rocking the gloves.
I am rocking. Hey man, no shame in my game.
You know what's funny is all of the people in the Peanut Gallery channel commenting about like temperature outside in geographical locations across the country and world.
Yep.
But I don't think you understand. It's colder in here than it is outside.
Yep.
That is true. That is true.
We don't know what's going on. They're taking heat out of this room somehow because it's not getting any warmer throughout the day.
Which is quite interesting because if we do a studio shot at some point, like there's nothing but giant lights everywhere.
Yeah.
Indeed.
People, lights packed in here. Yeah.
I think they're messing with us. They're like
think
a
so.
bunch of complainers.
We'll show them.
They said, I thought this was a conference about Rust. So they turn up the AC.
Oh man.
I mean, I would much rather be cold than sweating, so,
Sure.
you know.
Sure.
Goodness.
Yeah. Well, there's also another part of the Peanut Gallery I thought was
Wait, hold on, hold on. We have some extra time, it seems like. So, Akhil, where's Akhil? I was gonna have him help me out with my Comcast bill. Sorry. Yeah.
I think, he reports to the CEO, I think.
Directly. I mean, the same way you can call Satya on his cell.
Exactly,
Hey, man.
Hey, what would you
I've got a problem with the MS Word.
That's his version. Ours is like, your printer's broken or something like that, right?
Oh, yeah.
Yeah. But there was an interesting thing in the Peanut Gallery. There's a new challenge. There's a swag contest. I don't know if you guys saw that.
I did not.
The swag contest is, and this is unofficial, so that is to say there's no swag if you win. But the contest is to implement
You can have this that I hold in my hand.
This wonderful air, the prime air. It's to implement the worst possible use case for generics.
Oh man, here we go.
So Peanut
You know what's funny? I mean, jokes on them. For me, I'm just going to assemble all of this. I'm going to write a book with all of them, call it Anti-Patterns and Profit.
Yeah, that's the old, I want to, what is it? There's 9 standards. I'm going to make a standard to standardize 10. All the standards.
And now there's 10.
Yeah, so you're going to, Peanut Gallery, go at it, do your thing, and then Erik is going to
capitalize
all of them and make them, by definition, the worst.
Yeah, goodness.
So who do we have up next, Johnny?
Up next, we have Linus Torvalds. He's now doing Go full time.
They're integrating Go into the Linux.
We have Linus here. I just don't think it's that Linus.
It is not that Linus. But the Linus we do have, Linus Lee, thankfully, is here to talk to us about what happens when toy languages grow up. So and
he spent a lot of time working on his own language.
Yeah, he spent a lot, and we're gonna have some questions for him after this because I want to know more about this.
It's called Ink, and I think that we're probably gonna have to add a day to the conference for Ink Day.
InkCon. Here first. This is InkCon.
Somebody's registering a domain. You know it.
Well, we got like goforhealthcare.com, go for enterprise,
compliance.
Yeah. So we got inkcon.com.
Yeah. Wow. I think Erik keeps trying to rebrand this conference. Turn it into something that it's not. I'm not sure where that's coming from, bro. Some deep dark place inside of you, away from him, Satan. Anyway,
I love all languages.
All right, so. Without further ado, let's get into this. Mr. Linus Lee, tell us what you got.
Thank you. Today I want to talk about programming languages, and specifically toy programming languages. So languages that you might not use at work to build things like databases and servers and your production-grade services, but things that you might build for a side project or to solve a very specific kind of niche problem. I've spent the better part of the last year, and actually the last couple of years, building various little different toy languages and with Go. And I want to share a little bit of both what the process was like, what I've built on top of it, and then also how you might go about implementing your own toy programming language. Building a language is a little bit like this XKCD, where you start out with a problem that you might want to solve. Maybe it's about building a database, or maybe it's about solving a particular audio kind of engineering issue. And you start with a problem and you say, you know what, this problem would really be great to solve if I had the language that's just perfect for it. And you start working on the language, and of course the language isn't something that you build overnight, over a weekend, over a couple of weeks. It's a month-long, year-long kind of project, and so it consumes all of your time. And that's a little bit what happened with me too, but I do think that building a language is a really fascinating way to learn about different parts of a computer you might not come face to face with on a day-to-day basis. And so I want to share what that process is like for me. In a previous version of this talk that I gave earlier this year, I talked a lot about a language called Ink. It was a language based on, built with Go. It's a dynamically typed scripting language. It looks a little bit like this, what you see on screen. And I spent the last 2 years using this language, using the interpreter and the compiler that I built for it, to build things like Notes apps and Twitter clients and various kinds of personal tools that me and a few other people use. And Ink was my first programming language that I built on top of Go. And so while it was useful, it also contained a lot of little design mistakes and learnings that I had to get over the last 2 years. And so earlier this year, I started working on a second version, or sort of a successor to Ink, if you will, called Oak. And so most of the rest of this talk will be about Oak, the language, how it works, breaking down exactly how I built it using Go, and then some things on top of it that I built using Oak that might be interesting to talk about. When you're building a toy language, you're not really trying to replace something like Go or Rust or C++, because those are powerful general-purpose languages that are meant to be used to build anything from lower-level programs like databases all the way up to web apps or even more complex high-level applications. With a toy language, you're more targeting at a specific problem, or maybe you're scoping it down just to be able to do the things that you care about. And I would say those things are in the scope of little languages. Little languages are everywhere. There are things like the bash scripting languages that you use in your shell, the JSX templating language, like configuration languages like YAML or TOML, or even one of my favorites, the Google WUFS language, the Wrangling Untrusted File Format Safely language, which is a fully featured language that you can use to write parsers that are memory safe, that you can use to parse untrusted files like media files that you get on your phone or network payloads that you might get to your server. My favorite example of little languages of all time is the awk programming language. If you haven't heard of it, there's a book called The Awk Programming Language written by the authors of the language. It's a pretty short read. You can read it over an afternoon and learn the whole language because it's so small. But it's one of those things where it's designed so carefully and so thoughtfully for a very particular domain. In this case, that's processing text files and streams of text files in a Unix pipeline kind of context. And all of these are examples of languages that are targeted at a specific kind of solution. And it's sort of a language-based problem-solving approach. Rather than writing a program in Go to, say, process files or write configuration, you're using another language to do it. And I think little languages are an interesting approach to solve problems. And maybe if you write a toy language, little languages are an interesting way to think about what your language might be targeted at solving a problem about. So why might you want to build a toy language? The biggest reason for me is fun. Not only is the fun in building an interpreter or compiler and being able to understand exactly how a programming language works, but also once you have a language like Ink or like Oak, you can build things on top of it. The Notes app that I use day to day is written in Oak. The Twitter client that I use to check my Twitter is written in Ink. And once not only is it the fun that you get from just building your own tools, but once you're building it on top of your own language, you're working with the syntax that you defined, with the semantics that you defined, with the tools that you built, with the details into the language that you've baked in just because you wanted it there, and you don't really have to care about scalability or availability or anything like that you have to consider for production-grade languages. And so building tools on top of your language can be really fun. I also think building a toy language is a great way of learning about different parts of a computer that you might not be in touch with in your day-to-day work. Things like memory models, things like the process model, or asynchrony and concurrency. How does your language deal with problems that happen when two threads try to write to the same memory location? Or what happens when you have to read a file and you want to do it concurrently? These are details that programming languages that you use day-to-day today have worked out for you already because they have to think about it when they're designing a language. So you don't have to think about it as much as you would if you were writing your own language and you have to define these behaviors specifically and exactly so you can then not only design it, but implement it into your language to be correct. So I think it's a great way of learning about these different types, different areas of a computer. And then sometimes, very sometimes, occasionally, toy languages or personal project languages can become production grade, with languages like Clojure or like Python having started as sort of personal projects that have now grown into production grade languages that large companies use to build their production products. If you've taken a university course, or if you've gone through another kind of tutorial on how to build a language before, you might have come across material on how to build an interpreter or compiler. And while that's what gets a lot of attention in the programming language world, how an interpreter or compiler works, how to do type checking, how to do parsing, I think there's a lot more to building a language, especially a language that's practical that you want to build stuff with, than just the interpreter and the compiler. And so even if you've taken a university course or encountered how to build an interpreter elsewhere, I hope to, through this talk, share a little bit about what else on top of it do you need to build to have a practical language. Things like, for example, if you have just the interpreter, the Go spec and the Go compiler doesn't actually tell you how the Go language interfaces with the rest of your computer. How does it do things like writing files or processing network requests? Those you have to define separately in standard libraries that you have to write for your language, or foreign function interfaces to the rest of the system. And those are things you have to explicitly design as well. Another important part that Gophers know a lot about is language tooling, things like code formatting and profiling for memory and CPU usage. How do you deploy your software? These are things that typical programming language tutorials haven't covered that I have to sort of discover for myself, and I want to share with you a little bit of how at least Oak handles it. So I want to dive a little bit into the interpreter because I think it's the most technically sort of interesting part of Oak, and share a little bit of how it works. But before we look at the interpreter itself, let's look at what Oak actually looks like to run. So Oak is a programming language written in Go, and that's a little bit weird, but what that really means is that to run Oak, you just start, type in Oak, enter, and like Python or like any other interpreted language, you get a REPL. And because it's an expression-oriented dynamic language, programs can be as simple as just numbers. So if I type in the program 100, it evaluates to 100. I can add numbers together. I can add more numbers together. I have strings in Oak, so I can say hi, I can say hello, GopherCon. You can concatenate strings together. Oak also has floating point numbers, so pi. Oak has composite types as well, so Oak has lists of numbers. And lists and objects in Oak are actually heterogeneous, so they don't have to be all the same type. So you can have a list that contains numbers and also strings and also things like Booleans and keywords. And all of these are just values that you can work with in Oak. There is no concept of pointers or slices or arrays. Everything is just lists and values and objects, which are defined sort of the way that you would see it in JavaScript, for example. And lastly, Oak has first-class functions. So for example, we could define a function called double that takes a number and returns 2 times that number. So I can then say double the number 10, we get 20. I can double it and then pipe it, which is a little fun syntax, to double it again. That's how you would do it. And then because Oak has first-class functions, you can use functions as arguments to other functions. So Oak has a standard library function called stdrange that just gives you a list of numbers up to that number. So we can generate a list of 10 numbers or 100 numbers or 1,000 numbers. But let's take a list of 10 numbers, and then let's map it through the function double. And all this is doing is taking the list, and then for each element of the list, doubling the number. And so Oak has first-class functions. It has numbers, strings, the typical sort of values that you would expect in a programming language. But all of this is, again, a Go program. So Oak is just, if I witch it, it's about a 7 megabyte Go binary. And so when we look at how the Oak interpreter works, what we're really looking at is what is the Go program that takes the source code, the text strings that I'm typing into this REPL, and how does the Go program understand it, what it's supposed to do, and then actually execute what the program is meant to be doing within the program. Oak's interpreter, like most other interpreters or compilers, works in a sort of a pass-based way, where we start with initially a representation over source code, which is the representation of a program that humans can read and process the most effectively, and we progressively transform it down to other representations of a program that the computer can more easily understand. So to a computer, the source code of Oak is just a string. It's very opaque. There's no structure to it. And then we're going to go to token streams and syntax trees, which I'll explain a little bit, that contain more structure so that the computer can look at it and understand what the program is supposed to do. So let's look at the token stream and the syntax tree and what that looks like in practice. This is a little playground that I made recently to be able to look at, type in any Oak program and look at the token stream and the syntax tree representations of a program that correspond to the program that I'm typing in. So let's start with a very basic trivial program with the number 100. The number 100 is a program that just evaluates the number 100. And the token stream is a representation of a program where every symbol in our source code has been singled out. And the token stream is just a stream of these tokens, each of which are a symbol that means something in our language. And so, for example, in this Oak program, number 100, there's 2 tokens. We have the first token at position 11, which is line 1, column 1. It's a number literal, and it has the value 100. And then there's a comma that's automatically added by the tokenizer in the same way that Go has automatic insertion of semicolons at the ends of lines. That's something that I borrowed from Go. But really, there's only one meaningful token in our language in this program here, which is the number literal 100. If we add to it the number 200, now we have 3 different tokens that are meaningful. We have the number literal 100, we have the plus operator, and we have another literal 200. And you'll see that the tokenizer, one of the abstractions that the tokenizer peels back is the white space. So no matter how many spaces I add here, there's only three tokens. So as you'll observe that as we transform it down more to a machine understandable representation of a program, some of these abstractions that we don't need, like white space, will be removed by these progressive steps. The other thing that's interesting about our token stream is that it's just a flat list. There's still no sense of nesting or hierarchy. So for example, if we have 1 plus 2 plus 3, let's put that inside a list. Semantically, there's nesting in this program now, where we have a list value, and we have numbers that are being added together in sort of nested expressions. First, you add 1 and 2, and then you add 3 after it. All of that's inside a list. But our token stream doesn't actually represent any of that nesting structure. We're just looking at, again, a flat list of symbols. We have a bracket, we have a number literal, we have operators, other numbers, and then a right bracket to close it off. And so the syntax tree is when the nesting structures come in to our program. So let's look at the syntax tree together with our token stream representations of a program. So now we start again with a number 100. Again, this is just a program that evaluates the number 100, and we have a single token that represents the number literal. But our syntax tree now adds additional information for the computer to be able to understand our program. So now we've gone all the way from just a binary blob of a string to, OK, we're looking at an integer, and that integer has the value 100. If we add another number, the token stream is still a flat list of just number plus operator number. But somehow, in the path between the token stream and the syntax tree, we have to go from this flat list to a tree that says, OK, now this program is a binary expression. It's adding something together, this plus. The first thing that we add is an integer with a value 100, and the second thing that we add is an integer with a value 200. And so you can see we're adding a little bit more structure, we're adding a little bit more nesting, and we're getting closer to something that's structured enough for the computer to be able to understand our program. If we add another number, you can see there's even more nesting. So now there's a binary expression nested inside another binary expression. And let's look at a more complex example. So we can use the print line function from the Oak standard library to have a program that prints hello world. And in this program, there's a lot of structure. There's enough structure here for, say, a program to be able to tell you exactly what this program does. So at the top level of this program, it's a single function call, right? So our syntax tree says, OK, here's a function call. The function that we're calling is the result of a property access. We get the identifier std, and we get the identifier print line, and we access the print line property of std, and then we call that function with the argument string hello. If we add other arguments, our syntax tree will tell us, yeah, here are other arguments, integers 2, 3, and 4. And so again, going from the program to the token stream to the syntax tree, we're adding structure. We're removing arbitrary information we don't need, like white space. And the last important thing that the syntax tree step does, or the parsing step does, is it detects syntax errors. So for example, if I remove the parentheses at the end here, well, now we don't know when our function call ends. And so that's not evident in the stream because it's a flat structure, and we're not really giving a lot of attention to the nested structure of a program text. But in the syntax tree representation of a program, we have to know when our function call ends to be able to tell you what the arguments of this function are. And so when we can't find that parenthesis, our parser is saying, hey, there's a syntax error, there's an unexpected end of input. Or if we have a symbol that we don't expect, it'll say there's an unexpected token. So a lot of the rest of the interpreter work is going to be implementing the transformations to go from the source code to the token stream and then to the syntax tree. So let's see how that works in practice. To go from the source code to the token stream, we're going to have a path called a tokenizer. A tokenizer in Oak is a single function defined on the struct called the tokenizer. Its job is to go from the source file representation of a program to a slice of tokens, a list of tokens that we can work with.
And while it's doing that, it also keeps track of each token's original position. So if you look back at our tokenization step or token stream, you'll recall that each token has some position information about which line it's from and which column it's from. And that's important because whenever there's a runtime error for, say, failing to look up a variable, we have to be able to tell the user, here's where your error occurred, or a language will be undebuggable. So our tokenizer does that by keeping track of the file name, the column, and line for where we are while we're parsing our source code. And to parse our source code, we also need a slice of runes and an index into that slice to go along our list of characters and tokenize it. In practice, the way that we do it is a big switch case. So this tokenize function that abbreviated here is going to go through our string, which is our program. And for every character, it's going to say, what is this character? Maybe if it's a plus sign, it'll say, well, the plus sign is a valid token by itself. So we're just going to take that plus sign and say, this is a token, that's the plus operator, and ship it off to our list of tokens. If it's, say, a letter, we'll say, maybe this is the start of a variable name. So we'll parse the rest of the variable name, look at it. If it's a keyword like if, we'll consider it a keyword and ship it off as a token, an if keyword token. If it's a more general variable, we'll just say this is an identifier. If it's a string literal, it'll start with a quote. So if we see a quote, we'll say, OK, the rest of this token must be a string literal, and we'll parse it until the next quote. We'll slice that string off from the rest of our source code and consider that our token. And so it's a big switch case, looking ahead a few characters to see what the next token is going to look like, and aggregating all together into a single slice of tokens that represents our token stream, which is what we see on the left side here. The token stream within the oak interpreter is represented as a slice of tokens, and each token is just a struct that keeps track of the type of the token it is. So is it a comment, is it a comma, is it a parenthesis, its position, which we saw earlier, which is just a column and a line number, and this payload, which is the string value of the token for the tokens for which that is relevant. So things like string literals, numbers, comments, those need to know not only what type of token it is, but also what exactly is the value of that token. What's the value of the string, or what's the value of the number that this token represents? And this is where that payload goes. And on the left here, you can see a shortened version of all the different kinds of tokens that Oak has. So comments, comma dot, all the parentheses and delimiters, operators, keywords, as well as all the literal values that our language supports. We need a token type for each of them. Once we have the token stream, the next step is to go from this token stream to the syntax tree, and that's the job of the parser. If you've worked with parsers before, you might understand that Oak's parser is a simple recursive descent parser. What that really means is that the parser looks a lot like a tokenizer in that it keeps a track of a slice of tokens, which we got from the tokenizer. And then we have also an index that points into that list of tokens to see exactly where in the token stream we are as we're parsing along and popping out syntax tree nodes of our tree. The actual parse method on the parser is recursive descent. And all that really means is that for every token that we see, we're going to check, OK, what is this token? And then what syntax tree node might that be starting? So let's say if it's a number, then we're just looking at a number syntax tree node, like an integer 100 or something like that. If it's a keyword, like the function keyword that starts a function, we might say, OK, actually, we need to parse a function. So we can invoke the parse function method that's defined on a parser. And the parse function method is going to look at the next thing after the function keyword. Let's say maybe that's like an argument list, and say, OK, now we need to parse an identifier. And so we're going to call the parse identifier method, and so on and so forth. So it's parse methods recursively calling each other to be able to parse whatever comes next in our list. And we keep parsing through our list of tokens until we get to the end and we have all of our syntax tree nodes in our program. And what results is the syntax tree that has the structure that we saw earlier in our demo. The syntax tree in Oak's interpreter is represented by a single type, which is actually an interface type, rather than a concrete struct type as before. One thing that's interesting about this sort of series of transformation is that as we go along further in our steps, we get more structured information. And so when we were just looking at the token, every token could look about the same, because every token is really just a type and some extra string value. Whereas now we're at the syntax tree stage, and each node needs to know a lot more information about itself. So the information that a string literal node needs to contain is very different than what a function literal node could contain. A function looks very differently than a string. And so each of these different types gets its own struct. String literal has just a payload of what the string literal contains as a string. a function might have a name, a list of arguments, and some extra body. An if expression contains multiple branches that it needs to know about. And so all of these are represented by different struct types, and they're all wrapped up in an interface type that we call AST node for abstract syntax tree node. Once we have a syntax tree, now we have enough information to be able to run our program, in a sense. And so it's time for the evaluator. The evaluator is the thing that actually runs our program. It's a method defined on this thing called a context, which I'll get to in a bit. But all it does is it looks at every syntax tree node, every bit of our syntax that's now in a hierarchy, and says, OK, what is this node telling our program to do? For example, if it's a string, we just generate a value that represents that string and passes it off to the next thing. If it's a function call, we might look for that function and then call it. If it's a branch of an if expression, we might evaluate the condition and then call that branch if it's true or false. And you'll see there's an extra bit of scope here, and the scope is just the information that encodes what variables are in our current local scope. And so the eval_expr function is actually responsible for traversing through our tree and going through and actually running the program that the tree represents. Let's take a look at what all of that comes together to be when an Oak program is actually running. So again, the Oak interpreter is just a Go program. And so in this Go program that is running an Oak program, we have a big global interpreter state that keeps track of all the state that's relevant for the running Oak program as a whole. Things like, what are all the open files that our Oak program has opened? What are all the open network ports? It also keeps track of a global lock, which is just a mutex on the global interpreter state. And this ensures that even if multiple concurrent functions are being called in Oak, only one bit of the Oak program is running at any given moment. So if multiple files are being opened and multiple requests are being served, one convenient way that Oak gets around the problem of data races is we just ensure that at any given moment, only one part of the Oak program is being evaluated. Only one eval_expr function is actually running through our source tree or our syntax tree. And that means that we don't really have to worry necessarily about multiple parts of our Oak program writing to our variable or stack at the same time, or complexities that arise from parallel execution. So in the global interpreter state, there's a lock, as well as all the information that the program globally needs to keep track of. In an Oak program, an Oak program can import other Oak files. And this is the way that Oak sort of does module management in the way that you might do in Lua or in JavaScript. And so within the global interpreter state, there's multiple contexts or multiple files that we might have open. So in this case, we might have started out by running main.oak, but main.oak might have imported library.oak, which might have in turn imported math.oak. And in each of these files, there's a separate chain of variable scopes. Because if you think about it, a variable in one file shouldn't be able to access other variables from a scope in a different file. And so each of these files need their own chain of variable scopes that the evaluator can look up variables from. So let's look at what that looks like in practice in our source code. The global state that we just talked about is represented by this engine type right here. This is the mutex, the interpreter lock that makes sure that at any given moment, only one bit of Oak program is running. We have some other sort of synchronous bookkeeping stuff. We have a file map for keeping track of which file descriptors correspond to which open files that we've given to our program, as well as some error reporting, bookkeeping, things that I won't cover in too much detail here. But within this global interpreter context, every file gets this thing called a context. It's a little confusing, but this context type keeps track of, OK, for every file, what's the local scope, what's the global scope that corresponds to that open file. So if we start to define variables in our Oak program, then all those variables will get stuffed into this context data type. It has a pointer to which global context that this context belongs to, which engine it belongs to, this root path thing, which is bookkeeping for being able to do imports nicely, and then it embeds a scope type, which is the Go type that represents the local scope of variables. And so in every scope, there's a map that just maps variable names to the values that they represent. So if you define a variable A that has the value of number 2, then it's going to be a map that has the string A, and then it's going to map to the value that corresponds to the runtime representation of the value 2 in our Oak program. And each scope has a pointer to its parent scope, because a local scope, if the variable doesn't exist there, looking up a variable in the local scope might involve looking it up actually in its parent scope. So you can see how all that comes together to form a runtime state that looks like this, where there's a global interpreter state, And then each scope is sort of changed to its parent scope until you get to the global scope for each file. And then all of that is wrapped up in a little context that corresponds to each file. So now, going from the source code to the token stream, to the syntax tree, which has enough structure for our interpreter evaluator to run in this runtime, this is all we need to have an Oak interpreter. With all these parts coming together, we can now take an Oak program, give it to the interpreter, and have it do something that we want, like adding numbers together, or creating objects and running through objects, or looping through lists. All of that's possible with just this basic infrastructure. But there's a lot more to Oak than just its interpreter. For example, with just the things that we've covered here, Oak can't write to your terminal yet. It can't save a file. All of those things are outside of the realm of just the core language, and they're things that you have to build into the runtime separately as things that you can call out to. I'm going to highlight 3 things that are outside the interpreter itself, outside the language, that I think are really important for Oak and for languages in general, that I found interesting to implement within Oak. The first is concurrency, how Oak handles concurrency. This is important because if you want to open files or respond to web requests, one thing that I use Oak for a lot is writing web servers and web applications. And for that, you need concurrency because otherwise you're going to have to block on every web request, which is unideal. And normally, when you're implementing your own toy programming language, to do concurrency correctly, to have multiple threads of execution running at the same time, you would need to implement your own event loop, your own little local state that keeps track of which requests are in flight, which functions are paused or unpaused. But Go makes this really easy for Oak because for every request, for every file that we need to open, for every asynchronous task, we can just spawn a new Go routine. And we can tell the Go routine, do this task, read a file, or write to this network port. And then once it's done, run this bit of Oak code later. So when we give Oak a callback that says, write this file and then call this callback when it's done, we can implement that pretty literally within Go, and Go's Go routine and its runtime, or Go routine system and its runtime makes that pretty easy for us to do. We don't have to implement any sort of asynchrony ourselves in the interpreter. Oak also has a growing standard library that I wrote from scratch for doing things like string manipulation, formatting strings, dealing with cryptographically secure randomness, and dealing with setting up HTTP servers and the like. And the standard library is important, 1, because it enables you to write actually useful programs like web servers, and 2, because I think it's a good way to test your program if you're writing a toy language, test your language if you're writing a toy language, to make sure that it feels good to use under your hands, and also set some conventions, things like naming conventions, things like how complex can functions be, how does it feel to have a really long functions versus a really short functions. And these things are things that are not built into the spec of the language or the interpreter. They're things that you have to sort of conventionally define as you use it. And writing the standard library was a good way to exercise my muscle in actually feeling out how the language is supposed to feel to use. And then lastly, language tooling. This is something that Go does really well, and I wanted Oak to do this really well too. And so I have a little more to say about language tooling, specifically that Oak has self-hosted language tooling. What this means is that Oak's code formatter, its bundler, its compiler, JavaScript compiler, its testing and documentation tools, all of it is written in Oak itself. So for example, this is a screenshot of Oak format, oakfumt, which has directly inherited the name from gofumt, and it formats Oak code. You can give it a file, Oak program file, source file, and it'll format it and spit out another Oak program that's indented correctly, and all the spaces are normalized and correct. And it's written in Oak. Go has something similar, where gofumt, godoc, gotest, all of these things are written in Go itself, right? And the value of writing these tools in the language itself, self-hosted language tooling, is 1, that improving the language actually improves the tooling itself. So if Oak gets faster, oakfumt, oakbuild, all these tools are going to get faster alongside Oak. If Go gets more secure or more memory safe, all of those benefits are going to be inherited by the tools too. And I think that's a great benefit of writing self-hosted language tooling. Not to mention, you're exercising the language, so you're making sure that it works correctly and there aren't any bugs. The other underrated benefit of the way that specifically Oak and Go do it is that for both of those languages, parts of the language tools, the functions and the basic data types that you need to be able to use to write things like parsers and linters, they're built into the standard library. And for Go, that means there's libraries like Go types, Go AST, the Go static analysis tools that you saw earlier in the conference. Those things are part of the Go standard library or part of the more popular packages that come with Go, like Xgo tools. And what that means is that it enables sort of an ecosystem of tools that are compatible, and it makes it really easy to write things like linters for your code, or things like code formatters, on top of that initial foundation in the standard library. So this tool that I showed you earlier for showing a token stream and a syntax tree that results from an Oak program is actually written in Oak. This is a web app written in Oak itself, both the front end and the back end. It's compiled Oak down to JavaScript. And all of this output is generated by an Oak program that is using Oak's standard library support to be able to parse Oak code itself, which is a little bit kind of recursive and mind-bending. But what this means is that it's really easy to write Oak programs that work with other Oak programs. And language tools are fairly straightforward to write, because I don't have to write Go code anymore to write these tools. I can just write Oak code that knows how to parse other Oak code. So within Oak, there's a few different tools that I've written so far for code formatting, for auto-indenting code, a bundler that takes a bunch of different Oak files that import each other and producing a single file, sort of like a Webpack for the front end, and a compiler that compiles Oak code to the web to be able to write tools like this, because I like writing web applications. And Oak has similar enough semantics to JavaScript that compiling it to JavaScript is not that difficult. And then in testing and documentation tools, Oak Test and Oak Doc are not written yet, but that's something that I'm hoping to stamp out in the near future. All this time, having written Ink a couple of years ago and then now working on Oak, I've come away with a few takeaways about writing interpreters and programming languages in Go itself. Most of them positive, some of them things that might mean that Go is not the best language for a job. But overall, Go gives you all the basics. It gives you good enough performance where you can, if you design your interpreter correctly, you can compete with slower languages like Python and Ruby. It gives you easy cross-platform support, because if you write your runtime in Go, then Go's cross-platform support is there to make sure that that language will work on all the platforms that Go supports. Go also gives you a static binary executable when you build your language. This is actually much more important for an interpreter than it is for maybe a web server, because in a web server, you can have multiple different files that you need to run your program, and you can just put it all in a Docker container, ship it off to your server. But when you're writing a language like Oak, you want to be able to give a single binary to your user, to an Oak programmer, and say, this is all you need to write your own program. Just run it on your source code. You don't want to give them 100 files that import each other and say, OK, set this up on your computer, and then you'll be able to run Oak. So the fact that Go compiles to a single binary is actually really, really important for how Oak is practical to use as a language. Oak also gives you just enough control over the runtime in-memory representation of Oak values, of things like how is an Oak floating point number represented, or how is an Oak list represented in memory. And it turns out that's important to be able to get any kinds of performance tweaking that you want to do in your language, or to be able to do things like make sure that your language doesn't consume too much memory when you're running your programs. And then my favorite part of using Go for writing Oak, specifically for the type of language that Oak is, has been inheriting Go's state-of-the-art runtime. So Oak is a garbage-collected language, just like Go, and that means that Oak just inherits Go's low-latency garbage collector, and because it's state-of-the-art, Oak also has that state-of-the-art garbage collector. Go also has great CPM memory profiling tools. If you haven't checked out Go's pprof support for looking at what functions are costing you CPU time and what variables and what values are eating up your memory, I suggest you check it out, because it's been fantastic to be able to work with. Whenever I have a memory leak in Oak, it means that I don't have to write a memory profiler for Oak. I can just inherit Go's tooling and run it on run the Go memory profiler on my interpreter, and that'll tell me which kinds of values are eating up all my memory in my Oak program. The runtime also has a downside, though, which is that because it has all this great support for these tools and instrumentation, inheriting Go's complex runtime means that sometimes doing some things in Oak can be impractical. For example, one thing that Oak can't really do that well, or at all at the moment, is interface with a graphical interface. So usually the way that you build a GUI is by interfacing with a C library, like SDL2, or an OS-specific library, like Cocoa on Mac. And to be able to do that, your language has to call out to C functions. And because of the way that C Go is, and because of Go's sort of thick runtime layer between the rest of the operating system and your Go code, it means that calling out from Oak into a C function, calling an Oak function that calls a C function, and passing values in between them is kind of tricky, something that I haven't worked out yet. And so sometimes Go can't quite be low level enough. So depending on what type of abstraction you want to work out with your toy language, Go might not work for you. But I have found that for Oak, Go has been good enough for me to build the types of apps that I've wanted to. If you're interested in building interpreters or compilers in Go, or just in general how programming languages work after seeing this talk, the first resource that I'd recommend is Torsten Ball's Writing an Interpreter in Go, or Writing a Compiler in Go. I've heard a lot of great things about this book. I haven't read the book yet, but I've heard lots of podcasts and talks about it. And you can find them at interpreterbook and compilerbook.com. And both of these books walk you through building a practical toy programming language called Monkey in Go, and every bit of source code line by line. And I think it's a great practical way to learn how to write your own language. The way that I learned it is through Crafting Interpreters, which is an online ebook. There's also a hard copy, but again, written in Java, but walks you through the same sort of conceptual ideas on how an interpreter works. There's a few other resources on the slide, but the three other ones I'll highlight are TinyGo, GopherLua, and Auto. All of these are Go interpreters, Go-based interpreters that are targeted at a real production language that people are using to build real products. So these might be interesting to look at for looking at how a Go interpreter might implement something a little more complicated and a little more real world, a little more like the real world, like a JavaScript interpreter. My favorite part of working on a toy programming language in Go has not necessarily been the writing, the interpreter, or the compiler, or the parsers, although that's educational and I'm learning a lot. My favorite part is actually in having built a language and then now being able to write side projects with it, write things like my notes app with it, or write things like a context manager with it. Ramsey Nasser, who works on the Clojure compiler for the CLR, he says languages represent different ideas on how to capture human creativity on a machine. And I think this is the thing that makes building languages as side projects really special. It means that when you're solving your own problem, instead of using the rules that other people have defined to solve your programming problem, you can define your own words. You can lay out your own vocabulary for how you think about a problem, for what these like primitive values and rules that you work with are, and you can define your own constraints by which you try to build things that you want to build or solve problems that you want to solve. And I think that's a really powerful part and the really motivating part of trying to build your own language. And so if you're more interested in writing programming languages and how Oak has done it, there's a blog post where I talk a little more about programming languages and writing them at linus.zone/pl. I have a website at thecephalus.com where I talk more about software and also other things. And then the Oak project itself is open source. It's just a Go program, after all, at linus.zone/oak. So if you want to go and check it out and fork it and build your own variations on top of Oak, you can go there and read the source code. It's not that complicated, only a few thousand lines of Go. And I hope after this talk you'll be able to make sense of it and all the parts that go into it. And with that, thank you. I'll pass it back to the crew.
Thanks, Linus. That was an amazing talk. It's actually something I've really been interested in for years, and I keep telling myself I'm going to make an attempt at writing a compiler and interpreter and never get around to it. Linus, if you've got a few minutes, I'd love if you come over here and chat with us a little bit. Maybe come take a seat over next to Aaron. We'll get him to slide over here.
Yeah, come on down.
So it turns out we're going to have to cancel InkCon, it sounds, and start planning OakCon instead.
About the domain InkCon, you're out of luck. Yeah, all right.
All right.
Oh yeah, additional body heat.
Yeah.
Welcome
Right?
to the party.
It is chilling the
Where
studio.
were you for the whole rest of the day? So you mentioned a number of books. One of them that I read years ago that I thought was interesting is the Nan to Tetris book. Have you read that one? The Elements
I have
of
not, but I've
Computing
definitely heard about
Systems?
it a couple times.
Yeah, so if you've not seen that book, it's actually, I think, a series of 2 Coursera courses, and it starts at kind of like Boolean logic and builds up that into like building logical gates and NAND gates, and then how you can combine those to get to like an ALU for a processor, and then how do you build an assembler on top of that. And then it gets up into building a compiler, a VM, and the book is like this big. I kid you not. It's very like abstract. It doesn't go into a lot of the details about like how do you actually implement this thing, but it does provide like some test suites for, you know, this is what the output of your assembler should be given this input and things like that. So it's kind of a fun project as well for people to get started.
Yeah, definitely. In general, diving deeper into the low-level parts of a computer has been, certainly writing a language has helped me get a better understanding of it. And in general, I think I've developed an appreciation for sort of having that transparency into the rest of your computer, like what really is going on when you're writing Go code below the Go compiler itself. What's the operating system doing? What's the CPU doing? Although the talk that I just didn't cover it, as you get more deeper into this programming language world, I think a lot of the fun is in being able to understand what's going on in that lower level.
Yeah, that's learning a little bit of hardware was also another one of those eye-opening things. And you're like, wait, what do you mean that the the chip can be interrupted in between instructions, you know?
And you realize it's not as pretty as you kind of always assume, you're trained to assume.
Yeah, and even assumptions we make about time, right? You're like, oh, well, I'm going to sleep for 1 second. Like, and when you find out what that really means, right? Like, well, it could be a second, it could be 6 days. Like.
Right, it's the minimum. It's a recommendation.
Yeah.
I think my favorite version of that is synchronization between cores in a multi-core CPU, where really what's happening is that multiple cores are just sending signals to each other in the hopes that like they get there in time for the other core to get the information in time for the cache coherency to work. And like it mostly works out. But there's no like physical guarantee that it's going to happen. It's just that, you know, statistically,
it's all UDP.
It'll work. Yeah.
It was the same thing. Like I used to work in video space. Well, I still work in video space behind Learn TV, but working on like video multiplexing and stuff on like linear feeds, you actually have to look at CPU ticks. Because you can't really look at time, and because you can slowly like drift, and so you end up having to like kind of drop frames and things like that to get back aligned based on you woke back up at this interval and you thought 1 second passed, but it was really 1.01 seconds, and over a month that becomes
right for audio and video. Yeah, and then at that point you're also having to worry about things like the operating system interrupting you, because your program might, you know, other things might be going on, like the CPU scaling down, or maybe you're getting like a notification and the CPU needs to handle it, and yeah, it could happen anytime.
Yeah, because like at the end of the day, time is just, oh, well, here's the frequency of the CPU, and
everything is a lie.
This many cycles has happened, so we think that's how much time passed.
Right.
Well, so I mean, right there, everything is a lie, right?
Oh yeah.
I guess it doesn't apply to everything. Just computing.
The world, everything's a sham.
But you know, we're talking about, when we say full stack, we're talking about the full stack here. Right, so there's a lot of pieces that you know, starting at the bottom of the laptop all the way up to the screen. It's a lot of stuff to keep in your head.
Definitely.
So, you know,
a lot of assumptions are made the whole way.
Yeah, right. So how do you keep that stuff straight? Like when you're building a programming language, and where would you start?
That's a good question. I don't think I have a good answer to that actually, but I think, well, so first of all, I think at any given moment there's only sort of a window into that tower of abstractions that you can keep in your head. So if you're an assembly programmer, you're certainly understanding what's going on at the hardware layer much better, but then you're totally not understanding, for example, like if I send this network packet, where is it going to go? Like that's out of your sort of window that you're keeping in your head, right? Or if you're writing at the like JavaScript layer, it's impossible to think about the assembly that's being generated. And so I think you have that window, and in some senses, I think full stack is more about like expanding that window a little bit in both directions. So for example, when I'm writing Oak programs, the window is extended a little bit into when I'm writing my program, what is this actually running? What is the actual assembly code that's running on the machine? What's the Go code that's running to support this program? But I'm not thinking so much beyond it. I'm not thinking so much under it. There's that window. But I do think thinking about growing that window is helpful.
So one of the sort of the things that we value, right, about Go itself, right, is the fact that it makes a lot of things easy to wrap your head around, right? But it took a lot of work, right, under the hood to provide sort of these abstractions, right, that we use as sort of the end users of that product, right, to be able to sort of write the programs, you know, to be as readable as they are, right? So, but we know that, you know, even based on what we're talking about now, we know that there's so much, you know, effort and ugliness, you know, sometimes that goes into providing this nice sort of end user.
So you're saying they're beautiful on the outside,
they're
but
beautiful
ugly
and ugly on the inside. Yeah, exactly. You know where I'm going with that, right? So I'm curious if you experienced some of that tension, right, when you were sort of, you know, coming up with Go, and says, well, as a user of Go, right, because you're in the unique position of basically being the one who's creating it, and you have to actually use it to actually build stuff. And what's that pull and tension like for you?
So Go, I think, at least for the things that I've used to implement Oak, Go has been really great about it. I've only touched the beautiful parts, and I haven't had to dive in so deep into the more complicated things. But the things that I have looked at how, for example, Go implements the map, its own built-in map type, or the Go GC. And for the GC especially, and a little bit for the map as well, there are some, I wouldn't say ugly, but I'd say some details that you have to worry about for the GC to be able to work And for things like the GC that have to work concurrently and for the map that has to be really efficient with the hardware, you have to worry about things like, well, on certain CPUs, caches are this size, they're this big, therefore this data has to fit in this area of memory, and for that we need to like pack these bytes into this shape. And digging into that, how other more production grade languages implement it, has peeled back the curtain a little bit, and I wouldn't say ugly, but I'd definitely say they're worrying a lot about the details.
And so now every Oak program essentially needs to include the Go runtime inside of it, right?
Right.
Okay, so that's like one assumption that's made, unless you really wanted to go all out, build an assembler in there.
And there is actually, so if you look at like university courses or other materials on like building a compiler, a lot of them will focus on, okay, let's build a runtime from scratch, or like let's compile all the way down to assembly. And the trade-off that I chose to make is, if you do that, then you're going to spend months and months writing the runtime. And if you want to go from that to like, I want to send an HTTP request, you're going to spend forever covering all of that space. So I've chosen to sort of build on top of the Go runtime, and that means that I can build, maybe I'm not implementing my own garbage collector, but I am writing a thing that I'm using day to day with it, which to me is a little more satisfying.
Yeah, I mean, the great thing about that is you also benefit from any advancements to the runtime that the Go team makes.
One of my favorite examples of that has been, I think with Go 1.17, there was a linker change that made all Go programs like 7% faster. And I was like, okay, this release of Oak is 7% faster because it goes 7% faster.
Well, do you take credit for that? Do you put this release, we've made Oak 7% faster?
Exactly, thanks to the Go contributors.
Well, there you go.
Plus me.
You were talking about the windows, like you got that for free, but your window had to get a little bit bigger just to understand, okay, well, it is 7% faster. If I'm going to take credit for this, like I better understand what happened and why, why they did it and all that kind of stuff too.
Yeah.
And so how would you compare building your own language in this way, a compiled language and stuff, versus how a lot of people predominantly will create like DSLs and things like Ruby because of kind of the dynamic nature of the language? Is there an advantage to doing it this way, or is it just another approach because you get to run an efficient runtime without bringing the like Ruby interpreter along for the ride?
Yeah, that's a good question. I think it's a spectrum. So, for example, in Oak, for the like object implementation, the map implementation, it's like an object in Oak is like just a map with string keys, like JavaScript. It's just using a Go map under the hood. I could probably write my own type for it. That's like might be a little bit more efficient depending on like what type of, like maybe I can benchmark it and find the right use cases. But I'm leaning on Go, and that's on sort of further down one extreme. The other extreme is I just sort of like make a Go DSL that it just has a simple syntax for like string keyed objects. And with things like Ruby DSLs especially, I think it's a spectrum of like how much are you leaning on your host language, or how much are you defining a world for yourself? And I would say defining a world for yourself is maybe a little more fun. But certainly if you're writing something practical, it's totally possible to define, especially with more flexible languages like Lisp or Ruby, to make a DSL that maybe has all the syntax that you want, which is more what the effort is going to at that point. It's like API design. But you don't have to worry so much about implementing a parser, implementing a runtime, or things like that.
I guess the other advantage would be just kind of the advantage you get from going to a statically typed language, right? It becomes easier to actually compile time check things. Static analysis might actually be slightly easier to kind of do on your Go program versus...
Exactly, yeah.
So let's talk about the GIL for a little bit, the Global Interpreter Lock.
Yes.
You said that, all of a sudden I had flashbacks. Oh, Ruby, oh my goodness, Python. So I think in your summary you mentioned that basically using a Global Interpreter Lock meant you didn't have to worry about multiple threads, maybe mutating the same variables, and you didn't have to worry about data races and contentions of that nature. That was something deliberate. That was a deliberate choice on your part. Is it in your mind? Is it something that you're eventually going to get to, whereby you want to make it thread safe, or is this sort of the design philosophy of Oak is to basically rely on a GIL?
It's a good question. I have a lot of thoughts on this. I think so. Within the Python community, GIL has been a hot topic. There's actually recent, really interesting work to remove the GIL from Python as well. There's like a Google Doc white paper going around. If you're interested in it, you should definitely look it up. It's really well written on removing the GIL but keeping the performance, basically. There's two parts of the GIL for both Oak and Python, I would say. One is the performance and the technical aspect of it, of like this was simple to engineer. The other part of it, though, is that having a GIL means that there's like if you start writing something, that's going to run to completion before the next chunk of work runs, and work can't be interrupted. So if you assume something at the beginning of your function running, that thing's going to hold true until the end of that function being called, or until the task being done, which simplifies the way that you think about your program, especially in concurrent programs. And so with Oak, the thing that I think I'll probably keep it, just because Oak doesn't have to, I haven't encountered a case where that's a performance bottleneck yet. And the benefit that I get from that is that programming in Oak is simpler just for me to think about, because I didn't have to worry about variables changing out from under me, because there's multiple threads of execution running, even though maybe I'm losing a little bit of performance as a consequence of it.
My follow-up to that is an Oak program still faster than a Ruby or Python program because it is relying on Go?
It is not yet, because of the interpreter design. So one of the things I mentioned earlier was Go is fast enough to build an interpreter that can compete with Python, and can is the keyword there. Oak's design is, the interpreter that I talked about in the talk is what's called a tree walk interpreter. So it builds a syntax tree, and then it walks the syntax tree, evaluating the expressions. And that works. That's sort of the most basic type of interpreter. You can make it simple. It's easy to understand. But if you want to go faster, you have to go down a few more levels, even deeper into that chain of transformations. You compile down to bytecode, which is what both Ruby and Python do. And I think if you design efficient bytecode, and if you write a good VM for it, a Go VM for a bytecode interpreter for a language can probably compete with Python or Ruby. But Oak does not yet.
Not yet.
Not yet.
Any plans to build a bytecode interpreter?
Oh, yeah.
And IR and everything?
Yeah, definitely. I've actually experimented with, Ink, which is the previous language that I built, has
almost
come back.
We got it back in the mix.
It has. I've built a bytecode
bringing
interpreter
it back.
for it.
Ink's coming back.
Come back. I built a bytecode interpreter for it. I used it as the learning project for learning Rust. Just maybe a little bit of a,
Hey,
that's fine. It was fine.
Coming back.
See, now you got to kick two of us out.
But design mistakes with a learning project, and I was trying to, I think, bite off too much at the same time. But I think it's something I want to writing a bytecode interpreter and a faster interpreter is something I want to do, figure out, and so I'll probably try that once I feel like Oak is at a good place to try to make it faster.
Very cool.
Nice.
Awesome. So I think it's about time we wrap up the day. Thanks for joining us here.
Thank you for having me.
Feel free to hang out while we wrap up the show.
Yeah.
But it's been just an amazing day with a bunch of speakers. Oh, one note I did want to make is CrowdStrike threw out a challenge to the whole how terribly can you use generics.
At first I was like side-eyeing. I'm like, why are you doing this? Then I was like, okay, I guess if we start identifying all the bad use cases right now, we can definitely help out
so
your book.
they've made some promises. Whoever has the worst use of generics gets a free plushie,
soaked in sewer,
and the lifetime promise of never being hired to work at CrowdStrike.
Yeah, so you get a cost benefit. You want a plushie soaked in sewer water, or do you want a job at CrowdStrike? So that's the trade-off that all our viewers.
So here's the question I want to know: what if it comes from a CrowdStrike employee?
Oh, man.
I mean, are they grandfathered into keeping their job, or do they immediately get fired?
Edge cases.
There you
go.
So this is the technicalities. It says never get hired, but they were already hired. So.
Yeah, I think you just put yourself on the blacklist for CrowdStrike for those kind of comments.
They're like, oh yeah, this is going to be bad.
Trash. It's not going to work.
So tomorrow morning we're going to start back at 8 a.m. Pacific. We'll all be here bantering for 10 minutes earlier. Take that as you will.
Please come join us. Please come. It's very early. We would love to see you all.
We're going to be cold. We're going to need the company. We're going
I'll be thinking of San Diego and Denver.
Oh yeah.
All places that are warmer than here.
I don't think Denver is warmer.
I'll bet the Denver Convention Center is.
Even the moon might be warmer than this place.
It's pretty high. I think they're skiing about this time of year.
You can get heat at the convention center, though.
You can get heat at the convention center.
Yeah. This is true. Please, Peanut Gallery, join us tomorrow. We would love to see you at 7:50.
Warm it up a little.
Yeah, warm us up. Yeah.
So I want to take a moment to thank all of our sponsors for making this happen. Again, thanks to Salesforce, Capital One, Microsoft for helping us bring this thing online last minute. Thank you to all of our speakers, Linus, Mark Bates, and all of the Lightning Talks speakers, which we're going to have plenty more coming up over the next 2 days. They put a ton of work into that stuff. Thanks so much to the GoTime team and their guests. Linus again. I'm just everywhere.
Thank you, Linus.
They're also going to have some more content coming up tomorrow and Friday. Tomorrow is an AMA with the Go team, and then they're doing the Gopher Say Family Feud style.
GoTime.fm/GS. Don't forget.
It's time for the troll
Stump
entries.
'em. Yeah, yeah.
Cargo build.
You gotta alias your Go command to cargo. That's the ultimate.
That's a good troll.
Yeah, right.
Oh, man.
Yeah, so also Peanut Gallery. Obviously, we've featured many Peanut Gallery commentary today. That will,
if you don't know what that is, you've joined us through finding us organically on places, on the GopherCon Discord, which you can get to from discord.gophercon.com.
Was up
It's not
there.
back there.
Yeah.
We were blocking it.
Okay.
If you join there, there's a channel called Peanut Gallery. All of the hosts were kind of hanging out in there, and that's where some of this commentary we're picking up. You can heckle us.
Heckle us, give us great
Tell
ideas.
us you know how to do the job better.
Yep.
That we're fired.
Almost certainly you all do.
I mean, we already have got screenshots of me with like my next Halloween costume face. We've got Johnny meditating, so let's round it out. We need the third MC.
There's a screenshot last year somebody got of me popping one of the confetti things in my office, wearing like 2020 like celebration glasses. Trust me, it doesn't get worse than that. Somebody's going to drop it back in the channel, I'm sure.
I bet it can get worse. Have you seen mine? I'm just saying.
Anyway, that should be your driver's license photo.
Yeah, I'll make sure to never get pulled over.
I'm sending it to GSAM here, our global security. I want it to be on his badge.
Yeah. All right, well, we'll make that happen. I'll have my badge tomorrow, my new badge. I wanted to take a second also to thank the crew. There's a crew of I don't know how many people doing all of the back end stuff, the AV, the scheduling, getting people in and out.
Running in here, fixing cameras and mics behind the scenes.
Turning the air conditioning down to 2 degrees. All of them, even you, whoever turned it down. Really, thank you. I mean, this isn't the last day. We're going to thank you guys.
Yeah, we've got people editing the videos. There's already a couple of them popping up on YouTube already. So yeah, there's a whole crew helping to make this happen behind the scenes and make us look good.
It's a Herculean effort, and we really appreciate them. We're just the faces that read stuff from the Peanut Gallery channel.
Yep.
Everyone else does the hard work.
And makes silly dad jokes.
And then also thank you to the entire crew that helps plan GopherCon, and this
Year after year.
had to like replan it. So planned an in-person conference and then had to replan it all. So Heather, Jose, Julie, the whole crew for doing all of this again.
So we planned 5 conferences in the last 2 years or something like that.
Right.
That's what it was.
Yeah. So when we get back in person, that whole team is owed a lot of hugs.
Yes, indeed. But yeah, obviously we want to thank you for hanging out with us today, watching the talks, jumping into Discord and engaging, meeting new gophers, and meeting people you didn't even know you had common interests. Like there's a Mainframe group that just got started. I think Kaylyn's about to run a meetup
slide
group.
into that startup.
Mainframe now.
It's going
Exactly. Who
places.
knows? I know, right? Yeah, startups are being created out of GopherCon. I mean, it's
I mean, you think about it. We're bringing back all of the old technologies.
Go
And
ball.
they're getting cool new names.
ball.
So mainframes are coming back, but they just need a new hip name.
Right.
Gopher Towers. I don't know. I mean,
Yeah,
Gopher
just
Towers. What do you think, Peanut Gallery?
It's just what came to mind.
Yeah, it was pretty bad. I'll give you that. But you got to start somewhere.
Mainframes 2.0. 3.0.
Mainframe 3.
Yeah, Mainframe 3.
Yeah, okay. I like it.
Yes, indeed. But yes, indeed. Thank you so much, and we hope you will join us again. What time are they joining us tomorrow?
8 a.m. Pacific.
8 a.m. Pacific.
And then also there is GopherTown. So if you've not been on GopherTown, it's a cool little virtual world. You get to wander around. When you bump into people, all your cameras pop up. You can sit down. You can play games with each other at the little virtual tables. There's sponsors hanging out in there. So that's a ton of fun if you've not jumped in there. That's another fun way to meet people outside of just looking at the text and the dots while people are typing.
And I mean, don't count out Discord though. This thing is on fire right now. I mean, how many channels? Is this 50 plus
I mean,
channels?
people keep asking for channels.
Yeah, not to mention there's a voice channel.
I mean, we had requests for like stock trading channel.
Yeah, there was a high frequency trading or something. Futures trading as well. Yeah.
They were getting any requests for cryptocurrency channels or something?
I don't think, there has not been an NFT channel yet. But now after this statement, there's going to be an NFT and Web3 channel.
Yeah, we should mint your picture. And
I asked someone, but they said they already copied it. It can't be minted or whatever. I don't know what
You can't right click on it?
You can't right click on it, apparently. It's not possible these days in Web3.
Web3 has no right click?
Nope. Nope.
Oh, man.
All right, thank you all so much. We will see you bright and early tomorrow morning.
See you, bud.